Good morning or good afternoon, everyone. Welcome to participate in our CVPR 2021 workshop, Autonomous Driving Perception, Prediction, and Planning. We stream this workshop on both Zoom and YouTube. If you don't know the YouTube link, please check our website. You can feel free to interact with the speaker and the organizers on the chat box. Also, you can ask questions on both YouTube and Zoom. As we know, autonomous driving research have a great impact on society in general. The goal of this workshop is to draw attention to problems connecting the whole perception, prediction, and planning stack. Furthermore, the workshop intends to foster the communication with researchers working on autonomous driving from both academia and the industry. We have 7 outstanding organizers. They have contributed a lot on the workshop. Aaron Lee is a research head at AWS AI. He also an adjunct professor at Columbia University. Peter is a director at Lyft Level 5 research team. I'm Yan from Cornell University. Sergey and Balaji are research scientists at Lyft Level 5. Juan is a professor at Stanford University. Jana is a professor at Georgia Mason University. Thanks again for their contribution. In the workshop, we have invited 10 keynote speakers from both top university and top autonomous driving companies. They will share their perspective and awesome research works about autonomous driving on the workshop. As we know, Raquel is a founder of Wabi. She also a professor at the University of Toronto. Killian Wimberger is a professor at Cornell University. He works on machine learning, computer vision, and autonomous driving. Dasar is a professor at Stanford University working on robotics. Anka is a professor at UC Berkeley working on robotics. Charles is a research scientist at Waymo Research. Chen is an engineer director at Waymo. Sergey is a professor at UC Berkeley working on reinforcement learning and robotics. Sanya is a professor at the University of Toronto. She also leads a team at NVIDIA. Arun leads a team at Aurora. Shenlong will join UAUC as an assistant professor. Previously, he worked at Uber ATG as a research scientist. Since our workshop is a whole-day event, we split the invited talks into 3 sections. In each section, we would have 3 or 4 speakers to share their awesome works. At the end of each section, we would have a Q&A session. In the Q&A session, we would select the questions from both Zoom and YouTube. You can ask questions about all the talks in the section. Furthermore, we have 3 post sections in the Gather Town. In the Gather Town, you can watch the spotlight video and also discuss the papers with others. We encourage all the attendees to join the Gather Town at that time. Finally, we would have a panel discussion section with outstanding researchers to discuss the interesting questions about autonomous driving. We present the schedule detail in our website, ADP3.org. Also, we show the YouTube link on our website. Please check it. We would stream our workshop on both Zoom and YouTube. You can get the Zoom link in CVPR virtual platform. However, if you not register the CVPR, you can watch the workshop on YouTube for free. We would select the QA questions on both Zoom and YouTube. You don't have to worry. if you use YouTube. We encourage the speakers to directly answer the questions on the chat box. Thanks the authors for their submissions. At the end, we got 17 papers in total. Each paper is assigned at least 2 reviewers to review. Finally, we accept 11 papers. The accepting rate is 64%. All the accepted papers have a spotlight videos showing our website and also the gather town. If you have time, please watch the video that you are interested in. All the works are really good. Based on the review and the discussion, we have selected 4 best paper nominees. They are Imagine the Road Ahead Multi-Agent Trajectory Prediction via Differentiable Simulation, Pilot, Efficient Planning by Imitation Learning and Optimization for Safe Autonomous Driving, Domain Adaptation with Morphologic Segmentation, HDMapNet, an online HD map construction and evaluation framework. Congratulations! Finally, we have do a discussion. We got the best paper. It is Imagine the Road Ahead Multi-Agent Trajectory Prediction via Differentiable Simulation. The authors are Adam Weilesos, Daniel Payman, and Frank from UBC. Congratulations. Thanks for your awesome work. That's our introduction. The next part would be the invited talk section. In the first section, we would have 4 speakers. They are Peter from Lyft, Killian from Cornell, Dawson from Stanford, and Raquel from Wabi and Toronto University. Thank you for your listening.
Hi, everyone. Let me introduce Peter. Peter is a head of research at Level 5 division, where he lead a team working on machine learning planning and simulation technology for self-driving cars. Prior to Lyft, Peter was the co-founder and CEO of Blue Vision Labs, a company that developed large-scale localization and mapping solution for robotics and AR. The company was acquired by Lyft in 2018. Peter did his PhD at Oxford Robotics Institute and worked at Google, Facebook, Microsoft Research, MetMind on computer vision and machine learning system. Then let's watch.
Hi, my name is Peter Andriuska and I'm the head of research at Level 5. In this talk, I would like to tell you about machine learning planning and simulation my team is working on. So what I will cover is my views on the limitations of the current self-driving technology that is adopted across the industry. And then I would like to tell you about the Autonomy 2.0, which is a machine learning first approach to solving self-driving. And that is composed of 3 key pieces: machine learning planning, machine learning simulation, and large-scale data collection. And what I would like to convince you about is that this is a very promising approach we should be all going towards to. Before we dive in, let me tell you a little bit more about Level 5. So we are part of Lyft, and now we are becoming a part of Toyota Woven Planet. We have more than 300 people across California and London. We are operating our in-house fleet of autonomous vehicles, and we are working towards development of L4 and L5 self-driving technology. What we are also doing, we are organizing a tutorial on the data-driven autonomy, which is very much something I will be talking about here as well. So if you want to learn more, please just visit www.selfdrivingcars.org and you can hear more there. So let's dive in. So I would like to start telling you a little bit more about how the self-driving cars work today. It's a self-driving car that has a number of sensors, cameras or lidars that allows us to see the world. And the first thing to do anything for self-driving car is it needs to understand what's around it, which means like the position of other cars, cyclists, pedestrians, position of other lanes or traffic lights. When it knows what's around it, the next task is being able to tell what's going to happen, which means where is everybody going, such that you can predict the future. And when you know that, the car plans its behavior, which is motion planning. And finally, this plan is executed, and the entire cycle repeats again. When you look at this stack, and you look how much machine learning is used in these individual steps, what you discover that in the current technology that is widely adopted across the industry, the amount of the machine learning is used, but not to solve each step. In particular, perception is more or less machine learned, but when it comes to planning and simulation, this is still very handcrafted solutions. Just to understand then why, when the car is planning the behavior, the most usual approach that is used is optimization of expert-based cost function. You are trying to find the trajectory that keeps the vehicle enough space. It sticks to the middle of the lane. It trades off different cost factor about comfort and safety. And this generally works. But one big disadvantage is that it's very difficult to scale and to new scenarios. And moreover, this process needs to be repeated for each new geography. Furthermore, testing of the stack is also takes a lot of time on the road, which is expensive and limits the speed of iteration. On the other hand, Autonomy 2.0 is a machine learning first approach to self-driving that is trying to solve all pieces using machine learning, which is mostly in the space of solving planning and simulation using machine learning techniques. And finally, to power all these algorithms, we need a lot of data. So how do we get all this data? And we're talking about that in a bit as well. But it has a number of benefits. So instead of handcrafting the behavior of what the car should do, this behavior is learned from the human demonstrations, which is much more scalable approach. And testing can be then mainly offline using machine learning simulation. Given this, a significant benefit is that the performance of the system increases the more data you are training on. And what it also allows you to do is to build the entire stack just once and then deploy it many times. You just need to collect different data from different countries and retrain the model. And that allows very rapid scalability across different geographies. So this would not be possible without Autonomy 1.0. Okay, now let's talk about each of these three elements: machine learning, planning and simulation, and data collection in turn. As discussed before, handcrafting the behavior of what the car should do is very expensive and has limits in the complexity of situations that you can handle. So what you can do instead is to train a neural network that learns from human demonstrations to drive the car. It looks something like this. We are feeding the network the input what's around the car. This is coming from the perception and the HD map of the area, and the network is producing the steering command of what the car should do. So to make the thing safe, we are also applying a safety net that limits the behavior of what the car should do only to the safe ones. And there are many different ways how you can train this network, ranging from imitation learning, perturbation training, or closed loop training, that I won't be able to go into details of due to the time. But the main takeaway is that the more data you are training this system on, the better it works. And that's one of the big benefits. To see this, then here is a system that was trained only on 3.5 hours of human data. And you can see that even with this little data, the system can actually already keep the lane and drive in it. When you though add more data and you train on 1,000 hours, what you see that the behavior is more stable, and but generally already like this simple behavior can be learned from just a little data. The situation gets more complicated with the complexity of scenarios. So here is a car that is coming to an intersection behind another car, and as you can see, it cannot handle stopping towards the lead car. But as you train on more data, then this behavior is successfully learned, and the car can wait for the green light and then just follow through the intersection, keeping the safe distance to the car in front of it. Here is another example. This is waiting for traffic light on an intersection again. And the network is not sure when to start moving, and that leads to a collision. And as you train on more and more data, this behavior is successfully learned. And as I said, none of this is actually scripted or engineered by the engineers. This is all learned from the human drivers. Next, this is how it looks when you put it on real cars and let the network drive a real car. So here is a scenario where the car is nudging to the row of cones that are blocking the way, and this was also learned from the demonstrations captured in the world. Here are a few more examples that of handling unprotected left turn, handling the cut-in, and also nudging around the vehicles. And this is something that we do. We are improving the performance of these systems. There is still several open questions. What's the best way how to train machine learning planning systems such that they scale and deal with the complexity of the real world, but this is very, very promising. Okay, let's talk about machine learning simulation, which is one of the components of Autonomy 2.0 stack. To understand this, let's first explain how the self-driving testing happens today. It starts with identification of some feature or block that you want to develop, that you implement, and then you test it on the road to see how well does it work. And based on that, you debug whether it's working or not working, and that informs you to make changes. The problem with this approach is that it's extremely expensive and scales very poorly. And also it's not reproducible, which makes this testing very difficult. Until the same situation happens on the road again, it takes a while. So instead, the question is, how can we best test the performance of self-driving technology offline without the need of much road testing? This doesn't mean we will not need any road testing, but it's much less important in the development cycle. So what is simulation? So simulation is basically ability to replicate the real world experiences that you would encounter on the road offline without actually needing to go there. So this is the view at the how the self-driving car sees the world around itself, as you've seen before. And the goal is to be able to replicate these kind of experiences, both the usual and unusual, and see how the self-driving car performs in these situations. The most naive approach that is widely used is called log replay, that you take a piece of a recorded scenario that actually happened on the real world, and you basically replace the behavior of the car with the new behavior that you developed and see what happens. The problem with this approach is that the environment is non-reactive, which means that if your behavior is different to the one that you actually did on the road, other cars or pedestrians don't react to it, which makes the evaluation very difficult. You can make it better by scripting the behavior of other agents, or use a simulator that already exists, such as Scala, to get the reactive behavior from other traffic agents as well. But the problem is that this doesn't scale in terms of complexity. You cannot script all the possible situations that everybody might do or that might happen. So our approach that we are using at level 5 is we believe that the only way that we can achieve very realistic level of simulation, we basically have to learn it from the real world. And this way we can bridge the gap between the reality and the simulation. We recently published this work at the ICRA, so please feel free to check it out. I will provide you a very brief overview how does it work. So you can train a neural network on historical observations and get it to predict the future. And this, you take a bunch of data, you run it on a cluster of computers to train a neural network, and you get your neural network that you can then use for simulation. And then during the testing, you basically replace every agent with this neural network and get the neural network to control that agent during the simulation. And this is pretty simple, and it works surprisingly well. So just how it works, so you start with some initial state, and basically then in every step you use neural network to control all other cars as it seems in the real world. So here are some examples how are we using this. As you can see, like these are all synthesized scenarios. These are not real logs, and each agent is controlled by a neural network. And you can see that the behavior is almost indistinguishable from the one that you would actually see on the real road, even though like this is completely synthesized scenario. So you can see that if there is a red light, that the traffic for that lane stops, nobody's moving, and when you can also see that the cars are following the lane, etc. And none of this was scripted. This was all learned from the real-world demonstrations. And what we also observe is like it works better and better the more data you are training this on. And this is very promising, because to improve the performance, all you need to do is really to collect more data and get better simulations. So I hope that by now you are convinced that machine learning planning and simulation is a really promising approach that scales its performance with the data rather than with engineering, and that has many benefits. So the logical question then is, where are we going to get all the data to train these systems? And we will likely need to collect millions of miles of driving to see all different situations and to learn from them. If we were today to scale the current hardware to collect all this data, it would be very expensive. So the question is, can we use cheaper and low-cost commodity sensors to get the value out of them? And this is indeed an open question. But one of the benefits of having the fully machine-learned sovereign stack, you can answer these questions empirically by running experiments. And that's what we did. So here's an experiment that we also published at ICRA this year, where we took the data from the high fidelity self-driving sensors that contain LiDAR cameras and radars, and we decreased its performance by reducing the, the quality. But what we did, we increased the quantity. We trained on much more data of that type. And what we saw is that the performance of such system is better despite it's being trained on lower quality data than just training on a high quality data coming from, but in lower quantity. So this is very promising, and it says that perhaps we can relax some of the requirements in order to be able to collect large data sets and to use them for training autonomy 2.0. So in summary, what I wanted to show you in this presentation is some of the work that we are doing on machine learning planning and simulation, and that is very promising approach that we believe can solve many of the current issues of the current technology that is used in industry, and that also that we need large-scale data sets to train all the systems. So I would like to conclude with sharing with you 3 resources if you want to go deeper and help us solve these different problems that are still there to solve. We recently open sourced a 1,000-hour prediction dataset, which is the largest dataset of its kind and that can be used for training machine learning planning and simulation models. We also released an L5 kit, which is an SDK that allows you to train these models using the dataset. And it also contains a number of baselines you can take as a starting point. And as I said at the beginning, we are also organizing the tutorial where you will see videos from people working at level 5 talking about different parts of the self-driving stack, and also contain hands-on sessions where you can try to implement your own solutions. So please check it out.
Hi everyone. The next talk will presented by Dasar. Dasar is a assistant professor in EECS at Stanford University. Her research interests lie in the interaction of robotics, learning, and control theory. Specifically, she is interested in developing algorithms for safe and adaptive human-robotics interaction. Dasar received her doctorate degree in EECS from UC Berkeley in 2017 and received her bachelor degree in EECS from Berkeley in 2012. She is awarded the NSF Career Award, the NFOSR Young Investigator Reward, and the IEEE TCCPS Early Career Award, the Google Faculty Award, and the Amazon Faculty Research Award. By the way, you can ask questions on both Zoom and YouTube. Also, as a QA session, you can directly talk with professors from Zoom. Yeah, let's watch this talk.
Hi everyone, I'm Dorsa Sadik, and today I'd like to talk a little bit about some of our work in the space of autonomous driving, and specifically settings when our human modeling assumptions fail and we need to do something about that. So to start, let's motivate this by an example where we have a plastic bag on the street and you have an autonomous car driving down the road, and the question is, what should the autonomous car do? So you might want to act safe, and if you want to act safe, you might decide to slow down every time you see a plastic bag because maybe it is a real obstacle and you should really worry about it. And if you do that, what happens is that by the end of leaving that vehicle, you're going to feel really nauseous, and you're not going to feel very comfortable because you're stopping for every single plastic bag that you see. The other option is you just treat it as a plastic bag and assume that you can just speed up and go over it. But the thing is, we could also be in scenarios where maybe there's a person like holding a plastic bag, and you don't want to really detect that as something that you can speed up and go over, because that would be really dangerous and that could lead to all sorts of accident scenarios. So this kind of creates a very difficult challenge here. Like, how do we come up with the right objective with the right reward function? And how do we balance these different objectives that we really care about in the setting of autonomous driving? And this is a problem generally for robotics, but in the setting of autonomous driving, it's very apparent that we need to trade off between safety and also between efficiency and comfort and some of the other things that the human passenger in the car might really care about. And this becomes even more difficult when we are in near accident scenarios. When we are in challenging scenarios, these types of trade-offs become a bigger problem. So what I'd like to do today is to really focus on some of these near accident driving scenarios. And for the very first part of the talk, I'd like to talk a little bit about what we can do in terms of coming up with a policy for autonomous cars in these near accident scenarios. I'm going to discuss a hierarchical approach which combines reinforcement learning and imitation learning to kind of act in these near accident driving scenarios. And then for the second part of the talk, I'd like to switch topics a little bit and think about the human model specifically and what we can do as a better way of doing behavior modeling and modeling humans driving, again, when we are in these near the end of the risk spectrum, near accident scenarios. All right, so let's just jump into it. So the way we are looking at near accident scenarios, or the way we are defining them, is by using this notion of phase transitions. And the idea of phase transition is you have this egoed vehicle, the red car coming down the road, and it's basically driving everything in the environment is changing smoothly. And even though we have smooth changes in the world and in how the other drivers around us act, we might need to have a phase transition in our own action. So here there was occlusion, and because of the occlusion, we didn't really see this blue car. The blue car was coming down the road with like some smooth behavior, some smooth velocity. But the moment we see the blue car, we're going to actually slow down because we don't want to be in an accident. And that jump in our velocity, that jump that you see in the behavior of the autonomous car, that is what we are referring to as phase transitions. So these phase transitions are kind of interesting because these phase transitions are naturally creating a set of different modes of driving. So for example, in this particular case, you might be an aggressive driver that just speeds up, or you might be a timid driver that kind of slows down, or you might decide to like swerve, or we can call this anything. But the thing is that these phase transitions kind of allow us to think about these different modes of driving, and phase transitions would be switching between these different modes, where in each mode you have a smooth behavior, you have kind of like a within distribution behavior, and then you have these different modes that you need to switch between when you're in a near accident scenario. And that kind of covers like the setting and our decision making here. So the question we are interested in answering in near accident scenarios for an autonomous car is, what is the optimal switching between these different modes of driving if each mode is basically a setting without a phase transition? So the way we approach this problem is to think about each one of these modes of driving as a low-level driving behavior that could be learned, let's say, using imitation learning. So for each one of these modes of driving, we have data within the same distribution, and we can run imitation learning to figure out what is the right policy in each one of the modes. And imitation learning becomes actually a much easier problem because now you don't need to worry about data out of distribution, and you're basically training, like in this case, you're training a conditional imitation learning for each one of these modes, each one of these low-level types of behaviors. And then the high level basically does this optimal switching, the difficult part of how should we drive in near accident scenarios. And the high level, the way we're modeling the high level is by using reinforcement learning. And what reinforcement learning needs to do here is to decide how to optimally switch between different types of imitation learning policies. And again, this reinforcement learning problem is a much simpler reinforcement learning problem as opposed to me running reinforcement learning on the full-on autonomous driving. And then the reason is it's basically making decisions between these low-level, between these discrete number of actions that correspond to our different modes, as opposed to deciding between continuous actions of the vehicle, which could be pretty difficult. So we call our algorithm HRAIL, which is this hierarchical reinforcement learning and imitation learning algorithm. And the idea of our algorithm is that we have this high-level reinforcement learning that governs these switches between these low-level policies of the imitation learning. I'm not going to go into too much details of the algorithm, but I just want to show a few different evaluations. So we were really interested in settings where we have phase transitions, near accident scenarios where we have phase transitions. And we have studied 5 different scenarios. So these are the scenarios: a cross-traffic scenario, kind of like what I showed earlier, where there's occlusion and there's another car coming down the road, so you need to slow down. A scenario where another car, an incoming car, is coming in the wrong direction, so it swerves into your lane. A scenario where a car in front of you just like slows down. An unprotected left turn scenario, which is a very difficult setting where you have occlusion and you don't necessarily see the blue car coming down. And also a merge setting where you need to merge between these 2 vehicles because your exit is coming up. So you need to kind of like figure out how to merge between the 2 vehicles. And you can kind of like see our results using HRAIL in all of these different 5 scenarios, but the only one I'm going to show here for the moment is this merging. So let's go over this merging behavior. So I'm just going to show the video of it. So we have this red vehicle coming down the road, and basically it's after an intersection, an intersection is also coming up. So you don't want to change lanes in the middle of the intersection because that seems to be dangerous, but afterwards you would like to safely merge between the 2 vehicles, and that can be pretty difficult. So what we show is that if you run imitation learning only on timid data, what ends up happening is that your vehicle ends up just merging behind the blue car because it's not acting aggressively, it's very conservative, it's kind of like you slowing down for every single plastic bag scenario. If you act aggressively, what happens is that you end up doing this maneuver kind of in a dangerous way with very few headway between your car and the green car, the other vehicle. It turns out that if you do imitation learning, given that we have 2 different modes, and we never told imitation learning that there are 2 different modes, there are 2 types of distributions, and then you end up getting like out of distribution behavior, and you end up basically getting compounding errors where your red car is just like swerving all the way to the left. And if you're using HRAIL, then the idea of HRAIL is it can trade off between efficiency and safety in an effective way, and finish the merge in a way that is also safe in terms of collision rate and efficient in terms of completion time. So if you look at HRAIL results, which is shown in orange, it's kind of something that's in between the timid and aggressive behavior. In terms of safety, it's still pretty good, but in terms of efficiency, it ends up being quite a bit better than the aggressive behavior. Similarly, we ran a study where we showed these different driving behaviors to a user, and then we asked a user, well, which one do you prefer? And it turns out that people significantly prefer the HRAIL policy as opposed to some of these other baseline policies, which was kind of promising because it does the right trade-off. So just to summarize what I've been talking about, well, we are integrating reinforcement learning and imitation learning in these near-accident driving scenarios, and the proposed approach outperforms some of these baselines in terms of safety and efficiency and kind of balances that correctly. And this was a work that we presented at RSS last year, and it was actually a collaboration with folks at TRI. So that's great, right? Like, what does that get us? What that gets us is a policy for the autonomous car that figures out how to balance safety and efficiency. And the reason it figures that out is there are these phase transitions, so we can think about low-level modes and high-level decision makings to do these phase transitions correctly. So that's a very learning-based type of approach for what the autonomous car should do. And then in this work, I didn't do any type of like human modeling that was trying to get into the specific model-based or structures that we might have about how a human might act in the world. So in the second part of the talk, I'd like to take a more model-based approach and think about predicting human behaviors in near accidents and driving. So I'm not going to worry about what my autonomous car should do, regardless of what the other drivers do. What I'm going to worry about here is how I should predict how human-driven cars around me drive in near accident scenarios. And we were using ideas from behavioral economics to do this prediction. Okay. So remember this unprotected left turn example that I was mentioning earlier. So this is a near accident scenario where there is a car, this red car coming down the road, and this red car wants to make an unprotected left turn, and there is another vehicle that is part of the environment, and this other vehicle is this blue car that's coming down the road. So this is the scenario. And the question is, should the autonomous car, that vehicle, that red car, should it wait in the middle of the intersection? Or should it complete the merge? Should it wait for the blue car to pass, or should it complete the merge? And the setting is a setting where this light is going to turn yellow now. So the light for the blue car is going to turn yellow. And the question is, under that setting, what should the blue car do? So the blue car in this setting, if it assumes that what should the red car do? So the red car in this setting, if it assumes that the blue car is acting optimally, it should assume that the blue car is going to stop because that's a yellow light that's coming up. And based on that, it should decide to complete the unprotected left turn. But the thing is, not all drivers necessarily stop in these scenarios. Like, I've personally passed yellow lights many times, and that is a very high risky situation. And if that vehicle actually passes that yellow light, then you're going to be in an accident, which is not that ideal. So the question is, in general, like if you have robots or autonomous cars, they should be able to recognize that people, human-driven cars, pedestrians, like humans in general, they might act suboptimally when we are in risky scenarios, and we should try to capture that suboptimal behavior. We shouldn't just assume that, oh, everyone is just acting optimally in all scenarios, because if we do that, we might end up in some of these more accidenty type of scenarios. Okay. So how do we model humans? So this goes back to this question of how do we model humans? In the first part of the talk, I was using these imitation learning models. I was using conditional imitation learning, COIL, as my human model. Another way of modeling humans is assuming that, well, humans are optimizers of some sort of reward function, which is kind of a very similar way of saying, well, there's a policy for that human that comes from optimizing some sort of reward. And then this is, again, very common in human-robot interaction and autonomous driving as a way of capturing how humans act in the world. There's an optimal action. I have a rational, optimal human that takes that optimal action deterministically. But the thing is, I think we all agree that humans are not deterministic, right? They're not going to deterministically take an optimal action. And because of that, well, the field has moved on, and then there are other types of models. Specifically, there is this noisily rational model that exists that tries to capture the fact that humans are not deterministic. They might act probabilistically, and the probability of their actions is proportional to exponential of some theta parameter, some temperature parameter that's often referred to as a rationality coefficient, times the reward function. So there is kind of like this Boltzmann rational model of the human that captures rationality of humans and captures this non-determinism. But the thing is, this noisily rational model of the human, it still assumes that the most likely action of the human is the optimal action. And it really doesn't capture the fact that there are some settings where the most likely action of the human actually turns out to not be the optimal action. Maybe the most likely action is to accelerate and run a yellow light, and this model would not be able to really capture that. So what we would like to do is we would like to diverge and consider models when we are looking at some of these near accident scenarios, and consider models that are risk aware, that capture the risk and capture the fact that this most likely action might not be the optimal action. And to do that, the model that we're using, this risk-aware model that we're using, is based on ideas from behavioral economics, specifically from cumulative prospect theory. And our model is basically similar to before, where we're saying probability of actions of humans is proportional to exponential of some theta parameter times some reward function. But this reward function is not the old reward function. This reward function is now going to be a nonlinear transformation over the original reward function. So if you remember our original reward function, it's going to be a product of a sum of products of probabilities of outcomes and rewards of specific outcomes. And when you're considering this prospect theory idea, what we're going to do is we're going to make nonlinear transformations both to the reward function and to the probabilities. And let's very briefly look at what that nonlinear transformation is. So when we consider the reward function, if the true reward is shown in the dotted line, what this risk-aware model really captures is this particular nonlinear behavior where we are looking at high reward and low reward scenarios. If you're considering the end of the spectrum, it turns out that people have a hard time differentiating between different reward values. And when you're and we have a higher, smaller slope here. But if you're considering lower reward values, like closer to normal behavior, you're going to have a larger slope here. And this is the same exact phenomena where we are comparing, let's say, $1 and 10K, right? Like that scenario, 10K has a lot of value for us. But if you're comparing $1 million and $1 million and 10K, then all of a sudden 10K loses its value. Like it doesn't seem like much. And that exact behavior that it doesn't seem like much, that corresponds to the smaller slope behavior that corresponds to how humans act when we are near the end of the risk spectrum. So that is a transformation that one needs to do to the reward. Okay, and this model has a set of hyperparameters that one needs to fit to data collected from humans. And similarly, if you're considering the probabilities, one needs to make a set of nonlinear transformations to the probabilities as well. So again, the dotted line is a true probability, but then what we end up doing is we end up taking this risk-aware behavior that overweighs low probability events and underweighs high probability events, which is also the same phenomena as like why we buy insurance or why we buy lottery tickets. And again, this model also has a set of hyperparameters that needs to be fit to how humans act in these scenarios. All right, so that models our reward function, and then we take the same noisily rational model with this new reward function, with this transformed reward function. And we've actually ran a study where we have looked at this near accident scenario. And what we have noticed from that study is that we have high risk scenarios and low risk scenarios, where high risk is a setting where the light turns red 95% of the times, and low risk is when the light turns red like 5% of the times. And it turns out that in the high risk scenario, people are actually acting optimally. But in the low risk scenario, that is actually where the majority of people are preferring the suboptimal behavior. So they end up acting suboptimally. And what we have noticed is that if you run this noisily rational model and the risk-aware model, in the high-risk scenario where people are acting optimally, both of them fairly capture the behavior fairly well. They're at the same level. But then in the low-risk scenario, that's exactly when people are acting suboptimally, then the risk-aware model is going to actually capture that behavior better. So lower here is better. So the metric we are looking at is the KL between the true behavior and the predicted behavior. So lower is better, and our risk-aware model is able to capture how humans act a lot better in this scenario. Okay. Then the question is, okay, so I've modeled humans. Now, how am I going to use that model in the setting of interacting with humans? How should my autonomous car or how should my robot use these models? The scenario where a human and a robot are putting a set of cups on top of each other. And we have two settings where we have an efficient setting where you can build an efficient tower, but it's unstable, kind of like the Tower of Pisa. And then you have a setting where it's inefficient, but it is stable. So you're for sure making sure that the table is staying, the set of cups are staying upright. And you're making sure that it's always stable, but it turns out to be inefficient. And in this setting, it turns out that in terms of reward, it's better to take risks. It's better to go for that unstable tower. And when you're using this model of the human, this noisily rational model of the human, our baseline, it turns out that the baseline doesn't capture human suboptimalities. In this case, humans turn out to be overly concerned about the tower falling, and they don't take risks. In practice, they actually just go for the efficient tower because they don't want to, for the inefficient tower because they don't want to take risks. But the noisily rational model doesn't know that, and because of that, it goes for the same cup that the human goes for, and it has to come out empty-handed. But if you're using our model, this risk-aware model based on prospect theory, then we are able to capture this risk-aware behavior of the humans, the fact that humans are overly concerned, and based on that, we can collaborate better with humans. And you can consider like a similar setting where we have an autonomous car that models humans accordingly, and it can complement humans' behavior based on these risk-aware types of models. So just to summarize here, we are capturing suboptimal human behaviors using risk-averse human models that are motivated by behavioral economics. And this was a work that was presented at HRI last year. So just to summarize, I have talked about this idea of learning policies of autonomous cars in near accident scenarios and the fact that we can predict human driving behavior using a model-based approach by capturing structures that come in humans' behaviors and using those structures.
Yes, thanks, Dother, for their awesome talks. Our next talk is from Kilian Weinberger. Kilian is an associate professor in the Department of Computer Science at Cornell University. He received his PhD from UPenn in machine learning under the supervision of Lawrence Saul, and his undergrad degree is mathematics and computing from Oxford. During his career, he has won several best paper awards at SML, CVPR, ASDAS, and KDD. In 2011, he was awarded the Outstanding AAA Senior Program Chair Award, and in 2012, he received an AFS Career Award. He was elected co-program chair for ICML and AAAI. So let's watch the talk of Kilian.
Hello, my name is Kilian Weinberger from Cornell University. I'm talking about persistence priors. So essentially the setup of self-driving cars, the perception of self-driving cars is typically that mimics the machine learning setup. So you have a training setup, you collect data, you train your system, and then you deploy it, and you assume during testing you see, IID new data. And you're not allowed to keep training on the test data, of course. This works fairly well for the common case, and as we all know, there's the tail. The tail is these rare hard cases. Why are they hard? Well, for various reasons, right? So essentially, that always boils down to these are cases that are not like the training data. For example, they're too sparse. You have some domain shift, or you just have a lot of false positives because there's so much background, or you have extreme weather, right? That basically you can't prepare every possible weather condition in your training. So how do we attack this tail? And the good news is that we made the problem maybe a little bit harder than we should have, right? The reality is actually that most drivers don't just drive new routes all the time. In fact, quite the opposite. They drive the same routes over and over again. You commute to work, you commute to shopping, to schools, etc. Or even if you don't drive the same route every time, you drive on routes that other people have driven right before you. So what we could do is we could actually take this assumption and allow our system to keep learning on the test set. Basically say, essentially the hope is if you have a rare event, if you see it for the 10th time, maybe it's not so surprising anymore. Let me give you an example. So for example, this cardboard cop, right? So that's something the police sets up to dupe people into, slowing down, right? And the first time you see this, you're like, oh, there's a cop, right? So you slow down, but then you realize, oh, it's just a cardboard guy. But the second time you do it, well, maybe you still fall for it. But by the 10th time you drive by there, you're not going to fall for it anymore, right? You say, oh, well, yeah, that's the cardboard guy, right? Same thing when a road is closed and there's some, for example, a sign like this, or there's a hole. At the beginning, you're surprised, but then eventually you know, oh, yeah, there's this hole in the street, right? So essentially, my point is that of this tail, there's a good chunk of this tail that is rare cases, and we can't really prepare for it during training, right? For example, let's say we built the car in California, we ship it to Ithaca, New York. These are maybe a case that only exists in Ithaca, but it's persistent in Ithaca. So if we drive down there many times, maybe we can eventually kind of learn how to deal with it. And so this is maybe the way to kind of deal with a good chunk of this tail by saying, well, if these rare cases are repeated, then they're not so scary anymore. To this end, we are collecting a data set. I don't really have time to go over it, but we call it Ithaca 365. it's inspired by a similar data set from Oxford. We're driving down a route in Ithaca over and over again, many times under very different weather conditions and very different streets, like highway and urban, etc., downtown. And you can use exactly this data set to mimic our setting, the setting that I just said, that basically is saying, well, imagine you now get your car to Ithaca and you drive down this route. The first time you're in the setting, it's new, but the more often you're in exactly the same location, right? Now you've already seen it 50 times, right? Even if it's covered in snow, maybe you can deal with it. Okay, so how do you deal with it? And essentially, the first thing we're introducing is what we call a persistence prior. And this is a paper that's currently under submission. And essentially, we attack the bare bones problem. So given a LiDAR, point cloud, detect the objects in there. And in this particular point cloud, if you detect the objects, you actually find something very curious, right? Here, there is a car, right? And this looks very dangerous because this car looks like it's going to dash right into you. So you maybe slow down. But maybe it's just a spurious false positive. And if you actually, look at the camera, you can see, well, actually, yeah, that's just a street sign, right? So what's the problem here? The problem is that, well, we've never been here before. This is a new scene, and we only have a bunch of LiDAR points here that kind of look like the side of a car. So how could we tell that that's actually not a car? Turns out, well, if you assume that you maybe, the first time you are here, but you're not the first person ever to drive this road, right? So let's say there's other people who've driven this road before, and they've also recorded LiDAR data, and they uploaded it to the cloud, and we have access to it. Or, you've driven it before, and now this is the fourth time you're driving it. So let's say we have 3 previous traversals from previous days, and these previous traversals now have 2 advantages. Number one, we can see, oh, okay, wait a second, the same object is here every single time, right? If the same object is here every single time, it almost certainly is not a car, because cars don't do that, right? Or even if it's a car, it's not dangerous. It won't dash out in the street. The second thing is that actually here in our current setting, right now, the sign, the sign is really far away, so we only have a few LiDAR points. But in the past, we could record a whole traversal that goes really close to the scene and then drives past it. So we have many LiDAR points. So we have a pretty good idea of what it looks like, and this doesn't really look like a car anymore. All right, cool. So how do we incorporate this information into our detection pipeline? And essentially what we're doing is we are using something that Barnes et al. Introduced before as an ephemerality score, and we adapt it to our setting. So essentially, here's how it works. So imagine we have the scene, and we would like to know for every single point, given that I've been here before, what's our prior belief? Is that going to be part of an object, or is that going to be part of of some background? And we want to be very fast because we want to stick this into our perception pipeline. The way we do this is we pick, every given point. We can do this in parallel. We assume we have past traversals that are aligned. That's easy, right? You can do this offline. And then we do a nearest neighbor search. So essentially what we do is we take this point that we use the query. We want to know, is this point persistent across time, or is this something that is an object that's actually moving right now? And so we take this query point, we go through all the past traversals, we look what's in the neighborhood. Is this in a dense neighborhood, or is it in a sparse neighborhood? And what gives away that something is not persistent is if it's sometimes dense or sometimes sparse or always sparse, right? So things that like houses and so on, they are always in the dense region. So for example, here in the background, you see this is always dense, always dense, always dense. Whereas here, this object here in the front, this car, if I look at the first traversal, it happens to be there, coincidentally, there was also a car. So we actually have some points here. In the second traversal, there was also a car there. In the third traversal, there wasn't. In the fourth traversal, there also wasn't. So we have very few LiDAR points in these two and many here. That's what tells us that this is, an object and not not background. So how do we quantify this? We essentially take these balls of points and we compute the union of them. That's really easy. And imagine you color each point by the traversal it comes from. So this is the first traversal, second, third, and fourth. And now we can define a probability and saying, well, imagine you would randomly take a ball from this union. What's the probability that I get something from the third traversal? And we call that the probability of the third traversal. So how do we do this? We essentially count them and we normalize them. And now we get these probabilities that we can define as such: the number of points from the third traversal divided by the total number of points. And what you see here is that if these probabilities are roughly all the same, so high entropy, then it's an background object. But if they look like this, where sometimes there's something here and sometimes there's not, then it's basically very typical for a car or for a pedestrian. Like sometimes in this location there's pedestrians, often there's not. And so we take these probabilities, essentially we compute the entropy. To be precise, we say 1 minus the entropy, the KL divergence with the uniform distribution, and we normalize this. So if this has a large score, close to 1, this means that this is very, very uniform. This means that this is probably a background, like here. If this is a very small score, this distance is large, then it's probably an object. There's a very important specific case, and that is when there's no points at all. So we have a query point here in the current traversal. We look at our past traversals, and all look like this. They have no points. What does that mean? Well, in that case, it's very likely an object. But if there's nothing there in the past, right, this is not an object. This is not persistent. So this has a very low score. All right. So essentially, what's happening? We compute the score, this persistency score, and a high value means this is persistent. This is probably not a car, not a pedestrian. Low value means it's not persistent. We can now take this scene and compute this for every single point. Here's what we get. Right? So you see all this background here is persistent. Street is persistent, but these cars are not persistent. The beauty is this can be computed super, super fast. Right? We have a three-dimensional nearest neighbor search. You can do this very fast with KD trees on GPUs in parallel. Right? So it takes a few milliseconds to compute the score for every single point in this light up point cloud. All right, so once we have this is of course just a prior. It's kind of like, a little like segmentation, but it's just like object or not object, or persistence or not persistence. I can actually show you a few examples here real quick. So here's a scene of a, obviously a building and some cars. And what you can see here is that the car here is very clearly low score and everything else is high score. So it's red, whereas this is blue. Same thing here, we have two cars. If you look at the past traversals, there was nothing there. So it very clearly detects, oh, right, these are the points that correspond to objects. Let me also go over two failure cases. So here, and these are rare, but just to be fair, we want to include them. Here's a case where someone put up this fence, and we just drove by after they put up the fence. So in this case, in the past, the fence was never there, but now the fence is here. So what happens is the fence is a very, very low score, basically marked as not persistent. So, however, the cool thing is the next time someone drives by, this will be in the past traversal. So suddenly the fence will actually become more persistent, and very soon it will know to ignore the fence because it's always been there. And that's exactly what we want, right? We basically say, okay, well, sure, these rare events, the first time you see them, they are rare and they surprise you, right? But by the 10th time you see them, there's no big deal anymore. You know what it is. Here's another fail case. We have, parked cars, and turns out in this particular street, there's always cars parked. And so this car here actually is half red, and this one also a little bit, because it turns out in all the past traversals, there was actually a car here. So the cure here is you need more traversals probably. All right, so I can actually show you this on a little video. So here we're actually driving through this the self-driving car. Here you can see we can take the LiDAR point cloud and color it by the persistency scores. And what you see here below is actually the past traversals, right, of two previous traversals that are lined up. And you can see very, very nicely how these cars basically pop out as blue. This does not do any object detection, right? This is really, really important. All it does is this very, very simple millisecond neighborhood lookup, right? And it works really, really well, right? It's really, really amazing how well all these objects pop out here. Okay, so now that we have these priors, how do we use them? Well, we do, exactly what you think we're doing. We take our input LiDAR, we compute the persistency score, we decorate all the LiDAR points with this point cloud. All the point cloud with these persistency scores, and now everything is colored. So essentially, every single LiDAR point now has a value, and we stick that into our 3D detection, and out comes the bounding boxes. If you now go back to this motivating example of this sign, here we use VoxelNet. If you run VoxelNet on the original, just on the LiDAR point cloud, it actually does not. It does detect this sign as a car, so it's a false positive. If you color it, you can see that this here is actually, this is the sign. It's very clearly red, right? So VoxelNet gets the additional information. Oh, here are some points that actually are always there, and so it does not mark it as a car anymore. I can give you some few more examples to have time for it. 1 second. Yeah, okay. So here, for example, we have some false positives here, right? This traffic sign is actually classified as a false positive. In this case, actually, it has learned this fast traffic time has been here for a while. And so essentially, it has learned to ignore it, and it's no longer a false positive. Another example here. So here we have these here are, here's supposedly a car, and it's a cyclist, I believe. And of course, again, same thing here. It has learned that this is always there. So it doesn't detect a false positive anymore. Here again, a false positive that goes away because it knows that this is all red. This is basically not an object. Our last qualitative example, here we have 2 false positives. And again, I guess based on a fire hydrant, it learns the fire hydrant is always there, so it learns to ignore it. Are there also cases where it fails? Yes, here's one. Also, I'll let you decide if it's a failure case. Here on the left-hand side is, again, without our, just the raw LiDAR data. And you actually see here a false positive. It sees a car here. With our persistency score, this false positive disappears. However, a new false positive arrives, and that's this one. And essentially what happens is there's this object here, which is arguably not a car, right? But our persistency score realizes this has not been there in the past, so it makes this highly blue. Oh, sorry, here it is. Makes this highly blue. And given that it's highly blue in this corner, essentially that convinces VoxelNet that this actually is a car when it's really not. However, if this was a self-driving car situation, well, you still want to drive around whatever that thing is. So it's probably the safer way to err, actually. Just look at some numbers. So essentially, here we have various different baselines. Each one of them basically we can use with or without the persistency score. So one thing that's very, very nice about this prior is you can really stick it into any of the prior work. It's orthogonal to all the different architectures and methods to detect objects. And essentially what you see here is, without persistency score, and below is the mean average precision with persistency score. This is on the LIFT data set so that we can compare with other papers. And you can actually see, here the difference here is actually a very, very consistent improvement almost across all cases. If you essentially use these detectors with our persistency score, you get, substantial gains in accuracy. Finally, if you could just evaluate only the persistency score by itself and just say, how often does it, detect that something is foreground or background, or essentially what are its values for foreground and for background? And what you see is for background points, you get a very high value very often, whereas for foreground points, you very often get a very, very low value, right? So in itself, it's already a pretty, very good feature to detect if something is foreground or background. All right, in conclusion, essentially we're claiming that the reality of self-driving is actually easier than we've made it seem to be. Essentially, people drive the same routes over and over again, or even if you don't drive the same route over and over again, someone else has probably driven it. So if we are happy to share data, or we use our own data from past traversals, we can use that information to combat the tail of the distribution and to essentially make rare cases familiar cases, right? And familiar cases we know how to deal with. So we introduced this persistency prior. It's based on the ephemerality score from a group at Oxford University. And it's very, very fast. It essentially gives us a very cheap prior. You can see it down here on this video. And we can feed this into the detector and get, you can compute it in real time. And it improves essentially the results of all the detectors. And I want to thank my co-authors, the other faculty, Bharat, Mark, Wen, and Harry, and of course, all our students, and in particular, Yurong and Katie, who really went above and beyond and helped me a lot with making these slides. All right, thank you very much.
Thanks, Killian, for his great talk. I saw a lot of questions, so Killian will answer them in the Q&A session. Our next speaker is Raquel. She is a founder and CEO of Wabi and a full professor in Department of Computer Science at the University of Toronto and the co-founder of the Vector Institute for AI. From 2017 to 2021, she was the chief scientist and the head of the research and development at Uber ATG. So welcome, Raquel, give her awesome talk.
Thanks, Jan, for the kind introduction, and let's hope that this works. Can everybody see my screen?
Yes, yes.
Cool, fantastic, thank you. So today I'm going to be talking about learning to drive in highly dynamic environments. But before I do so, I want to tell you all the exciting things that we are doing at Wabi. So self-driving, if you think about it, right, is one of the most exciting and important technologies of our generation. And once solved at the scale, it's really going to change the world as we know it today. And if you look at all the progress that has happened since the DARPA challenge, so the industry has made meaningful progress, but commercial deployment is still very limited to very small and simple operation domains. And one of the problems that, the reasons for this is that the traditional approach to engineering self-driving vehicles results in a software stack that does not take full advantage of the power of AI, and instead requires really complex and time-consuming manual tuning. And this makes scaling costly and technically very challenging, especially when it comes to solve the long-tail events of unpredictable scenarios. Now, building on the lessons learned on the last 2 decades, Wabi is launching and tackling self-driving in a new way with an approach that really fully exploits the power of AI. And in particular, we have an AI-first approach that leverages deep learning, probabilistic inference, and complex optimization to create software that is end-to-end trainable, interpretable, and capable of very complex reasoning. And this, together with a revolutionary closed-loop simulator that has an unprecedented level of fidelity, enables testing at the scale of both common driving scenarios and safety-critical cases. Now, this approach significantly reduces the need to drive miles and miles on the road, as we typically see what's happening in the, with some of our competitors. And as a consequence, we can actually develop this technology safer and in a more, affordable way. Our first use case is going to be long-haul tracking. And the reason for this is twofold, is that there is a chronic shortage of drivers, and there is a really need for, enhanced safety. This is one of the most dangerous, professions that you can do in North America. Okay, so we are back up with the best-in-class investors in terms of deep technology, logistics, as well as the thriving Canadian ecosystem. And we launched the company last week, so this is very, very recent. It's very, very exciting. Announcing one of the largest Series A in Canadian history. Now, we have offices in both Toronto and San Francisco, and if you are excited about self driving and really pushing the needle, come join us. We are definitely hiring very, very significantly. All right, so given this, now let's talk about really the topic of the workshop, right? So how to handle situations where you have highly dynamic objects everywhere. So let's start by reviewing quickly how a self-driving system works, right? So the vehicle sensors the environment, then basically you localize with precision of a few centimeters so that you can see, you can basically import your high definition maps that tell you a lot about the environment without you even need to see anything. Then basically you can perceive the objects around you. You can predict where the different actors are going to be going in the next few seconds. And given this information, you decide to plan a maneuver, which you execute every fraction of a second, basically every time that you have a new measurement. Okay. So this is in a nutshell how self-driving systems work. Now, if you look at the work that we have been doing over the past couple of years, one of the things that we discovered quickly was that instead of treating these different models as different tasks that don't really relate to each other apart from an interface, is that you can train more and more of these things together, such that you end up getting better and better performance. And at the same time, you actually share computation and you can correct from mistakes that otherwise will be impossible with just a cascading approach. Now, one of the first models that we built for this was Fast and Furious, where the idea was very simple, which is that instead of having a separate perception and prediction system, these tasks are super related, right? You need to detect something and predict where it's going to be going. So we can actually do this with a single neural net, right? Where basically you can, given the raw sensor data, you can detect the objects and you can regress their trajectories in the next few seconds. And so this actually is a very, very simple idea, right? But it turns out that was a game changer in terms of how these systems actually work. I'm showing you here, some of the results at the time. And as you can see, so the single neural net can actually do perception, can actually, in terms of detection, tracking, as well as prediction into the future. So same color means that it's persistent tracking across the different frames. And these emanated points basically mean our predictions into the future. All right, so a lot has happened since then, right? And maybe one of the things to think about is what are the underlying sort of challenges when one tries to understand how the actors are gonna, what they are doing, as well as plan accordingly a safe maneuver. So if you think about it, right, one of the problems is that the future is inherently multimodal. What does this mean? Is that, given, for example, a situation where we have this vehicle here, right, on the left picture, we don't really know what this vehicle is trying to do. So it potentially can actually continue driving straight or turn on the intersection, right? So we need to handle the fact that we actually don't necessarily know what the future might look like. On top of this, it's not that every vehicle, independently behaves in the scene. Instead, there is very clear interactions between different actors. For example, these two vehicles might have different goals into where they are going. However, they are going to end up with maneuvers that actually react to each other so that we don't end up in a collision. And the third thing that is important to think about is latency, right? This is a safety critical application, so you actually need to end up with a decision in a fraction of a second. Otherwise, no matter how complicated and accurate your model is, it's not going to be safe. Okay, and typically the interactions, the multimodality, and the latency are things that actually sort of pull, different design choices as you basically, design what the autonomous system is for self-driving. Now, in terms of multimodality, we've seen recently a lot of work into how to predict these multimodal futures. Whether it is with Gaussian, a mixture of Gaussians. This is something that, for example, the Waymo team likes to do a lot. We like to do things, for example, with occupancy grids, which are a great representation. Basically, it's a non-parametric representation so that you don't need to commit to a fixed number of modes. You can also do this in a non-parametric way. This is also a representation we like quite a bit. Where the idea is that you can sort of enumerate the set of possible trajectories and then build a probability distribution over those. So by definition, this will be multimodal. And other types of ways to handle multimodality is by maybe building an autoregressive model where you sample, and given every sample, you basically unroll into the future. So if you look at these ways of handling multimodality, what you really see is a trade-off between the expressivity of the model, how complicated it's going to be, how good potential it's going to look at the, predicting the future, and the memory and time complexity, right? So you typically do a compromise between these things. Now, if you look at how these models have really been used in the literature, is that this uncertainty is done at a per actor basis, meaning that these models typically predict the marginal distribution of trajectories for every actor in the scene. And this is problematic in the following way. So let's look at this with an example. So, and one of the problems inherently to this is the fact that they don't really think about the motion planning task. They basically stop at the prediction task. So if you are, say, a self-driving vehicle and you're predicting the marginal distribution of each of the actors, then the question is, how are you going to plan a safe maneuver? Well, one thing you can do is like sample from the distribution, from the marginal distribution of every actor, and basically you will end up with a lot of different possibilities of what might happen. And this might seem very overwhelming for the self-driving vehicle because, given all these possibilities, it needs to react, right? So we're going to end up with overly conservative motion planners in order to handle, all these different things. However, if you think about the problem, this is not really what happens, right? In this particular scenario, there is maybe like two different things that might happen, not this, all these different possibilities, the cross product of your samples, right? And in this case, right, what might happen is that these vehicles might yield to you, and then you can pass, or they might not yield, and then you have to brake. Right. So if you look at this, right, so in order to do better planning, one of the things that is important is that we would like to model the joint distribution of all the actors such that we can precisely model what are the possibilities of what really might happen in the scene. Not this, cross product of all the possibilities that maybe one day will happen, right? So this is a much better way to model prediction. All right, so let's look at how we can actually do this and how we can build a motion planner that is able to take these sync consistent samples. So in order to do this, we're gonna go through different pieces of the model. So first we need to perceive the world by detecting the actors of interest. Then we need to learn a distribution that is able to sample the diversity of what might happen in terms of how the scene together might unroll, right? Taking into account your sampling from the joint distribution of all actors. Then we need to learn to do this in a way that is actually diverse. We're gonna score every one of these possibilities so that we have a notion of likelihood. And then I'm gonna tell you how to actually design a planner that is less conservative while being super safe. All right, so let's get into this. So let's start with how we can actually detect objects. So the idea is very simple, right? You have your measurements. This can be multimodal. Okay, it doesn't need to be just LiDAR, but for simplicity, let me just illustrate this with the LiDAR. You have your representation of the maps, which is very important for prediction as well as for planning. And the idea is that you're gonna use a neural net to basically compute information across the map as well as the raw sensor measurements. You're gonna fuse this information and create some feature representation from which we're gonna do detection. We're gonna use a two-stage detector such that we can actually have very precise detections and predictions. And the idea is to simply use a rotated region of interest, align on the detected bounding boxes and align also in terms of heading. So now we're going to have this way a representation for every of the objects that we actually detect, and we just encapsulate this information with this variable x, which is observed in this case, since it comes from the observations. All right, so now that we can detect the objects of interest, the question is, how can we predict their future trajectories in a way that basically we model the entire joint distribution of these actors? So a pretty good way to actually do this is to employ a latent variable model, where you can think of this as a sophisticated conditional VAE, where basically we are going to have a distributed latent variable that is going to where the encoder is basically a graph neural network, so that it takes into account the relationship between all the different actors. And the decoder as well is going to be another graph neural network that decodes, given the latent representations, into the behavior or trajectories of every one of the actors. Okay, so all the stochasticity is going to be here in terms of the latent variables, and this is actually a model that you can do inference really, really fast, and it's very simple. So the idea is that you do your forward pass to create your detections. Then you basically do inference in your graph neural network by passing messages between the different actors. Then you're gonna sample from the distribution. You're gonna get your latent variable, and then given this, you basically deterministically decode into what every single actor is gonna do. Okay, and you can sample from this multiple times, and you have the multiple realizations of the scene. And note that one sample here basically gives you the entire scene, meaning that it's consistent across actors. Okay, so I'm going to showcase this here with simply getting 2 samples from the model and interpolating in the latent space and basically decoding. And this is the representations that you have here. Okay, so you see that, as we move in the latent space, basically all the actors move. And this is just showing that indeed it captures the full joint distribution. So you can actually learn this model in a simple manner. And the idea is that we're going to use, so you can learn it end to end, the entire thing, right? You can have a loss for the detection, which is, the standard loss of classification, as well as regression for the more precise bounding boxes. And on top of this, you will have the standard KL loss for the conditional VAE, and then we will have a reconstruction loss, basically saying that we should be able to decode something that is similar to what actually happened in practice in our data set. Right. So again, you can train this end to end, and it also actually this type of model works really well. This is showing, compared to basically the state of the art in terms of prediction models. This is showing how consistent the predictions are. So this is as you predict things, whether they collide or not. And you see that it's way more consistent than anything out there. So the lower, the better. And at the same time, it also represents better what happens in practice. So it's much closer to imitating the humans. Now, if you look at the, some videos of what this model actually does, although the predictions look great, one of the things to note is that they are not super diverse, right? It only uses multimodality in a few cases where actually it's pretty, it's actually uncertain. And if you think about, the task that comes after, which is motion planning, right? So you would like to actually have a representation that is much more diverse, right? Because you would like to make sure that you can actually plan accordingly to any single thing that might happen in the scene. Okay, so let's look at how we can actually enhance this model to basically capture diversity. Now, if you think about these types of latent variable models that we've seen in the literature, or any of these probabilistic models like multipath, the problem is that they are very sample inefficient. You're gonna need so many samples to get diversity of the possible modes that this cannot run in real time on the car. So instead, and the reason why, right, is that they have these independent samples that just decode. There has been a couple of works that look at whether you can add diversity or a diversity objective so that your samples are actually diverse. But the notion of diversity, in my opinion, is not great, in the sense that they look at sampling different trajectories that are different between each other. But that's not what we care about in driving, right? What we would like to do is like sample different trajectories or realizations of the scene such that we actually, the self-driving car will behave differently, right? And if we are able to do this, then with a very, very few samples, we should be able to actually capture all the possibilities of our reactions to what might happen in the scene. So the way that one can do this, which is what we propose in this, in this paper, is to basically employ, we're going to employ a graph neural network that is going to sample at once k realizations of the entire scene. Okay, so every one of these decodings is basically an entire scene into the future. And basically we sample k of this. And this sampler is learned such that we encourage diversity in terms of the planner reaction to the scene unrolling. Okay, and this is the way that you can actually cover the, what matters in terms of the future with really a few samples. One thing that we need to do is, since we actually have changed the sampling procedure, we need to estimate a likelihood function so that we understand how likely every one of these realizations of the future are. And one can do this, sorry about that, one can do this very, very easy by just learning a probability distribution by encourage basically the likelihood to be correlated with what originally happened in our training scenes. And the last bit that we need to do now is, well, now we have a way to have diverse samples that are gonna trigger different reactions in terms of the motion plan. And we can do this again in a very efficient manner. So the last thing that we need to do is design a motion planner that is able to don't get overwhelmed by all these different things that might happen, but instead that is non-conservative but super, super safe. And in particular, we have quite an pretty interesting planner here, which is based on the idea of contingency planning. So let me quickly explain you why we need a different planner than what you see in the literature and what is the underlying idea. So if you look at typical planners, so the way that they work is that for say 8 to 10 seconds into the future, they actually plan a single trajectory at every point in time, right? So every time that you get observations, you plan a single trajectory for the next 8 seconds. And as a consequence, when you actually model all the possibilities of the future, you end up with actually like super, super conservative estimates, because on those realizations, right, there might be one of those that actually is unsafe with respect to all this trajectory, right? So you end up by being super conservative, always slowing down, just to make sure that no matter what happens, it's a worst case scenario kind of planning. So no matter what happens, you always, you will be safe. So while this is typically safe, it's not great as a user experience, right? Because typically the self-driving car will go very, very slow. However, there is a way to actually get as safe or more safe, while at the same time not being super conservative. So being something more similar to what humans do. And the idea is that to basically exploit the fact that we are working in a model predicted control, which basically means that every time you get observations, you replan. So what this means is that you don't really need to commit to the entire trajectory for the next 10 seconds, because you're going to replan as you go. Instead, there is a short-term trajectory that you want to make sure is the right one, such that it's safe, and no matter what happens, you can react. But for the rest of the trajectory, you don't need to commit to a specific realization. Instead, depending on what might happen in the future, you actually might end up with different realizations, right? Depending on how the scene might unroll, you will do one maneuver versus another. And the thing that will be common will be the short-term trajectory. And this is a very key idea that allows you to really do this in a safe manner and non-conservative, okay? So the way to do this is that you can sample a set of short-term trajectories, and for every short-term trajectory, you can sample a set of longer-term trajectories. And the key here is actually how do you decide into what is the best short-term trajectory to do. All right, so, and the way that you're gonna do this is, we're gonna do this is by basically costing these trajectories and choosing the best one, right? So the idea would be that for these short-term trajectories, we are gonna work in the worst case scenario, meaning that we wanna choose the trajectory that is safe with respect to, say, the next bit. Typically, you can think of it of maybe half a second or 1 second, very short term. But however, instead of committing to a single trajectory into the cost to go, we are going to look at for every realization of the future in terms of how the scene unrolls. We're going to look at the best trajectory that you could do, right? So depending on the realization, we will have a different trajectory. And basically, we're going to cost the cost to go by just weighting this by the likelihood function that we were just mentioning that we obtained for these multiple realizations of the scene. Okay, and the cost basically is, like always, a combination of safety, progress, and comfort. So in pictures, what does this mean is that, So imagine this is a situation, and let's say that we want to commit to a certain trajectory of this form, which is actually pretty aggressive. Then, if they yield to you, then it's fine, right? But if they don't yield to you, what you're gonna need to do is to really have a hard break, right? And this is actually not great. So this is gonna cause this short-term trajectory to not be, this is the cost to go, right? Which is bad. So this trajectory will not be selected, right? It's unsafe. Yeah.
So we are over time 5 minutes. So maybe summarize it a couple minutes. Yeah.
So let me just finish this and then show a video, then I finish. Cool. So instead, right, a trajectory that is more conservative, right, will actually be safer in the future. Okay. So this actually works really well, and let me actually show you the video.
Simulation. The SCVs at the center in green, and the other vehicles and their trajectories in blue, and finally the pedestrians in pink. Let's focus on the diverse predictions and response from the planner. The short-term action plan in the SCV is plotted in black, and the contingent trajectories are plotted in different colors, which in this case accounts for the variations in the speed profile of the left-turning car. As you can see, the SCV passes the intersection safely and cruises smoothly.
So these are close-loop simulations. So you really see the reaction of the vehicle.
To unlikely samples from oncoming traffic coming into our lane, and successfully goes across the intersection. Here, our model avoids the hard brake before making the left turn by planning safe contingent trajectories to the diverse speed profiles from oncoming traffic, and smoothly effectuates an unprotected left turn in this fast-moving scenario. Here, the car in front of the SCV might turn or go straight, and thus it might potentially brake before turning. The SCV plans both cruising and braking trajectories to safely account for that, and it comfortably drives through the intersection.
Cool. So just to summarize, right, I show you, how to have multiple realizations of the future that come from the unit distribution, how to have samples that are very efficient, and that they are actually trigger diverse reactions of the motion planner, and a contingency plan where basically you can be less conservative than traditional planners, but be as safe as with those planners. So thank you for your attention.
Great. Thanks everyone for your awesome talks. Yeah, currently we are in the Q&A sections. If you are in Zoom, you can feel free to directly ask questions to those speakers. If no one asks, I would pick the questions in the chat box. Yeah, feel free to check with speakers. Okay, I got a lot of questions on the chat box, so I may first ask Peter. Li Dong asked, is the learning process only take the final result of the perception system, or it actually an end-to-end learning process from image video to planning action?
So we are using mid-representations rather than end-to-end learning. And the reason for that is that when you're using mid-representations, you can actually synthesize the scenarios that never happen, for which you actually don't have any underlying sensor data. And that allows you to build different kind of algorithms, for example, like closed loop testing that allows you to synthesize scenarios that never happened.
Yeah, thanks. Another question for Dasa. Q Chuan asked, hi, what is your action space? It's the same with all scenarios.
Yeah, so I presented, okay, hi everyone first. And then, yeah, I presented two works. So in both of the works, the action space is a steering angle and acceleration, and the steering angle, acceleration, and braking of the autonomous vehicle for both of the works. In the first work, we are doing this imitation learning idea where the input is going to be visual data, and the actions still like the same set of actions that I said. In the second work, I'm mostly talking about it from a very model-based idea and perspective, still the same action space, but we're defining the reward function, and we are doing prospect theory over that reward.
Yeah, thanks. Another question is for Keeling. Also, actually, Keeling has answered a lot of questions on YouTube. I pick one from the Zoom. MH asked Keeling, how robust are persistency prior in traversal with noise localization?
I see. Yeah, so that's very easy. So essentially, you have these past traversals, and using GPS to find the same location of the past traversals. So obviously, there's a problem. What if GPS is not really accurate? But turns out actually that's very, very easy to fix, because if your GPS is inaccurate, then all the points are off by a little bit. So you can just use ICP to correct for it. So it's a very simple algorithm that you can do offline, and then basically, they're all aligned. So it's not an issue.
Yeah, so thanks. People also ask Raquel, may I ask, in which data set do you train and test your method?
Yeah, great question. So this was trained on what we call ATG4D, which is around 5,000 snippets of 20 seconds of driving. And in terms of testing, I was showing a closed loop simulator where basically with sensor simulation, where basically we have in particular 200 scenarios that are super, super challenging, where the vehicle has to basically behave and navigate around, which is one of the things that is very, very important, is that we see a lot of metrics in perception or prediction. We need to go further the pipeline and have system level metrics, which is really what is done in industry. So even if you develop an algorithm in perception, you should look at how well or how that influences your motion planning metrics. And in terms of system level metrics, it's super important that you actually do something that is reactive, that is closed loop. If you end up with just simulation of the just replaying what happened in the past, that's not reactive, so that doesn't give you a lot of signal. So yeah, so as a community, we should be moving towards more simulation, closed loop simulation.
Yeah, thanks. Another question is for Peter. Fatima asked, how do you measure the quality of your data?
So the quality can be approximated by the performance of the perception system that is using the data. So for example, when you can be measuring like the performance of the detection, like false positive, false negative, but also the positional accuracy. So for example, with LiDARs, you have better positional accuracy. With cameras, you have slightly worse. So this is something that you can use to approximate the quality.
Okay, thanks, Peter. Another question from YouTube for Dasar. Alan asked, how frequently does real L translation between models with one scenario? For example, for the merge scenario.
Yeah, that's a very good question. So the exact results of this is actually in the RSS paper, but it's actually not that frequent. The idea of transitions are capturing the space transitions that we see in near accident driving scenarios. So in general, it's actually not that frequent because the autonomous car shouldn't be doing too many of these space transitions. So I would say it's in the order of, like, for example, for the merge scenario, it's in the order of like 5-6 transitions. So it's a very small space of mode transitions when it comes to these near accident driving scenarios. But the exact details for the 5 different scenarios I've discussed are in the RSS paper. So
yeah, thanks. I also got a question for Keeling. Any thought on how PP can be extended very large maps, as storage will be becoming a limitation factor?
Yeah, good point. So if you have, basically you have to store these past traversals. If you have a very, very large map, how do you store all this? And the answer is simple. You only actually need local information at any given time. So if I drive somewhere, right, I may have a plan. So, I could just download whatever, point cloud I need around the current, where I am right now and where I'm planning to go. So even if I'm a very, very large city, I'm only ever traversing, one street at a time. And that's, probably, would work really well.
Thanks. I have a small question for Raquel. So there are a lot of good models from Uber ADG and also from your lab. So would you release some of the models? Yeah, so it will help a lot. So a relevant question is from Danish. They ask, is kind of large end-to-end network deployed directly in the car for inference? Also, what are some of the challenges for having large network for inference when deployed in real-world self-driving cars?
Yeah, so let me, I guess, answer the two questions. And I was laughing about the first one, which is an interesting question. So as I guess people know, I love to share things with the community. And, we were in the process of actually releasing many different benchmarks as well as models. This process has been halted due to an acquisition of a company along the process. So I'm fighting the battle to be able to share with the community all the stuff that we wanted to share in the first place, okay? So bear with us, all the things that we promise, we are trying, okay? But it doesn't just depend on us right now. In terms of the deployment into the real system, so I obviously, unfortunately, cannot say what goes into the production system of a different company. Instead, what I can tell you is that the good thing about this type of models, end-to-end trained models, is that you can choose what you deploy. You can take just the perception system. You can take the perception or prediction system, etc. And the fact that we train them for the end task results in much better performance in terms of those intermediate tasks as well, because you're actually training them for what matters, instead of just saying detect the objects everywhere, regardless of whether they are important versus not. So you have the choice of which piece you take of the puzzle here.
Yeah, thanks. There is another question asked Raquel and Peter. When using learning-based method for planning and control, how do you guard against rare but catastrophic mistakes?
Peter, you want to go first?
So that's a really good question. Raquel, do you want to go first?
All right, we'll go first. So the way that we actually do this is through our closed loop real-time super high fidelity simulator, where we can do things like create adversarial examples that are tuned for particular software stacks, regardless of whether they are differentiable versus not. There's a paper at the CVPR that we have, explaining all the details of how you can do this. And then you can train with these adversarial examples and you get much more robust systems. So I definitely recommend for you to look at this. And what is interesting is that you can create this adversarial, and examples here means actually entire simulations, right? In terms of the actors, their behaviors, their appearance, etc. Right? And what is interesting is that you can create these adversarial scenarios employing any software stack, and those are actually useful for the other types of software stacks as well. So there's quite a bit of nice transfer there, and this is the way that you can train to be much more robust to things. And if you think about it, right, as your system gets better and better, the test that you typically do, whether it's on the test track, on simulation, or the real world, you're gonna pass all those tests, right? So you need automatic tools to understand and poke your system into where it might fail. And this is where this type of approaches like adversarial sim, which is what we call, are super useful.
Yeah. So the way we look at this is that you will always probably run into some situations during the test that you never seen during the training. So, and I would say, like, no matter how much you trained, because you never seen anything like that, like the behavior of at that point might be unpredictable. So what we actually do, we have secondary system that runs on top of the machine learning system, and that is checking for kind of collision course with other vehicles as well. And it's giving us that guarantees that even in these cases, the things don't go terribly wrong. So we have actually the secondary system that is on top of the machine.
Yeah, thanks. So because of the time limitation, I would ask the Dosa and Kilin the last questions. And there are more questions. So please, the speaker, if you have time, can directly answer them on the chat box. For Dosa, Sergey want to ask, how do you make sure the reinforcement learning policies is stable for sub-policy switching? Meaning, could it be possible that the policy turns into a very uncomfortable regime?
Yeah, that's a very good question. And that's something that we did worry about. Again, like going back to that first question of how many mode transitions are you actually seeing? And is this like unstably changing between the modes? So I think you can put as part of the reward function of reinforcement learning, you can actually put a reward that penalizes these types of like quick changes or these types of like frequent changes. We actually didn't do that. And maybe we got lucky and we didn't see too much like instability. And partly it is because it is actually like with the current reward function, you can actually achieve the task with very minimal number of switches. But I'd imagine that you can as part of the reward function, you can penalize these high switches just to make sure that it doesn't become unstable. But that's very interesting. Yeah, empirically we haven't observed that.
Yeah, thanks for your answers. A question for Kilin. Does slightly moving objects create issues? For example, due to wind, the tree leaves move, car is parked slightly at a different place every day, and some other examples.
So that actually does not create issues. And if you think about a branch with leaves, right, and they move around, so you good point, right? So they are not technically not persistent, but actually the way we do it is we just, we take a 50-centimeter ball and say, well, any points within this ball count, right? So basically saying, now I'm seeing some leaves here. In the past, have I seen some leaves within a 50-centimeter ball? So there would have to be really hard fluctuations for them to be all outside the ball in a given time. So it's quite robust against these kind of small changes.
Yeah, nice. Yeah. So thanks for the attendees. Thanks for your questions. I think we have not answered every question. So if you have time, you can directly answer them on the Zoom chat box and the YouTube chat box. Currently, we have roughly 130 people join the meeting. Yeah, our next session will be the poster section. So you can feel free to join the Gather Town to watch the spotlight video and the PDF paper and discuss the paper with others. Yeah, thanks.
Thank you, Jan.
Yeah, thanks, Kilin.
Thank you.
Thank you.
Yeah, thank
Everybody.
you.
Hey, Mohammed. Maybe can you go through your paper, please? Yes, I can see it. Hello. Yes. I'm sorry. I think my microphone is not working. So for your loss, do you apply the loss for 2 consecutive frames, or do you apply the loss for also skip frames?
Hi, are you asking questions for Raquel?
Hello. Hello. Hello.
All right. Hello, everybody. My name is Sergei Zagoruka. I'm a research scientist at Level 5, and I will be moderating the second session of the workshop. And let me open the first talk. The first talk will be from Chen Wu, who is an engineering director of perception at Waymo. Chen leads a team responsible for how vehicles use Waymo's custom sensors, including cameras, LiDAR, and radar, to see the world around it and recognize objects such as other cars, pedestrians, and cyclists. Prior to Waymo, Chen worked at Google on the algorithms that optimize photo speed and quality for Google Glass. Before that, Chen was at YouTube, where she used machine learning to enable 2D videos to be viewed in 3D. Chen holds a PhD and MSc in electrical engineering from Stanford University, and bachelor in control theory from Tsinghua University in China.
Good morning, everyone. My name is Chen. I'm an engineering director in perception at Waymo. Today, I will talk about how to scale perception development as well as the whole AV stack with efficient learning and simulation techniques. Scaling the AV system faces multiple dimensional challenges. One of the challenges is that we have different vehicle platforms. At Waymo, we have 2 vehicle platforms for Waymo 1. One is Pacifica, the other is Jaguar I-Pace. And we also have Waymo Via, which is a tracking platform. The sensor suites and placements vary across the different vehicle platforms. The second challenge is that the Waymo driver operates in diverse operating domains, from suburban to dense urban to freeway and to different weather conditions. Also, the sensors keep evolving. Last year, we introduced our 5th generation sensor suite. This includes even more powerful LiDARs that sees up to 300 meters. The camera system covers 360-degree long-range occlusion regions, as well as an imaging radar system that offers unparalleled resolution, range, and field of view. On top of all these, the Waymo driver needs to meet very high safety standards because we operate a real public transportation service with drivers. In October last year, Waymo opened up the world's first full driverless service to the general public in Phoenix, and also we also published our 5th safety framework that described how we qualify our software for fully autonomous operations. So to recap, at Waymo, we need to build technology and systems that can quickly scale to all of the sensor suites, vehicle platforms, and operational environments, while also meeting high quality standards for safety. To achieve such a mission, it requires both solving very challenging research problems and also build very robust and scalable engineering systems. And how do we do that? In this talk, I will talk about a few techniques that can be used for perception to help it to scale. I will also introduce the Simulation City project at Waymo that enables the entire stack to learn faster in a realistic and large-scale simulation environment. First, let's look at some of the perception techniques. Well, the first type of technique is domain adaptation, where the tasks are the same, but the domain shifts due to sensor differences and also due to environment differences. So here's one example with the sensor changes. This screenshot shows was captured by our previous generation LiDAR. And in this slide, this is a short video showing a scene that's captured by our new LiDAR. And there's a significant boost in terms of range, field of view, and density. And also you can see this point cloud carries more information. And why do we need domain adaptation? In a normal development cycle, it requires a large quantity of data and also large diversity of data in order to achieve high quality perception. Moreover, as the quality gets closer to the a fully autonomous driving quality level, we need even more diverse and long-tail examples to materially improve the system performance. And such examples can often take quite a long time to collect and also costly to label. With domain adaptation, it allows us to speed up development to the new domains while leveraging existing data collected in another domain. There are two phases where domain adaptation can be particularly helpful. The first phase is in the initial bring-up phase, where a big portion of the knowledge can be quickly transferred from one domain to another. And the other phase is in the long-tail development, where both the knowledge of the long tails and the data of the long tails, if transferred effectively, can quickly bring up the long tail capability of the new domain, therefore reducing development time. And how do we do it? A straightforward strategy is to really understand the differences between the domains so that we can really know what knowledge we can transfer and what knowledge we have to learn. A very simple example here is to structure the model so that it can learn feature encoder on the similar sensor features and feature encoder on the dissimilar sensor features separately, in the hope that the feature encoder for the similar sensor features can be reused for the new domain. And sensor simulation is a very critical technical component to enable realistic end-to-end simulation and also to enhance perceptions training, especially on long-tail examples. We have LiDAR simulation, which need to closely represent the LiDAR characteristics. It is not just about geometry. LiDAR simulation is very important to learn the characteristics from different returns from different objects and different material, and being able to recreate that realism. Here's a rendering of our camera simulation. On the left side is the real camera image. On the right side is the simulated camera output. If you look closer, you can see that the shadows of the building and the light poles match very closely to the real camera images. We have accurate models and texture for the buildings based on the 3D data collected by Geo. We also have accurate placement of all the scene props like fire hydrants, light poles, different static objects from the 3D map that we collected. We simulate the sensors under weather conditions. There are different types of weather conditions, and for each of them, there are different degrees of it. For example, for rain, there's a light rain, medium rain, heavy rain. For fog, there's a different visibility level. It is impossible to collect like the whole diverse set of data under every weather condition. Therefore, it is very important to be able to simulate them. On the left side, you can see this is a camera image simulated with raindrops and wiper. As the wiper sweeps through, you can see the raindrops goes away. On the right side is a point cloud with a simulated fog effect. Here's a paper that Waymo published last year in CVPR. It is called SurfOGAN. In this work, the goal is to generate realistic camera images for autonomous driving simulation, given any novel trajectories. And what is a surfel? A surfel is short for surface elements. It's a 3D map representation for imagery data. This is a rendering of Waymo's 3D surfel map. In this rendering, you can see different levels of the map. There's a 3D represented elements, and for each surfel element, there's a texture attached to it. In the SurfOGAN model, it takes 3 different inputs. The first input is a rendered surfel map at the camera pose of the novel trajectory. The second and third inputs are semantic and instant segmentation masks. Then the SurfOGAN generates a realistic looking camera images. On the right side, you can see two examples. The first column shows the surface image rendered from the surface map. It has gaps and are not entirely realistic looking. In the middle column is the surface GAN output. The third column is the original view. Note that the surface GAN output and the original view are different because the surface GAN is supposed to generate a novel image from a novel view. Data augmentation is one type of approach that could be particularly effective at increasing data diversity. In this work, we synthesize diverse pedestrian poses with realistic point cloud. So there are 3 steps to it. In the first step, we generate a 3D model. It can be either from a 3D pose estimation from an example point cloud, or it can be from a user-specified pose. In the second step, mesh diversification, it adds augmentation along different dimensions. It could be pose or LiDAR position, it could be shape. And these augmented 3D mesh then go through a realism enhancement, which is the third step. It's a conditional GAN that imposes a realistic noise that's learned from the point cloud and make the 3D point cloud more realistic, matching what we see from the real LiDAR point cloud. When applying this method into the Waymo open data set, each of the augmentation improves performance, improves the F1 max score, as you can see here. And when added together, this method does improve the performance by a dramatic margin on top of the baseline methods. So here's another work where we try to leverage unlabeled data for data augmentation to improve 3D detection. This work applies pseudo augmentation policies on the unlabeled data and also applies progressive population-based augmentation to automate the hyperparameter search of the policies. There are 2 types of augmentation we're trying to add here. In the first one, pseudo bounding box, it pastes the pseudo label boxes objects into the input frame. And the second one, pseudo background, it pastes label objects in the input frame onto the pseudo label background. So basically 2 approaches. One is to trying to diverse the objects. The other one is trying to diverse the background. And then PPBA is used to automate hyperparameter search. This method outperforms SOTA data augmentation PPBA and maybe up to 9.5x and 5.8x more data efficient compared to the baseline vehicle detection and pedestrian detection. So auto-labeling is another way to leverage unlabeled data. You'll hear more details about this 3D auto-labeling pipeline that we developed at Waymo from Charles T. So I will be brief here. In a nutshell, the idea here is to emulate human labelers to label 3D objects with 3D boxes. It uses a whole sequence of data and generates highly accurate 3D boxes and tracks. Then we can use these highly accurate boxes and tracks to either auto-label the sequences or do data augmentation. And this method has been approved to be more robust with domain shifts as well. So some of the perception tasks can effectively benefit from weak or self-supervision, therefore reducing demand on labels and shorten the development cycle. Here's one work where we want to estimate 3D human pose. You could try to get ground truths by 3D labels on the point cloud to get 3D key points, but that will be very expensive. Another way, a cheaper way, is to get 2D key point labels from the camera images. And that works. The way you can do is to elevate the 2D image based key point labels into 3D to get pseudo 3D key point labels. And then we can train the model against those pseudo 3D key point labels. There are 2 laws that we apply here. One loss is on top of the 3D key point prediction. The other loss is on top of a per point predictions. And this method is able to achieve satisfying results. Here are a few examples from the 3D human pose estimation. As you can see, the predicted pose matches the ground truth pose pretty accurately. And also this method is robust to different lighting conditions because it uses both laser point cloud as well as the camera image. On the left side, even though the scene is at night, it's dark, the pedestrian is also wearing dark clothes. The 3D prediction is pretty accurate, representing the pose of the crossing pedestrian very well. Another example is optical flow. You can get very decent results from unsupervised approaches already. Here's a paper that's a joint work between Waymo and the Google Brain. It's called SMURF. It's an unsupervised learning of optical flow that improves SOTA on unsupervised approaches by 36% to 40% on all the benchmarks. In this method, there were two ideas here. One key idea is using sequence loss with augmentations. So instead of just using the loss at the final iteration, it adds up the loss from each iteration to be the final loss, and also applies data augmentation to train the student model. The second key idea is the multi-frame training, where 3 frames are used, and we leverage backward and forward flow consistencies. This has proved to be effective at disambiguating at occluded regions. But we can add supervision to optical flow to make it better. Here lists 2 different supervision sources. One source is we could use synthetic examples, where I show some camera simulation, and we can get very dense optical flow ground truths from camera simulation. The good thing about this ground truth is that it's dense and accurate. However, it lacks realism and diversity. The second approach for supervision is to get proxy ground truths. You could get it sparse ground truths from laser point cloud, odometry, and object level labels. They are realistic because they are from real driving. However, they also suffer from alignment, calibration errors. There could be laser artifacts, and we have to live with rigid box motion. Well, but any supervision helps. Here is a comparison of the output between the unsupervised model and the semi-supervised model. And you could see advantages of the semi-supervised model. For example, with some supervision, we could effectively remove motion on the shadows. And the semi-supervised model also yields a sharper object boundaries. Now let's zoom out of perception and look at the entire AV stack. I'd like to introduce Waymo Simulation City effort. The mission of the Simulation City solution is to train the autonomous driving vehicle in a highly realistic simulated environment at a very large scale so that it can learn much faster than from real-world driving. And this is a new simulation solution with some key differentiations. The first key differentiation is that this is real-world based. This simulation solution learns from the 20 million miles that Waymo has driven, and also from external data sets. With such a large data set, both from real-world driving and external studies, we are able to build accurate behavior models for our simulation. The second key differentiation is high realism. I already talked about 3D surface map and sensor simulation and auto labeling. All such techniques are applied in this simulation solution to achieve higher realism. And third one, we programmatically generate full trips in all kinds of driving environments and also generate traffic. The last but not least, this simulation solution is integrated with Waymo's safety framework and is a key component to help us validate and evaluate our system. Our goal is to programmatically generate simulation at scale with different behavior samples from the prior data models. For example, in this example, we have an autonomous vehicle followed by a blue tailgater vehicle. We can draw the samples of driving behavior from a human response model for this blue car and estimate the tailgating rate, which is a critical safety metric. And as you can see from the right side, we can build a response time distribution from the real driving and being able to statistically represent what could happen in simulation to represent the real world situations. And another key capability of this simulation solution is to generate dynamic traffic into the scene. And here's an example of a Golden Gate Bridge. And of course, in real life, we almost never need to generate traffic for Golden Gate Bridge, but you get the idea. So our solution aims to create traffic at different location, time, density, and behavior distributions. Here's a simple example to illustrate the idea. In this example, we simulate a passenger drop-off with a cyclist passing by. The autonomous vehicle is able to safely yield to the cyclist before pulling over. In the end, I would like to conclude my talk with this video. It's an 8-hour simulation of freeway driving. Don't worry, I won't play it for 8 hours. And in this simulation, we have covered a wide range of driving behaviors, road environments, and also surrounding traffic. And this is a powerful tool to help us train and test our system. And this makes the Waymo driver learn much faster compared to only using real driving data. And this concludes my talk. And thank you very much for watching.
Right. So the second talk will be from Anka Dragan. And Anka is an assistant professor at UC Berkeley, where she runs the Interact Lab. Her goal is to enable robots to work with, around, and in support of people. She's also a staff research scientist at Waymo, where she advises the behavior team, who is responsible for prediction and planning. Anka did her PhD in the Robotics Institute at CMU on eligible motion planning. At Berkeley, she helped to found the Berkeley AI Research Lab.
Hi, everyone. I'm Anka Dragan from UC Berkeley. I wanted to share a little bit about human behavior prediction today and how to make it both expressive, but also maintain robustness, safety. And so I'm talking about these problems where you have a robot that needs to do something. For instance, this quad rotor needs to travel from the current state to the goal GR. And there's also a human also doing something. And you want to make sure that the robot does not collide with the human. And this could be for an autonomous car navigating around a pedestrian or even around a human-driven vehicle. What I'll talk about today will apply to these settings, but I'll stick to this quad rotor example, running example, because that's what we did hardware experiments on. So how can the robot figure out what to do here? And clearly to figure out what to do, it needs to anticipate what something about this human, what the human will do, because once it has the states that the human is likely to be in, it can sort of set up its own optimization problem that says, I need to find XRs and URs, states and controls that minimize costs, that satisfy dynamics, and that importantly, the states don't end up intersecting with the human, with the states that the human will occupy. And so out of all these different options, the robot has to figure out what's feasible and lowest cost. And that later part is something we can do these days, but crucially, it relies on the first part, the prediction that the robot has made about where the human will be. So how do we make this prediction? That's the focus of my talk today. And the first answer is that, well, where the human will be, the states the person will end up in, that's really a consequence of the actions, UH, that the person will take. So the question is, what actions will the person take? What decisions will the person make about how to act? And answering that is really hard, right? Because who knows what's going on in people's heads. And so on the control theory side, what people do is they cleverly decide to not answer it. They say, look, there's a set of possible actions that the person can physically take. And so we kind of have to protect against all of them. And so any of them is just as likely. And if we use them to construct sort of the set of states that the human could potentially reach in 1 step, 2 steps, and so on, this is formally called a forward reachable set. Now there's a breadth of tools and techniques from control theory that someone can use to actually compute these sets for arbitrary nonlinear models. So the idea is, rather than avoiding some specific area where we think the human will be, avoid anywhere the human might end up in. And that's a wonderful thing to do because it has this wonderful property that 100% we will not collide with this human. But unfortunately, it also makes the robot utterly and completely useless. So here we have a robot with a goal behind my student Ellis. Ellis is just walking, minding his own business. And the robot is guarding against the forward reachable set for Ellis. So it's defending itself against this version of Ellis that might just turn around at any second and start running towards the robot to try to collide with it. And as a result, it has no choice but going to the kind of the corner of the room and not able to reach its goal. And similarly for cars, right? If we did this for cars, cars would never leave the garage because if you have an oncoming car, then there's always a forward reachable set of that car so that it can intersect your lane, and then bam, you have to teleport yourself out of the situation to satisfy the safety constraint. So that's not good. So instead, another solution that is super popular, especially in the computer vision community, is to collect a ton of data of human behavior and train a human policy to imitate that data, right? To imitate that behavior. So this is kind of the supervised learning approach. And what's nice about this is that it's no longer, well, everything goes. Now, this model will assign higher probabilities to actions that make more sense. If you go towards the door, that makes a lot more sense to step in the direction of the door. So the model will probably do that. Only problem is that doesn't always happen. So we see examples like this. This is from Sergey Levin's group, where we try to imitate human driving, and we do it from dashcam data. And there's this really interesting correlation in the data where basically every time a person decides to brake, there's a light brake that turns on the dashboard. And if you want to predict braking, you don't have to figure out that the person is braking because there's a pedestrian in front and they need to slow down. All you have to figure out is that there's a light that turns on the dashboard. And so what the model learns is basically to pick up on this correlate and to predict braking whenever the brake light indicator is on. Unfortunately not when the brake light indicator is not on. And so you won't stop for pedestrians this way, and that's a problem. I'll give you one more example we encountered in the lab recently. So here we set up this collaboration task, and it's inspired by the game Overcooked. Now, this is very different from driving, but you'll see the same issue. So we set up this game. You have to collaborate with another agent to make soup, okay? So you take onions and you put them in the pot and you leave them there until they turn into soup. And then you take plates and take out the soup and then deliver it to these gray areas up the top. And so what we did is we collected human data, so data of humans playing. We trained a policy, and here it is at work. And it's glorious. It works fantastically well. The agents are getting these onions, putting them, delivering soup. Everything's working out. And not only are they making soup, but they're also working together. So you'll see the situations where one is preparing with the plate to take off the soup, or the other one is waiting with an onion to put it in the pot, right when the plate it gets filled. And it's perfect. They learn how to make soup and work together. And so you look at this and you say, supervised learning is amazing, right? It's just they figured out how to do stuff. But then we put them in this situation here where we put a plate on the counter. It's very reasonable for a plate to be on the counter, but it's not really something that happens a lot in the training data. And so what happens is all hell breaks loose. Now they're going through the motions, and so it appears that they're working, but if you look at what's going on, none of it makes any sense. They're walking around with full plates, not delivering them. This one just put a plate up the top instead of delivering it. It's like they forgot what soup is. And so this happens just from, inducing this distribution shift of, okay, now there's a plate on the counter. It's right, it's an outlier in the data. And we've seen this in driving too. So we've seen this for highly interactive situations. So here, kind of ignoring the orange line at the top, what we see is that just getting more data of human behavior on the x-axis, depending on how you collect that data, doesn't help. So the robot's reward stays bleh. And only when you add a particular kind of very fancy, idealized kind of exploration that we have no idea how to produce algorithmically, that's when you start seeing improvement. So what's going on here kind of boils down to this very simple reality that if this on the top right is the space of all possible policies, what a real human would ever do is some very small part of that. And the unfortunate part is that when you get data, even if you get a lot of data, there are going to be many policies that you can represent with your model, with your hypothesis class, with your function class, that are consistent with the data that you've seen, right? Some of them will be kind of the thing that you want right here in the space of human policies, and others not so much. And who knows which one SGT will converge to, right? It doesn't depend just on the initialization, but honestly on what features are easier to build. For instance, it's much easier to look to detect a brake light than it is to detect the actual reason for braking. And so you'll converge to that. And so kind of the question here is there a way to converge to the causal explanation, the causal model? Or in another way of phrasing this is there some structure, some inductive bias that we can assume that we know and inject into this domain so that we end up converging to a model that's actually robust? And I don't have the answer for this, but I'll tell you one piece that seems to be an important part of the story, which is that the reason people are not sort of in this area of the space, the reason they're not just kind of arbitrarily doing stuff, and they're here in the small part, is because their actions aren't arbitrary. We decide on actions to take because we're trying to do something. The person has some goal, GH, for instance, in the room that they're trying to go to. A driver is trying to make progress and avoid collisions and stay on the road and so on. These are intentions that people have that drive their actions. And so the thought here is that if human actions are driven by human intent, and we know this, it seems like a pretty useful inductive bias to try to use somehow as we're learning these models. The question is how, though. And so concretely, take people walking in a room, their actions are driven by them wanting to get somewhere. There's, in this case, 3 possible intentions they might have, right? 3 possible destinations in the room. How do we structure the policy that we're learning to take this notion of people have intentions into account? And well, what we can assume is that each intention corresponds to some Q value function, that there's a way for that's more or less optimal ways to achieve that intention, and that human actions are going to be distributed in proportion to that Q value function. So condition on the door, going straight towards the door, is a lot more probable than, say, going away from it. And now that structure that we put on this policy, and it's not that we have no use for data. Data is still very useful, but not to learn the actions directly. Instead, you use the data to figure out what the space of intentions is, this capital theta, as well as a reward function that is data dependent, that leads to the Q values that explain human actions for that intent that you actually observe people take under different intentions. And so that's what you learn from data. And then at inference time, you don't know the intent data. So you might start with a prior. The moment the person takes a step, takes an action, that right there is evidence about the data, their intention. And so you can use a simple Bayesian update to update a prior into a posterior, again, by using this policy of what actions you expect condition on data based on this thing that you learn from data, what the datas are, but also what the reward function is. And then a distribution over theta that you have as part of your estimate leads to a distribution over actions, and then therefore over states that the person will be at every given point in time. So that's your prediction. And this ends up working well, even with off-policy data. Like we're seeing that you need less data and you don't need it to be, under magical exploration condition. It doesn't even necessarily need to be on policy. So here's an example of this prediction and planning pipeline in action for the same setup as in our running example, but now in hardware. And you see that the robot's making these predictions and then able to make sure that it doesn't collide with the person as it's planning. And this is all great, right? We found a way to inject intentions in there. And so with this structure, right now, the robot can sort of in different situations figure out what the person would do. Great, but not so fast. We haven't really solved everything. So imagine that I spilled coffee now in the middle of the room. And the person is not going to walk straight towards her goal anymore. It's going to avoid this coffee. And imagine that I haven't seen coffee spills at training time. This would be an out of distribution event for a black box predictor. But it's also problematic for the intent-driven predictor because if we haven't dealt with coffee spills at training time, the reward function that we would have learned in the space of intents we would have inferred from the data, they do not capture that people might want to avoid coffee spills, right? It's just not in your model and your hypothesis space of intents. And so at inference time, what happens is tragic. The human moves to avoid the coffee, but the robot keeps thinking, well, they're going to turn and go straight towards the goal because that's the optimal thing to do. And then that leads to a collision. And we don't want that. We don't want that with quad orders. We don't want that in driving. And at this point, oh gosh, would it have been nice to have used this full forward reachable set instead? Because if we're defending against the full forward reachable set, we would have protected against, avoiding the coffee as well. But we saw we can't do that all the time because that's too conservative. So what we'd want intuitively is for the robot to somehow use the learned model when it's correct and then fall back on being conservative when the model is incorrect. Like we would want it to sort of kind of keep going along, use the intent-driven learned model, and then go bam, something doesn't make sense, I'll use the forward reachable set and then avoid this. There are hacks and heuristics you could write to try to achieve that. But what we found is that there's this elegant unified model of human behavior that we could use that just seamlessly interpolates between the intent-driven prediction and the conservative forward reachable set. So to figure this out, we went back to the intent-driven model itself, and what it says, right? Probability of actions is proportional to the exponent of the Q value. It says people take noisy optimal actions in pursuit of their intent. Key here is noisy. Where does this noise come from? Where is it encoded? And it's encoded in this parameter beta in this distribution. So it's built into the model. And if you assume a high beta, what you're really assuming is this very peaked distribution that says that only the optimal actions really have some probability. And so you'll predict the person will pretty much go straight towards the goal. If, on the other hand, you use a very low beta, then you're kind of going towards a uniform distribution where you're saying the person's random, anything can happen, they can do anything. And that is essentially the forward reachable set construction. And so the idea was that as we change beta, we end up with a different model of the human from everything goes, right? The FRS model, to something intermediate to the perfectly rational human that heads straight towards their goal. And our idea was simple. Instead of treating beta as fixed, thereby assuming a particular rationality level, optimality level for the human. Let's estimate it from data. And if we're estimating it from data and the person does not appear to be rational under any kind of intent that we have, then that means that our set of intents or our human model is wrong. It probably doesn't mean that the person is crazy, bonkers, irrational. It probably means that we, the robot, is missing something. And so we start with some prior over beta and don't keep it fixed. Let's say we observe the person go away from the door. Well, then that robot uses that to update its belief over beta. So it's asking, okay, the step that the person just took, does it have highest probability for low beta, medium beta, or high beta? And the answer is for low beta. And then if you see this is for the door, if you see this for all intents that you have, that you end up with low betas, then that means that the human data is suboptimal for all modeled intents. And that probably means that we don't know the right notion of intent. And so now the last step is, what does the robot do once it detects that? Oh, I don't have the right notion of intent. I don't have the right human model. What does it do? Well, the thing is, we don't have to intervene in any way. The robot automatically does the right thing here, because if it infers the low beta, that automatically leads to it acting more conservatively. So it starts making predictions with that low beta, which models the human as going everywhere, which ends up being basically like a forward reachable set or something closer to it. And then the robot naturally wants to stay away from that and give more space. So it becomes automatically more conservative. Here is a quick video that shows this at work. The person is now going to avoid the coffee. The robot becomes more uncertain and bam, shifts away and gives more space. Or here we see the person goes towards one modeled goal. Everything's fine. Well, the robot has some amount of confidence in what's going on, so it can kind of keep going. Then the person goes towards the second goal. And now the person's going to go towards a third unmodeled goal. And bam, the robot's going to realize that it can't explain that. Its uncertainty will grow and it will stay behind and wait and then go around the person. We did this for multiple people as well. What's hard with multiple people is that you don't know how they'll interact with each other. But with this, you can kind of assume them to be independent. And when they start interacting, your uncertainty will just grow because that won't match the rational thing to do under the model you have. And then the robot kind of stays back and then sort of comes in when this is triggered, by the way. Okay, so human actions are driven by human intent. And I think that that is very useful structure that our models should take into account in order to be more closer to the causal explanations of what's going on. And that's then the problem is that if you just have an intent-driven model and that's what you're using, you might still not have the right notions of intent or the right model. And so we can pair that with this monitoring, with this introspection that robots can do to figure out whether their assumptions are making sense. And I wanted to just mention that this falls into this broader research agenda on accounting for people as being intent-driven. So what I've talked about today is marrying that with remaining safe. Then what also happens is if humans are intent-driven and robots are intent-driven, now you have two agents that are intent-driven, and that gives you a general sum game. So to really account for the interaction that they have, you have to go to game theoretic tools, and we've been working on that. And then finally, just because people are intent-driven doesn't mean that they're optimal in achieving that intent, doesn't mean that they're perfectly rational. So what we've been exploring is more sophisticated models that don't just assume noisy rationality, but sort of say, okay, what if people are kind of rational, but under different beliefs and assumptions about the world? And that has led us to sort of explain human actions in a much more accurate way and make better sense of them. So with that, I'd like to thank you for listening. Let me stop sharing my screen. And I hope that we'll do the next CVPR in person together. For now, bye, and bye from Treebeard. Take care.
All right. Just a reminder that you can ask questions both on YouTube and on Zoom. And after the 2 more talks, there will be a live Q&A where we will ask the questions to the presenters. So the next talk is on off-board perception for autonomous driving by Charles Tse. And Charles Tse is a research scientist at Waymo. Previously, he was a postdoctoral researcher at Facebook Research. And he received his PhD from Stanford University. Prior to Stanford, he received his bachelor from Tsinghua University. His research focuses on deep learning, computer vision, and 3D. He has developed novel deep learning architectures for 3D data, which have been well adopted by both academic and industrial groups across the world.
Hi, this is Charles from Waymo. In this talk, I will introduce off-board perception for autonomous driving. "3D applications such as autonomous driving require lots of 3D labels for both model development and evaluation. However, labeling 3D data is costly in both time and money. For example, annotating a 20-second sequence can easily take a human several days. To scale up the system, we need more automation. Can we push the limit of machine learning models to generate near-human quality auto labels? Is it possible that we develop some offline or off-board version of perception that is more powerful? More broadly, when we think about perception for autonomous driving, most of the attention has been on the onboard use case, where the perception is running on some onboard hardware giving real-time results. However, the perception can also be used in many off-board use cases, such as data mining, perception training, BP model training, behavior prediction model training, planner evaluation, or even simulation. Interestingly, those use cases may have very different requirements for the perception than the onboard use scenario. It makes more sense to have another stack of off-board perception to serve those purposes. It may share many modules with the onboard one, but could be more flexible in terms of input data format, compute latency constraints, as well as problem formulations. Our recent work published in the CVPR is one of the first steps towards building off-board perception, with a focus on 3D object detection. This paper, called Off-Board 3D Object Detection from Point Cloud Sequences, is co-authored by me and our collaborators Yin, Mahaya, Pei, Koa, Boyang, and Drago. We also have a poster session on Tuesday. You are welcome to join if you are interested in discussing more about it after listening to this talk. While most existing 3D detectors only use point clouds from a single frame or a few history frames as their input, we notice there is much more information in the sequence data. Different frames capture complementary views of the objects. If we can aggregate the object points across time, as the figure shows, we can get much denser point clouds and more complete geometry. From 1 frame to 5 frames to 10 frames, to all frames where this minivan is appearing in the sequence, we can get much more complete views. A naive baseline to leverage those temporal contexts would be using multiple frames as input to existing detectors, to make them multi-frame detectors. Given the non-sensor poses, we can transform the point clouds from a few history frames to the current frame coordinate. However, doing so will give us quickly diminishing returns as we increase the number of input frames, as shown in the plot on the bottom right. On the downside, it also increases the compute and RAM usage by a lot. considering having 10 frames as inputs, the input point cloud is now 10 times bigger, and the early convolution layers will spend much more time to consume all those points. The underlying cause for this inefficiency is that we aggregate information across the entire frames. While some objects may appear in up to 100 frames, but some others may only appear in a few. By setting a fixed frame context size, we cannot easily adapt to different objects. So to address this issue, instead of aggregating temporal context over the entire frames, we can aggregate information for each object track, such that we can leverage all sensor data captured for a certain object. This also opens doors for new algorithm formulations. The only downside, as far as I think, is that we'll need to rely on detectors and trackers to collect object tracks. However, with very fast advances in detection technology, we believe this is not a bottleneck. So based on the discussion and observation above, now we present our object-centric off-board 3D detection pipeline. From the point cloud sequence input, we first run an off-board multi-frame detector to localize objects in the scene. Then we use a multi-object tracker to link detections across frames to form object tracks. Next, we have a unique module to aggregate object points from their tracks across all frames. For static objects, we would have very dense points with a very good coverage of different viewpoints. As shown in this example, we have more than 80,000 points from 109 frames for this car. For dynamic objects, we would have its full trajectory with points at every frame. The trajectory geometry will help us optimize the heading of the car as well as its position to make it very smooth across frames. We take a divide and conquer approach to process those two types of objects separately. We have a track-based motion state classifier to classify object tracks into static ones and dynamic ones. And we then refine the boxes of the object tracks with specialized deep neural networks. The final outputs are the accurate and consistent 3D bounding boxes of the objects at every frame. I want to elaborate a bit more on how we refine the object shape for its track data. For static ones, the aggregated points are naturally aligned. The key is to select a good coordinate system, for which we can use the box coordinates from the highest score frame, so that we get the best heading and the best center estimation from that frame. Then it is a series of operations including foreground segmentation to remove the clutters around the objects, as well as a cascaded box regression process, similar to that in the cascaded RCAN. Notice that the key ingredients here is 1, selecting the best initial box. Given the entire object track data, we can select the best frame to get the best viewpoint. And then it's also another key is the series of geometry transformations and cascaded optimization. For dynamic objects, the object track points are not aligned because we don't know the object motion between frames. We take a sliding window approach to refine for each frame separately. For a given frame T, the input are the sequence object points from nearby frames, as well as sequence boxes. The box sequence can have a larger temporal context, as the box input is much smaller in size. Then we have 2 branches to encode the point features and box features before merging them. There are many other alternative designs, such as using ICP-based methods to align the points before any refinement, or using a flow prediction model to align the points. However, aligning the points across frames can easily become a more challenging job than refining the boxes themselves, especially for occluded cases. In our empirical experiments, it's not easy to match the performance of the current formulation using align first and then refine method. A more fancier formulation would be sequence-to-sequence models, considering that the input is a sequence of points at every frame and a sequence of detector boxes at every frame. We can have a sequence input and then output the entire sequence for each frame as refined boxes. We also tried a few like baseline implementations, but again, it's not easy to match the formulation as the current one. So we will leave this to more future research to explore more efficient and effective problem formulations and model designs. As the pipeline has many similarities to how humans annotate 3D objects in a sequence, meaning that they first localize objects, then they track objects across frames, and they will take a deeper look at each object track to make sure the boxes are consistent across frames. We call our entire pipeline 3D auto-labeling. Evaluated on the Waymo open dataset, we show that our method largely outperforms existing detectors. The plot shows that the 3D average precision at different IOU thresholds. It naturally decreases as the criteria becomes more strict, meaning higher IOU thresholds. We compare our methods with two popular detectors, which are often used in the onboard cases, the point pillar detector and the PVRCN detector. We see that our offboard pipeline consistently outperform the baselines, especially at higher IOU threshold, validating the high quality of our auto labels. Here we show more complete evaluation results comparing with more methods. As our pipeline is built on top of detectors, it's very important to have strong detector backbones to ensure the high quality overall performance. We are glad to see that our internal enhanced multi-view fusion detector called Multi-View Fusion++ has already outperformed most existing works, even though it's in a single frame input format. By having more input frames to the detector, as well as having some test time augmentation, we can further improve its performance across all metrics. And finally, the 3D auto-labeling pipeline, which leverages the detector as a backbone module, as well as the object-centric auto-labeling refiner modules, we can get the best results. And notice that it significantly improves on top of the already very strong multi-frame detector. Reflecting our pursuit at the very initial motivation stage, we want to reach near human performance in detection. So to understand how far we are from human labels, we did a human label study on 3D object detection. We selected a few run segments or sequences from the Waymo open dataset and asked different annotators to independently relabel each sequence from scratch. We see that although human agrees in most cases, there are still inconsistencies, as shown here. We visualize different humans' labels in 3 different colors, red, yellow, and blue. There are some inconsistencies in both the geometry as well as the recall. By considering the human annotations as detection outputs from humans, we can compare their results with the ground truth in the original Waymo open dataset to get human average precision. We can rank those detections based on the number of points or the distances of the boxes. By comparing the average precision of auto labels and humans, we found that auto labels from our pipeline have achieved on par results as humans. The gap at the 3D AP at 70% IOU threshold is just 1 point. And at a bird's eye view AP at 80%, auto labels even outperformed human labels, which is very exciting. With such high quality, a natural application is semi-supervised learning, where our pipeline can be used to pseudo-label unannotated data to train student models, together with the mixture of human labels. In the low data regime, using auto labels can largely close the gap between using 10% and 100% of the human labels. As we can see in this plot, using just the 10% of the human label, we see a significant drop in performance compared to the same model trained with 100% data. If we train the offboard perception pipeline on the 10% data, and then use this offboard model to auto-label the rest of 90% data to train the student model, we see the gap can be largely closed. In other words, using 3D auto-labels can lead to a close to 10 times data efficiency boost in this low label regime. Our pipeline can also help the student to better generalize to a new domain, in the case of unsupervised domain adaptation. Here, the old domain is mostly sunny weather, and new domain is mostly rainy weather. We see that the student trained on old domain data performed not that great on the new domain, with 59 points in AP. But if we use the offboard detector trained on the old domain as well, and use this to auto-label a set of unlabeled sequences in the new domain, we can augment the training data for the student model. And the student model trained on both the human label on the old domain and auto-label in the new domain can be significantly improved compared to the baseline. We believe there are more applications to be discovered for the offboard 3D detection. Now let's look at some visualization results. Here we can see in the city driving, the parked cars on both sides are very stable. And then the moving cars have very smooth bounding boxes. And this is a very busy intersection. Notice that how the headings are very accurate. And we are still having some flaky results for the pedestrians because the tracking for crowded pedestrians is still a challenging problem. This is a scene for the parking lot. We can see stable boxes for those densely parked cars. Okay, another application of our offboard 3D detection is behavior prediction. We know that behavior prediction or motion forecasting is a new frontier in autonomous driving research. Both its training and evaluation will depend on perception data. So to really focus on the study of the behavior prediction problem itself, we would like to control the variable, meaning that we want to separate perception noises from the BP problem. To do that, we can leverage the offboard 3D object detection pipeline, as we mentioned above, to construct the Waymo open motion dataset. More details about this dataset is summarized in this archive paper. Here I want to visualize some example results in this dataset. Here is a very dense intersection with a lot of things happening from both pedestrians and cars. And here is an interaction case where a car is waiting for the self-driving car to pass to turn right. This dataset with minimum perception noise thanks to the offboard perception can provide new opportunities for BP research and help us to get more focused research without worrying about noises in perception. To know more about the dataset and the related challenge results, you are welcome to join the organized workshop for autonomous driving and there will be a talk on the Waymo Open Dataset Challenge on Sunday, 9 a.m. Pacific time. To summarize, in this talk, we have introduced the off-board perception problem and an off-board 3D object detector pipeline using point cloud sequences. The object-centric formulation to leverage long-horizon temporal context is key to our success to achieve close to human detection quality. There are a wide range of applications from assisted human labeling, semi-supervised learning, unsupervised domain adaptation, to the creation of a large-scale motion forecasting dataset, and many more to be discovered. That's it for the talk. Thank you for listening, and I will welcome any questions in the Q&A section. Thank you.
Right. So the last talk in this session will be from Arun Venkatraman on the value proposition of forecasting for motion planning. Arun is a founding engineer at Aurora, the company delivering self-driving technology. Arun completed his PhD at Robotics Institute at CMU. And during his time at CMU and REC, Arun worked on a variety of robotics applications and received the Best Paper Award at Robotics Science and Systems 2015 for work on autonomy-assisted operation via brain-computer interface. At Aurora, Arun leads the motion planning behavior planning team, bringing together the best in machine learning with the best practices in robotics development to develop the Aurora driver.
Hi everyone, my name is Arun Venkatraman. I'm one of the founding engineers at Aurora and the lead of the motion planning behavior planning team. Today I want to talk about the value proposition of forecasting for motion planning. How does forecasting fit in with motion planning, and what mathematical framework can we think of that makes forecasting and motion planning a unified entity that we can think about for the system level as a whole? And with that, let's dive in. So at Aurora, our mission is to deliver the benefits of self-driving technologies safely, quickly, and broadly. We believe with our multimodal sensing capabilities from LiDARs, radars, and cameras to the AI intelligence we're building inside of the Aurora driver allows us to build a product that can help deliver goods to the customers that need them and give passengers a comfortable and safe ride wherever they need to go. We have our technologies working on multiple platforms. Here you can see one of our trucking platforms delivering freight goods. We also have our same AI technologies working on passenger vehicles as well for the ride-hailing services and any other use cases we need in different operational domains such as highways and cities. So what really is it that makes the Aurora driver the Aurora driver? So the Aurora driver, like other self-driving systems, takes a bunch of inputs on the left-hand side to produce 3 outputs on the right. So it takes inputs as LiDARs, the radars, the cameras, the map and vehicle state information such as brake lights and vehicle odometry. In effect, it does a giant compression to move these into steering, throttle and brake, and turn signals so that we can show our intent to other actors in the world. And if we think about data rates for a second, on the left-hand side we have something on the order of half a gigabyte per second, and on the right-hand side we're producing very low-dimensional outputs. We're producing a steering angle of some sort, a longitudinal control of some sort, and a simple boolean for a turn signal indication. And if you think about this, this is about 100,000 times compression factor. So what we're doing in the Aurora driver is taking all of these high-density inputs and trying to compress them into produce just a single action per cycle that contributes of these 3 components. So the core question of the Aurora driver is, how do I do this compression to figure out what actions to command at every cycle? From the inputs I see on the road, how do I convert this into actions I should take? And we can actually develop a mathematical framework to think about this holistically. On one side, we have the state representation. We're trying to understand what is the state of the world. And on the right-hand side, we're trying to produce an action in response. And to do this, we can define a utility function, Q, which is a value function, or action value function, that defines the goodness of taking any action at any given state. And that really is the crux of the Aurora driver, is that it's continuously trying to figure out, how do I maximize the utility, how do I maximize the value of taking any action? How good is it that I take a brake or throttle command? How good is it how much I steer? And should I turn on the turn signal indicator or not to show my intent? All of these together make up the Aurora driver. So let's try to break that down by talking about what state and action are in the concept of this utility function or value function. So we start off with the vehicle. Here's one of our older Lincoln MKZ platforms. It's booting up. Right now we have very basic estimation of state. We know, for example, what the brake light state is for the vehicle, or we might know some simple things like the gear and things like that for the vehicle. But this clearly isn't enough to do driving. If that's all I knew, almost like my blinds on my eyes, couldn't drive very well. The next thing to do is add basic sensing capabilities. So now we added cameras and LiDARs and radars. We have sensing of the world around us. But this still isn't quite state. I can't really just drive around if all I can see is this much information. You and I, when we commute to work every day, we don't just drive only as if the world is fresh to us every day. We might use something like a map information, know where we are in the world. And we use this to guide where we should go next. Knowing where we are lets us know where we need to go next. So the first step of making this state is using the sensor observations we have to guide us to where we are now. This is localization. But is this enough to now start driving? Well, you and I can look at this image. We do, and we segment it out. And we can segment it out to find objects in the world and find things like the traffic lights, and then estimate the state of those elements. So for the traffic lights, we can estimate that the state is red in this case. And for other vehicles, we can estimate their position, the extents, how big are they. We can estimate their velocities, their accelerations, and so on from the sensing capabilities we have. And these are all important to help build up a state representation, which is a compression of all that I've observed so far into a denser representation that lets me know that helps me then define what actions I need to take next. So then that gives us state. So we have world state, we know we're on the map. We have vehicle state, we know various odometry information about the vehicle. We also now have perception state. We have ideas about the state of the world, traffic lights, vehicles, and so on. So then the question now is, what is actions in this concept? Where do actions fit in? And we can watch this play out in motion. So here, starting from the very beginning again, we can see the first two cars go because they have a green light. And right as the light turns green, you can see an actor actually cuts the red, and the AV needs to make a decision that it should come to a stop, that the other actor isn't going to come to a stop for it, and it should go through. And now we come across, we're waiting at the unprotected left turn, or UPL for short, and a pedestrian crosses the intersection. So now we need to make a decision that we should not try to cut the pedestrian crosswalk because we need to give them space to go. And now finally, the vehicles have come to a stop, a gap is formed, and the AV sees that it is now able to achieve its mission of completing the turning following along the route as predefined. So all of this end-to-end we're seeing is that we have the vehicle defining state. It's looking at all the objects in the world, finding their state, their velocities, their positions, and so on, and then finding out what actions it should take as a result given the state. And the challenge in all of this, what made this challenging, and this is sort of the obvious challenge in self-driving, is that the future of other actors is what affects what actions the AV should take and affects this utility. When we decided that we shouldn't go in front of the first actor and that taking that first slot that we marked with red, this was because we believe the other actor is trying to come across the intersection, and they already have that intent, and it's really their right of way. So the future of what other actor is going to do really defines what's going to happen. For the actor very far away, we think it's mostly okay because we believe that the future of them gives them a chance for them to slow down if necessary. And for the actor in between, we're trying to decide what they are doing, and if what they're doing allows us to take the action we want to take. And this really comes to the core of the challenge for self-driving, is that in order for us to make an action, we need to know the future. So this therefore implies we need to have some concept of a forecasting system within the self-driving vehicle to have an understanding of what the future will be. So here's a common example of a situation our self-driving trucks come across all the time. Here it is driving down a highway in Texas, and on the right-hand side we have a bunch of vehicles coming in to merge onto the highway. And the question we must ask ourselves is, what slot, again, similar to the left turn we took earlier, what slot should the vehicle aim for here, and how good is that given what we think the world is going to do? So naturally you might say that, well, in order for us to do motion planning, we need to have an idea of what actors will do, since that is clearly related to how good something is. So let me first go with perception. We'll figure out what the state of actors is, and then we're going to try to get a first level forecast of where things will be in the future, and then afterwards it should be trivial to do planning on it. I just need to do collision avoidance given the forecast. And so how does this look in the classical way? So first we talked about we run perception first. So here we have the state of the other actor. We simplified it to just a single truck and a single actor. merging onto the highway. So the first thing is perception runs. We get the state, we get velocity, turn signals, hazard lights, so on. We then go into the forecasting stage. The forecasting system produces a forecast, here shown as unimodal, of where the actor will be. And this sort of thing naturally, almost naively, shows up in the data. We want to produce a forecast for the actor that minimizes some sort of loss compared to all the data we've observed before. So what naturally could happen here? Well, if this is what is believed as the forecast for the planner, then the planner really has no choice but to try to break for this actor. The planner must try to go behind this actor because the forecast tells it this is where the actor will be. Well, okay, we know that might not always be the case. In the case where we started in the very beginning, the actor was just right alongside the truck, and maybe there's another world where we want the truck to go forward in. Well, so we can make our forecasting a little fancier. We might say there might be multiple outcomes of the world and try a multimodal forecast, here shown as a bimodal forecast. We can get two examples here. We put two modes here, maybe a mixture of Gaussians or any other fancy multimodal prediction system we want to build. And we might want to ask now, okay, so I have these modes of the actor distributions. Now I ask, how should the planner respond to this? Well, if I do something naive and ask it to do so in expectation, we might get something that's still overly conservative to this behavior. Because we haven't asked ourselves fundamentally, is this the right question to be asking? Here we've shown the distribution of P actor, T to T plus H, is just the marginal distribution of the actor's distribution, given the state of the world. However, at training time, our data was never collected from asking this question. Our data instead was collected as the vehicle drove, so we drove the truck in manual or even in autonomy, and collected a bunch of data of other actors around us, and then used that to fit a model of P actor. However, the data was collected conditioned on what the actual truck was doing at the time. The other actor, if they were to go in front or go behind, actually was related to what the truck did. And we can see this illustrated in this graph, in this more visual format. We can see there are multiple futures of what the car can do, but you and I looking at this can tell that each of these modes is related to what the vehicle must have done online when that log was recorded, when the data was collected. Specifically, we can try to break this down into two stages. There's the P actor given future given what the AV is trying to do. So in mode A, we can have that the AV yields to the actor, and this leads us to a distribution for the actor futures that's conditioned on what the AV is going to do. And in mode B, we can have where the AV is going ahead of the actor and get a forecast that's a function of this new conditioning of what the AV is trying to do. So in each of these cases, we're no longer saying that we're trying to make the marginal distribution of the actor behavior from the observed data. We can now ask the question instead, what is the actor trying to do considering that it's the AV? In many ways, this is what happens when we start thinking about joint forecasting systems within actor-actor interactions, but we must also ask the question of actor-AV interactions. And the moment we start asking about AV and actor interactions, we're really asking for the forecasting and planner interactions. And that is really the crux of this argument, which is that when the AV is doing its motion planning, it must account for the futures of the other vehicles as a function of what it's going to do. And that together helps us create the utility function for how good it is we take an action from any given state. So here we have in the top, we again have mode A, which is the AV yielding to an actor, and this helps us define the utility function. That function itself is a function of the forecast, which I tried to demonstrate here with saying the Q function is related to the joint distribution of both the AV and the actor. So if we condition on the AV trying to yield to the actor first, a discrete bit, we can find a utility function that tells us, as a function of their forecast and our own speed, how good this will be. So if I'm trying to yield to the actor, I want to go slower. If I'm trying to go ahead of the actor in mode B, I want to speed up to convey that intent. So this utility function captures more than just the naive forecast, but also captures intent prediction for the AVs. The AV needs to communicate its own intent to their actors so that we can get ourselves to go into the mode that we're trying to aim for. We want to yield to the other actor, showing our intent early on, make sure the other actor knows to speed up as well. So this actor-actor interaction is also actor-AV interaction. And the way to unify all this is to think about it in terms of the AV's value function. So this is the key idea, is that forecasting must be in service of and joint with the AV's value function. We cannot do forecasting independently as an a priori step if we really need to make sure that the value that the AV does, the way it conveys intent to the world, the way it drives like a human out there, needs to be such that the forecasting system is aware of that interaction as well. And the way to do this is through the value function. And this is the Aurora approach for how we think about forecasting, is that forecasting is intertwined with planning. We want to make the perception system feed into the motion planning system and have forecasting and planning work together to help define out what we think is the value function for various modes of behavior that could happen in the world. And then in continuous space, how do we think about how our actions, like such a speed that we can choose, relate to the goodness of how to take that action? And that's illustrated here. And going back to a more real-world example, here's an example of the vehicle taking a relatively congested merge out in Dallas. And you can see here that it slots smoothly and comfortably between these two vehicles. And if you notice at the very beginning, there's actually not enough gap in the slot for the full vehicle to fit. But over time, due to showing our intent, being assertive in the right amount to get to the right speed, we're able to convey intent to other actors that we are trying to aim for this slot, and the gap helps makes itself. Whereas if we try to do forecasting a priori and try to come up with the different modes, we'd likely get much more conservative behavior, and we have seen often more conservative behavior otherwise that forces the AV to stay back a lot more and not convey its intent, and therefore be more confusing to the world around it. So this also create a natural behavior for the vehicle and be a good citizen of the road. And this is really where the value of machine learning comes in for motion planning, is manual tuning of this value function or the forecasts that play into how we construct it makes it very difficult for us to understand how we are doing relative to how the world expects us to evolve. And you're really using data-driven methods, and machine learning lets us think about from everything from the discrete decision space to the continuous application of those decisions, how does our parameters need to be moved to get the behavior we need end-to-end, including how the world evolves around us. So here we're seeing a great example of some discrete decision-making happening where we can use something even simple like supervised learning to get an idea of what this Q function looks like when we think about supervised learning as a way to learn a policy. We can then think about non-discrete methods and think about imitation learning even, and think about how do we know that the parameters we choose act more like a human. So here's a relatively mundane cut-in that happens pretty often on the highway. However, if you build an overly conservative system here on the description of the utility function, you can end up with over-braking, which can cause surprise to both actors behind us as well as actors in adjacent lanes and not realizing why the truck is braking so hard. So using human driving data, we can help develop what is the need for the forecast in order for us to derive a proper utility function for the planner to take. So we can tune all the parameters here relative to human driving data to get a better estimate of how to drive like a good citizen of the road. Here's another example of this happening during a merge, where you can check different versions of software against the baseline human driving behavior shown as the green boxes. So here you can see the truck under different distributions, different types of code, acting very differently compared to the human in different cases. And we can use our data sets to help split based on various feature dimensions to have more introspection understanding of why our models are doing what they're doing, and we can build ones that are then closer to what we expect other drivers around us to see. So to summarize, the Aurora approach that we're taking here to planning is that we want to create a unionized mathematical framework that thinks about forecasting and planning together, as opposed to the classic approach of thinking of only search and heuristics on top of a pre-existing forecasting that could be learned but learned outside of the planner. And here, by doing so, we're able to create human-like behavior and nuances that help convey our intent to the world around us and act in an interpretable way. We also want to make sure that our system is verified with safety guardrails on top of this, so we're not just relying on machine learned models to do everything. Here, for example, on the very bottom, we have an intersection where as the light turns green, a red light runner clears us, and we're able to still make sure that we preserve the ability to stop for them. And this sort of approach lets us combine the best of some engineering practices and what we have learned in robotics and motion planning historically with thinking about forecasting and motion planning together as a nuanced, machine-learned approach that's data-driven. So as I conclude, I want to mention one thing and a call out to my colleague Carl Wellington, who's talking at a different CVPR workshop, is that we talked about how forecasting and the motion planning must be interlinked. There are some parts of what we might call forecasting which can actually be pushed up into the perception side as well. For example, anything related to state. Again, that's where perception helps us a lot, is estimation of state. And in some ways, a lot of actor behavior is not fully governed by the AV itself. Some of it is just innate to themselves, and that's state. Where's their meta objectives? What lanes are they roughly trying to target independent of the AV? These are still valid questions to ask, but they should be asked in the sense of what is state in order to feed the utility function. And to summarize, therefore, the whole system as a whole is moving towards trying to understand what is the utility function, and how do I take the maximum of this to find the action to execute on the vehicle. I want to just thank everyone at Aurora that's helped me build this understanding over the many years. In particular, thanks to Drew Bagnell, Sanjman Chowdhury, Hilton Bristow, Carl Wellington, Paul Vernazza, Haiyang Fan, Sai Yelamanchi, Fletcher Marsh, and Karth Lexmanen. Thank you very much.
All right. Well, I'd like to thank all the speakers for the amazing presentations. Just one moment. For some reason, I do not see other videos appearing on the YouTube stream. Jan, if you're here, could you please help me?
Hi, I'm here. What's the issue?
I don't see the videos of other speakers appearing on the YouTube stream. Appearing on the YouTube.
I can see you on YouTube. So
yeah, but
only
just
the
me.
speaker can show it on the YouTube.
I can see you.
But when in the previous Q&A, there were other people simultaneously. No? When did you do that?
Oh, I guess should be fine. So when people talk,
Right.
it should show on the YouTube.
All right. Well, let's proceed. All right. So yeah, thanks again for the amazing talks. I guess let's start with a question for Chen, which is how the price of the new generation LiDAR sensors compared to the previous ones?
Well, yeah, that's a good question. I don't think I can talk about the price here, but what I can say is that Waymo, we have a hardware team that designed the sensors and integrate the sensors, and we have a lot of control over and optimization over the design, manufacturing, and also a very tight integration between the perception team and the hardware team, so that we can really maximize the utility and reduce the cost for what's most useful for Waymo's system. And also it's a continuous process. The hardware team always tries very hard to really make the sensors more cost effective. And yeah, at this stage, there's always a very tight collaboration and integration, but also really understanding all the use cases of autonomous driving. As I talked in my talk, there are many different environments that we want our system to operate in. So that's also a very important goal right now, to really understand the capability of the sensors for it to be fully functional. Yeah.
All right, thanks, Chen. And I have a question for Anka, which is human working policies can be arguably simple. Would the approach that you presented generalize to more complex scenarios, like driving, where agents have like more complex policies, and any other limitations?
Yeah. Yeah. So I didn't get a chance to talk about it in the talk. Thanks for that question. We've definitely been taking this approach in driving, and this problem of predicting motion, predicting behavior of human-driven vehicles. And what's really helpful there is, again, that when you try to do it with a completely unstructured high-capacity model, you can end up completely picking up on crazy spurious correlations that happen. Like you might predict that people only brake when others brake, or stuff like that, right? And then what's helpful about this kind of notion of, well, I know something about why people drive the way they drive. I don't know everything, but I know that there's some sort of components that they care about, and I can sort of structure my policy in terms of being informed by those components, while kind of still maintaining the flexibility of learning from a lot of data. I think that's in our experience proven to be very helpful. I'll point the person who asked the question to this. It's a very self-serving answer, but there's an RSS paper this year that we published in the lab that looks a little more closely at actually the comparison between these intent-driven models and the sort of end-to-end high capacity models. And the kind of the gist of that is that when you're sort of smack in the middle of your training data, everything's great and you should just use a high capacity model. But the moment you introduce any kind of shift or you have some sort of outlier from your training data, then you're screwed and all hell breaks loose. And then these more structured approaches are super helpful. And so the thing that I'm very excited about is how do I kind of use the structured approach as a prior and enable it to kind of grow into a more nuanced posterior with high capacity models while still maintaining robustness when you're hit out of distribution events.
May I ask a question for Charles? Yeah, so other people also have a similar question. So in your model, can you predict non-rigid objects? Basically, for example, the pedestrian. So their pose will be changed. It's very hard to do the alignment on the point cloud. How you deal with the non-rigid object?
Yes, thanks for the question. So we also apply for pedestrians. But for pedestrians, it's, as you said, it's more tricky to align them across the frames. So we consider pedestrian always as dynamic objects. So process them through a sequence way. So have sequence input and refine their bounding boxes at every frame separately. It also will be interesting that if you have key point models, then somehow trying to use those key points to help you align them. But it's not yet in this way.
Thanks.
All right, thanks. And I guess for Arun, there is a question from Anka. Anka, do you want to ask the question?
Oh, I have so many questions. We've been chatting on the side, so I don't even know which one to pick at this point. I guess I had a minor question and a more major question. A minor question was about since you're trying to predict what people do, even in response to the self-driving car, but even if you try to do it in isolation, what they do probably depends on your on what their internal states are, their driving styles, their intentions, and so on. And so it seems like when you're talking us through what do you need to put in your state for your Q value function, Q of SNA, you're saying, well, I look at everything that's around, I even look at their accelerations, but probably you also meant I kind of need to look at history as well, because it's history that's going to inform me what's going to happen right next as a consequence of my next action, because that's what people it's the internal states that drive them. So that was the kind of the minor question, and I don't mind just say, yeah, we have to use history. The major question was more like when you start doing these conditional predictions, how do you deal with distribution shift? How do you deal with the fact that now you're asking the model to predict based on hypothetical counterfactual trajectories that your planner is considering that maybe you've never driven, you've never seen driven, so they're completely out of distribution with respect to the data that you've trained your conditional model on?
Yeah, those are both good questions. I think the first one is a little bit almost easier to handle. We know in some level we have to solve a game POMDP. It's like worse than, so the naive thing is we set up a NDP, right? We all know kind of how to solve that. But reality, we know that's not quite true. As you said, like we choose our actions, other actors are going to respond to us in some way. And they have an observation of what we're trying to do and they're responding to that. So that's an observation model and they have hidden state. So when we say we want to find state, even that is one of the crux, that's the other maybe crux of the problem is what is state and how do we represent that well for the learner or for any engineer models even that we're building. So history is definitely helpful because when we think about POMDPs, now we have a partially observable model. Infinite history in some sense is necessary for us to have a sufficient representation of state. However, we might find a compression of that state, a compact representation that captures the bits we need. I said acceleration, but you're right. We do use things that look like history of what the other actors are doing. But you can't maybe use an infinite history because sometimes you're on the highway driving for thousands of miles and there's just the same truck that's behind you or in front of you the whole time. You don't want to store their infinite history. So you might assume there's some sort of finite impulse response. I mean, there's some great work in the machine learning conferences on how you can get good approximations of finite impulse response systems to things that look more IIR, but you can use things like turn signal states, how long has a turn signal been active. So this is a way of compactly storing that representation, sort of, every time step storing exactly what their exact state was. So I think some of the cleverness that you will have to do is try to figure out how to represent this compactly so you can build a practical robot, not something that's just theoretically more correct. We can't have infinite tape. So that answers the first question, I think, a little bit. It's you do what is necessary for you to represent state. And that's always a growing question as you encounter more and more complex ODDs, operational domains. For the second question, how do you condition, how do you deal with the counterfactual? I think I'll just ask it as that question, because I think that is the fundamental problem in almost all of robotics, is the robot can take any of these actions. So we are at a state, there are a sequence of actions, and in the continuous space here, we have infinite such actions we could take. How do you know how the world will respond to all of these? Anka herself sort of gave some of the answers to this, which is that strong priors help, is that the world is not arbitrarily moving on some arbitrary Rn manifold. There's physics involved. The world has some amount of reality to it. Other actors also have some amount of reality to them on their observation models. Like, when would we expect them to respond and react? So using certain priors here, we can help limit the model class that we want to consider into a space that we expect reasonable responses for anything the AV will do. We can also leverage large amounts of data. I think this is one of the benefits of working at a company like Aurora, which has just so many people and so many people that are really interested and motivated to help us solve this problem, is you can actually ask the counterfactual surprisingly number of times by going through your data set better. So having good tooling and really focusing on data set quality and having that exploration in your state space is super useful, actually. There turns out a lot of things. I think on the last slide I showed like a red light runner, and even on the early slides there was someone who just cut the red light. These are not actually that uncommon. Like, the long tail that we talk about often is actually quite heavy. It's not so out there until you get to tons and tons of miles. There's always small little things that you're seeing throughout your data set collection. So I think I'm sort of sidestepping a little bit by saying there was a paper, Anka, you had long ago, which was in December, like, if you can just get more state space coverage, you can start to answer more of these questions more directly, and then try to use simulation. So we use a lot of simulation to test different type of actor behaviors on top of what the AV is going to do. So we can ask the AV to even take specific actions and say, what would that respond to? And then we can effectively use that to relabel the data and have other ways to go create that situation. Some situations which are very safety critical that we need to do, we can even do simulations in test tracks where we can use dummies and things like that to make sure that we have a safe environment that we can construct these construct situations. So there's many different ways we can use it, but mostly comes down to we need to be able to cover the state space and action space that we expect to actually practically get to. We can't, for example, shoot to the moon. Like, that would be physically impossible. So we know that there is some limit to the manifold. Can we just stay in that and cover that state space?
Hey, thanks so much for Arun and Anka. We're running a little bit late. I guess let's extend a little bit the Q&A session and ask for another round of questions. So there is a question for Chen. The question is, if you have tried to train a depth model on the synthetic camera images, will the depth model perform similar as the depth model trained on real camera images?
So I assume the question when saying training the depth model on the synthetic images, that's a supervised approach, right? In the talk, I mentioned both unsupervised approach, where you can train from real images, but also using a proxy ground truth on the real data. So I can talk about both. I think it's the problem with synthetic images is that it's hard to be very diverse unless you invest a lot of time generating very diverse data sets. So in general, it's harder to have a real great results from just the synthetic data sets. Well, it's definitely possible if you spend a lot of time generating really diverse and large data sets. But everyone uses flying chairs, for example. That is very useful to build a baseline model, but then it doesn't entirely apply to autonomous driving situations. I mean, so in general, in our experience, a hybrid approach definitely works. unsupervised, where you can use the real driving images, some supervision from synthetic data set, but hopefully more EV-like synthetic data set, but also the proxy ground truths that I mentioned there. Not a perfect ground truth with the proxy ground truths, but still very helpful. So I will say in a practical sense, a combination of all of the approaches really help. Yeah, thank you.
Thanks, Jen. Right, there is another question for Anka from Jan. Jan, do you want to ask the question?
Yeah, thanks. My question is, you mentioned the beta model to detect the outliers. So would the beta model train together with the planning model end-to-end? How to guarantee the beta model learn a reasonable output?
What do you mean by training it together with the planning model?
The beta model will output a beta, and then the beta is a parameter of your loss function.
The beta, so just to clarify, there's a planner that in our setting is separate from this prediction model, whether it's a conditional prediction model like what Arun was talking about, or
I mean the prediction model, sorry.
Yeah, okay, yeah. So we train a prediction model, and then the notion is that the beta estimation happens online at runtime. So as you're observing the human, roughly what's happening is your model is making predictions about what the human will do, right, at every step. You have you yourself are observing what the person is actually doing. And after 1, 2, 3, 4 steps of this, the more the person is taking actions that have very low probability with respect to in the probability distribution that you've predicted, that is sort of the warning flag of, okay, something's going wrong. The nice thing about structuring the model with this sort of people have intentions and they're approximately rational is that because you can do this sort of detection of people are taking actions that have low probability in my model, regardless of the model that you're using. You don't have to assume that people are approximately rational to do that. What's interesting about assuming that people are approximately rational is that at the next time step, right? So after you've estimated based on the previous couple time steps that the person is not acting according to your model, at the next time step, that low beta in the rationality model will automatically start modeling the person with much higher entropy. And then that will automatically make the robot on the planning side stay further away from the person. When you're using a model that doesn't have this kind of intentionality, inductive bias to it, and you're using just your, take, for instance, Waymo's TNT or multipath or, whatever Arun has published on the Aurora side, take any of these things, if they're complete black boxes, then you kind of have to start figuring out how to automatically adjust the variance of your predictions in the future once you've detected this. And there are ways to do that even with those models that very actually closely resemble. In a sense, the more the model resembles the structure of exponential Boltzmann distributions over values, the more automatically this thing will happen and you won't have to hack anything. If you have a complete black box, then you can sort of add variance automatically, but then that's really hacky and janky, and I don't like that. So that's one, extra bonus of these intent-driven models is that they automatically adapt. But yes, to your point, it happens online. It's not something that you actually learn from your training data, because then that would defeat the purpose. The point is it's a monitoring system online that then adapts you can think of it as choosing from a space of models that you might have learned offline. And it's really choosing the sort of the variance of that model.
Thanks, yeah.
All right, thanks, Jan and Anka. There is a question for Charles. Do you have a sense of the main qualitative kinds of improvements you see with output 3D auto-labeling versus multi-frame detector with KF tracking?
Yeah, okay, thanks for the question. So I think the most improvements will come from the cases that are more challenging, like the occluded cases where you have very few points. considering like for static objects where you first see it, it could be very far away. But after you have seen the entire trajectory of it, you have a more complete viewpoint of that car, right? If we have succeeded in classifying it as a static one, then we can use a single static bounding box to cover its entire trajectory. So when you get close to the car, then you have more points, and this information can be passed to those distant frames when it has very few points. So those boxes will be significantly improved. And even for dynamic ones, as we have more points as the sequence input, and also as well as the box in the trajectory input, its heading can also be greatly improved. So those are two types of improvement we see for the vehicles. Yeah.
Right. Thanks, Charles. Okay, let's do one last question for Arun and switch to contributed talks. The question is, what about if there is a confusion between the actor-AV interaction and intent? As Q function is continuous, there are close interactions in both which might cause intent confusions. How do you tackle that problem? Does the AV just stop moving, or do you predefine the behavior as conservative?
This is a good question, and I actually did have a slide that would have been very good for tackling this, but I removed it for the interest of time. So this has happened, especially in the sort of merge situations we were talking about, or anything where there is this close interaction where you can easily get yourself in a situation where both the AV and the other actor are trying to yield to each other. So we are clearly conveying some intent. They're also trying to convey the same intent. We get ourselves stuck. So we talked about finding the conditional distribution. It's still a distribution over what we expect the world to evolve as, conditional on what we're doing. So even if we're starting to yield, we use things like their history, as Anka asked in her first question, to try to guess what is their intent simultaneously relative to the vehicle. And this allows us to understand what is happening jointly in the scene, and then we can decide to go either way. If we, based on the situation, again, this depends on exactly the, almost like where we are in state space, but we can actually move in either direction. So it's not saying that we must always act conservative in these cases. Is we need to therefore be even more crisp in showing our intent. That just shows up naturally as part of the utility function. It's not almost magical, because in your data there are cases we have where an expert human driver has gotten themselves in the same situation. This just happens naturally due to this POM-DP structure that we're talking about between anyone. It's a multi-agent problem where everyone doesn't have full state on everyone else. So even within our data set, we can see examples of this. And the system can learn that in order to improve utility, we need to either make one of those two sort of discrete decisions. In the case of a merging actor, go in front or go behind. And how we execute that motion especially changes depending on how the other actor is responding. So we're tied up. There was an example where we're tied up neck to neck. We're both trying to yield to each other. The vehicle can just decide to either speed up now to show its intent and say, I'm going to go, or should it pull back and come back? And that nuance is really defined by what we see in our data. What we see our expert trained vehicle operators doing, and trying to replicate that in our system itself.
All right, thanks, Arun. I'd like to thank again all the speakers for the talks and the Q&A session. And there is still some questions left on YouTube and Zoom, so if you could reply, we would greatly appreciate it. With this, let's conclude the Q&A section. Thanks again. And I will now turn the contributed talks, which are the best paper, which will be the talks for the best papers.
We present a novel domain adaptation framework that uses morphologic segmentation to translate images from arbitrary input domains into a uniform output domain. An input image is transformed into the output image using our framework. we first generate an edge plus segmentation map as intermediate representation, to then generate the output image in the target domain with an image-to-image translation gun. Here we see how images from different input domains are transferred into the same output domain. The first two examples show photographs, while the last two examples show renderings of synthetic scenes. Although the input image styles vastly differ, the output style is consistent. For instance, the cloudy second image now shows a sunny day, and the dry, desert-like environment in the third image is turned into a much greener version. Our framework has a number of applications. Firstly, it can be used to extend datasets. Creating labels for input images is a costly and time-consuming task. For our generated images, however, the EPS maps from which they were generated act as ground truth labels so that no additional manual labeling is required. Secondly, images from various sources can be transformed into a common look. Synthetic renderings are enhanced in this process, while photos can lose some of their details. However, artifacts like lens flare or blur are removed, and thus also photographs can be enhanced. Most importantly, we envision our method to be used for the training of downstream tasks. Since images from multiple sources are unified and artifacts are removed, such downstream tasks could be trained on simpler architectures in less time. Let us now take a closer look at how the EPS maps are generated. We start with the original image and use it as the input for a semantic segmentation network. The detected semantic classes are encoded with different colors in the output image. Here, we use the same class-to-color mapping as in the popular cityscapes benchmark. However, this choice is arbitrary, and every mapping that contains all required classes could be used. In the next step, we take the original image as input for an edge detection network to generate an edge map. Keep in mind that the edge map is different from a contour map. It also contains edges inside the object, and the boundaries of objects are not guaranteed to be closed loops. The result is a black and white image where white pixels mark the edges. Finally, to create the EPS maps, both images are combined. This is done through addition of the pixel values with subsequent clipping to the valid range. Effectively, this means that the white pixels of the edge map overlay the segmentation map. EPS maps are a compact representation of the geometry and types of the objects in the scene. In other words, they represent a morphologic segmentation of the scene. The two networks responsible for generating the EPS maps are in principle interchangeable and may be exchanged depending on the use case. Here we choose DeepLab v3 by Chen et al. For the semantic segmentation, as it is one of today's leading segmentation network. DeepLab can be used with different backends. In our case, we choose exception 71. Since we emphasize autonomous driving as an application, we chose a checkpoint trained with the classes and images from the cityscapes benchmark. For edge detection, we use DexiNet-V by Soria et al., again a state-of-the-art network. As edge detection is a more general task and does not rely on a certain set of classes, we use the default pre-trained checkpoint that is provided by the authors. Now that we have the EPS map as intermediate representation, it is used in the second step to create the final output image. To this end, we utilize a conditional gun for the image-to-image transfer. C-guns have a rich history in style transfer and domain shift applications, and thus we again can rely on a proven solution for this task, the Pix2Pix HD architecture by Wang et al. It takes the EPS map as input and produces a realistic-looking image in the target domain from it. Please note that at this step in the pipeline, the original input image is not used at all. To train the C-gun, we first have to collect images from our target domain. We choose to take dashcam recordings from YouTube and collect a total of 98 high-resolution videos with a total length of about 45 hours. The majority of them are filmed in Europe on summer days with clear sky, and these characteristics will reappear in our output images. Not all parts of the videos were suitable, and consecutive frames are highly redundant, so we selected a total of 101,000 frames as training material. The training was performed on 3 RTX 2080 Ti GPUs and took about 20 days. The pix-to-pix network requires pairs of images from the source and the target domain for training. Since we have an automated pipeline for the EPS map generation, those pairs are readily generated from the video frames and no manual labeling is involved in the process. To enhance the results, the network is trained with progressively increasing resolution. The generated images have a realistic look, but also sometimes contain artifacts. For a more objective measure, we therefore compute the intersection over union score of the generated images. First, the input image is processed into an EPS map. This EPS map is then turned into a generated image of the same scene. This result is then processed again to create another EPS map. We split the segmentation from the EPS maps and compare them using the established IOU score. The results then tell us how well the input image has been recreated. Please note that the segmentation network never saw any images created by our pipeline during its training. This histogram shows how well images from different input sources are reconstructed. The most notable observation is the Gaussian shape of the IOU distributions for each class. Furthermore, real pictures, such as from cityscapes or Kitty, tend to perform better than synthetic renderings, such as from Color or FCAF. We suggest that this is due to the fact that the semantic segmentation network and the edge detection network, as well as the style transfer network, were all trained on real photographs and videos. Our output images should not only resemble the scene of the input image, they should also have a uniform look, independent from the input source. To objectively evaluate this, we train an autoencoder to recreate images and visualize its embedding space using a t-SNE dimension reduction. When the input images are used, clear clusters emerge. This suggests that the input domain can be easily extracted from the images. In the second round, generated images from the same sources are processed in the same fashion. This time, the distribution in the embedding space is much more uniform and clear clusters do no longer exist. This suggests that it would be very hard to detect the input domain from the generated images, and thus that the domain gap was successfully closed. In conclusion, we have presented a novel framework that is capable of translating images from various input sources into a unified target domain. To this end, we introduced EPS maps, which are a compact representation of morphological segmentation. In the future, this framework could be used to improve the training of downstream tasks. Since the generated images have a lower complexity compared to the various possible input sources, we expect improved training results on tasks like classification, object detection, semantic segmentation, or others. More details on the method, as well as a more thorough evaluation of its result and a discussion of its limitations, can be found in our paper.
Hello everyone, my name is Adam Ścibier. I'm a co-founder of Inverted AI and a postdoc at the University of British Columbia, and it is my pleasure to present Imagining the Road Ahead, joint work with my collaborators at both those places. We're dealing with the problem of trajectory prediction, so very briefly the problem statement is we have a map and historical trajectories of some vehicles. The goal is to predict where they're gonna be in the future. We're working in particular with the interaction dataset, where we're given 1 second of history and predict 3 seconds into the future. The time step is 100 milliseconds. And you'll note that the colors in the visualization change after 1 second. This is very much deliberate and indicates that this is the end of history, and from that point on we start predicting. There are all sorts of existing approaches to the trajectory prediction task. The crucial distinction between different approaches for our purposes here is whether we do one-shot or sequential. So in one-shot, you combine all the historical data you have about the agent and the environment, encode them, and based on that you make a prediction for the full trajectory of the agent. In contrast, in a sequential setting, you only predict 1 step into the future, consider interactions with the environment and other agents explicitly, predict another time step, and so on. So we're taking the sequential approach here. And moreover, we're decomposing the predictive model into a policy and an environment. So the motivating idea for this is that the difficult part to model about how human-operated vehicles move on the road is the human driving policy. So we know that people receive some visual observations and based on that perform steering actions. And that is the part that's very difficult to model, and we effectively parameterize it by a neural network and learn that. On the other hand, the basics of how the vehicles respond to those steering actions and what sort of visual inputs the humans observe, those are not that difficult to model. So those we encapsulate in a hand-coded environment. It's a very simplified representation of what's happening on the road in that context. Now, what's crucial for making this whole setup work is we make the environment very lightweight so we can execute it quickly and keep everything on the GPU. But crucially, we also make it differentiable, because effectively we're doing imitation learning here, and being able to differentiate through the environment really helps with the covariance shift problem. So we learn the policy combined with the hand-coded environment, and jointly those two together combine form a predictive model of trajectories. To build the environment, we use a few very commonly applied components. One is the kinematic bicycle model, textbook stuff, translates the steering and acceleration into the motion of a vehicle. Two is the bird view rasterization. This is also well established in the literature as a means of providing input about the map and the other agents to a particular agent. So here we see in the top a particular situation unfolding in a fixed coordinate frame, and in the bottom row we see how different agents in the scene view the same scene from their own egocentric, ego-rotated perspective, where each ego vehicle is colored in red. The final component is the variational autoencoder. So we add some latent variables to the model, which allows us to predict not only the single most likely trajectory of a vehicle, but the full distribution over the possible trajectories. So in particular, in this image, we see that we both have a multimodality of predictions, where the red car can go either straight or left. And within each of those choices, those modes, we see that different samples lead to slightly different ways of going in that direction. So putting those components together and some standard recurrent and convolutional neural networks, we obtain full ITRA, where every agent is its own variational recurrent neural network and they're all interacting in this shared environment. So let's look at some prediction results. Here are 8 maps from the interaction dataset, where we unfold the predictions 6 seconds into the future. Now we trained for 3 seconds, unroll for 6. You might expect in this sort of models, as you unfold them longer than they were trained for, you'll eventually see some drift that takes them away from the data distribution. That certainly happens, but it doesn't happen immediately, so we can definitely produce good predictions for 6 seconds. And that's enough to observe some interesting interactions and predictions. For example, here we see a vehicle overtaking another one, or the red car, we don't know if it's turning left on the roundabout or taking right and the exit. So we see a nice bifurcation of the predictions here. The numbers are looking really good. I'm not gonna dwell on that too much. We have average and final displacement error. And what's really exciting is that we also tried the generalization track of the interpret challenge associated with the interaction dataset, where we tried ITRA on maps for which no training data was even released. So you see here some visualizations of those examples. And we achieved mean ADE of about 0.41, which is roughly twice what we get on the training maps. So full details about ITRA and the associated experiments are available in the full version of the paper. It's already up on arXiv and has just been accepted for publication at ITSC. And we can spend the rest of the time remaining in this talk to just look at some examples of the sort of behaviors that ITRA can generate. Now, something we're very interested in at Inverted AI is populating virtual worlds with human-like driving agents. So, in fact, we have instantiated ITRA as vehicles operating in Carla. So let's look at some examples of how it performs there. And just to be very clear, we've performed no domain adaptation here. We've trained on the interaction dataset, predicting 3 seconds. And what you see here is what ITRA does in Carla. All the vehicles and all the visualizations are controlled by ITRA. So starting easy, almost empty highway, see sensible driving behavior, following lanes, changing lanes, all good. Right? Moving on into the city, vehicles driving side by side into lanes, again lane keeping, and on the bottom you see Tesla successfully executing a lane change maneuver. Moving on to a more complicated setting on a roundabout, here we're doing a 14-second prediction into the future, and we see again ITRA is generating quite reasonable results, and you see that the cars don't exactly follow the lanes much like humans wouldn't. Okay, let's move on to some more interactive scenarios, and in particular, just as humans do, we'll see ITRA agents actually breaking the rules of traffic. In particular here, we have the black car is failing to yield and forcing the oncoming vehicles to slow down. Here, watch the red vehicle. You'll see as the truck exits the roundabout, it decides to cut in a very, very dangerous way. So sometimes things don't work as well, so just to be very transparent and give you some bad examples, here is a bad prediction of ITRA where you see the green vehicle decides to go off-road for no particular reason. And for when things go really, really bad, it took me a while to find this example, but you'll see we've disabled collision physics here, so you can see exactly what's being predicted, but it's basically just total carnage. Everything is colliding with everything. On the other hand, sometimes we see ITRA executing some quite sophisticated maneuvers. So watch the silver car here. It's executing a pretty long-range maneuver to go around that cyclist and into the intersection. Finally, I mentioned that we're not just learning a single most likely trajectory, but the full distribution. So look at the order in which the cars exit the roundabout here. And now if we take another sample from ITRA, we see this time the bus is going in front of the small car. And similar here, watch the silver car going in front of the police car. Taking another sample, we see now the police car is going first. All right, so it's a lot of fun to look at those examples. We could do it all day, but it's time to wrap up. So many thanks to my great collaborators, Vasilios, Daniela, Payman, Frank. Thank you everyone listening. Please come find me at the poster session or email me at adam@inverted.ai if you want to chat about those topics more. Thank you very much for your attention.
My name is Henry, and I'm presenting Pilot, Efficient Planning by Imitation Learning and Optimization for Safe Autonomous Driving. This is research done at 5, a UK-based autonomous driving startup. First, I'd like to briefly discuss the 3 foundational pillars of planning for autonomous vehicles. The first is safety. Given passengers will be putting their lives in the metaphorical hands of autonomous vehicles, it's our duty as engineers and scientists to design a system that is as safe as possible. We really take the view that we can't compromise on safety. Not only do unsafe vehicles put their passengers in jeopardy, but they also put widespread adoption of AV technology in jeopardy, as it fosters public mistrust. Runtime efficiency is also important, particularly in fast-moving environments, to ensure the AV can react quickly. This also contributes to the safety of the system when deployed. Lastly, the comfort and smoothness of plans is essential to wider adoption of AVs. We call this planning quality. However, existing methods struggle to achieve all 3 and tend to make a trade-off between these desiderata. The principal trade-off tends to be between runtime efficiency on one side and safety and comfort on the other. Let's discuss 2 popular families of methods that tend to fall on either side of this dichotomy. optimization-based planners, and data-driven planners. Optimization-based planners can produce provably safe and high-quality plans, but are typically slow. There's an example of that on the right-hand side. But data-driven planners, however, tend to be fast, but normally have no guarantees of safety or quality. In this paper, we propose an approach that attempts to achieve the best of both worlds by combining these two approaches and to satisfy the three pillars of AV planning. Our method is an efficient optimizer with a data-driven initialization. This achieves efficiency as the optimization is made easier through an informed initialization, and it guarantees safety and quality as the optimizer provides a layer of protection from the data-driven initialization. So PILOT, the name of our method, stands for Planning by Imitation Learning and Optimization. It uses a deep neural network to warm start an efficient optimizer. The neural network is trained to imitate an expensive-to-run optimization-based planner that is only needed at training time. So let's talk about training. Vanilla behavioral cloning is not sufficient for effective imitation, as errors compound and the distribution over states seen by the expert doesn't match the distribution encountered by the learner. To mitigate this, we use DAGA, dataset aggregation, which augments the dataset online with data from PILOT running in the loop of a simulation. This can be broken down into the following steps. First, pre-training the network using a base dataset of planning problems labeled with plans by the expensive-to-run planner. Then new problems are sampled from the state distribution induced by the learner's policy when run in simulation. The new planning problems are solved by the expert, expensive-to-run planner. These problem-plan pairs are added to the base dataset, which the neural network is retrained on. Then, at inference time, the trained neural network warm starts the efficient optimizer, which, when it converges, ensures the satisfaction of safety and smoothness criteria, without a major reduction in runtime efficiency. We do a case study of PILOT using the two-stage optimization-based planner from Irish et al., which is previous work from the 5 Edinburgh team to appear at TRO later this year. And we refer to this two-stage optimization-based planner as 2S-opt. And we use this here for PILOT as the expensive-to-run expert planner. This planner solves a simplified mixed integer linear programming formulation of the planning problem to enforce hard constraints of safety before feeding the result to a kinematically feasible constrained nonlinear programming solver to produce safe and smooth trajectories. 2S-opt produces high-quality plans, but at the cost of runtime efficiency, making it a good candidate to be the expert for PILOT. In this case study, PILOT and 2S-opt share input representations, and these have three components. A bird's eye view of the scene, the reference path the ego attempts to make progress along, and predictions of other dynamic agents transformed into the reference path coordinate frame. If it converges, 2S-opt guarantees a safe and smooth trajectory given those predictions, as feasible solutions from 2S-opt's optimizer can't break hard constraints on safety or smoothness. In our use case of PILOT for 2S-opt, we use the same second stage as 2S-opt does, the NLP solver, for the efficient optimizer of PILOT. Following the PILOT framework, we use the trained neural network, which has been trained on 2S-opt with L2 loss, to warm start initialize this NLP optimizer. This diagram visualizes the implementation of PILOT for 2S-opt. So as in 2S-opt, the state is first transformed to the reference path-based coordinate system. It's then encoded into multi-channel grayscale images. These were chosen for generalizability and scalability reasons. The spatial encoding allows an arbitrary number of road users in an arbitrary road layout. These images are used as inputs to the CNN neural network layers that has been trained on 2S-opt with DAGA. The output of those is flattened. Other scalar inputs which aren't visualized are then appended and fed into the dense layers. This is then fed to the NLP solver, which is the efficient optimizer, which then outputs a trajectory in the reference path coordinate frame, which is then transformed back into the global coordinate frame. So moving on to the results. Our results cover first how PILOT compares to the expert optimizer imitates. We then have two ablations, one comparing PILOT to the neural network alone, and another compares Pilot to using the efficient optimizer with heuristic initializations in place of the imitation neural network. And lastly, we compare to an external method, constrained policy network. So the results used the Kala simulator. And here we talk about problems, where one problem is a single planning instant, which is one time point with fixed predictions for an 8-second time horizon. And the plans are also for an 8-second time horizon. So we pre-train Pilot first with a dataset of 20,000 problems from Kala's Town 2. We then run Dagger in Town 2 with up to 40 static or autopilot vehicles. And the results that we show here are from comparisons on a benchmarking dataset of 1,000 problems from Kala's Town 1. So here we compare to 2S-opt. Pilot achieves a significant reduction in runtime. It's around 7 times faster when comparing to 2S-opt, which is what it imitates, while hardly sacrificing planning quality. There's a minimal average increase here in the optimizer cost function. And this whole comparison is made over the 962 out of the 1,000 problems from the benchmarking dataset where both Pilot and 2S-opt converge. And this video shows 2S-opt and Pilot actually running with the planner in the loop for this simple overtake scenario. In our first ablation, we compare Pilot to the imitation network alone, that is, without the optimization stage afterwards. This plot shows the constraint satisfaction on the y-axis for Pilot and the network for different hard constraints used by the optimizer. So as you can see, the network, which is in green, doesn't satisfy as many of the optimizer's safety and quality constraints as Pilot does, particularly the equality constraints related to kinematic feasibility. In our second ablation, we compare Pilot to the efficient optimizer when initialized by 4 simple heuristic initializations. This comparison in solve time and cost is only on the problems that both 2S-opt and the efficient optimizers solve. The reduced NLP solve time implies Pilot's neural network initialization produces trajectories that are easier to optimize. One heuristic, constant acceleration, has a slight advantage in NLP cost, but solves far fewer problems and takes significantly longer to converge. And lastly, we are comparing our method to an external optimizer-free method, constrained policy network, or CPN. This trains the neural network directly on a loss function constructed from the constraints optimized by the NLP solver, with ReLUs emulating hard constraints. We used a far simpler training dataset with only 3 static vehicles, as training the CPN was highly unstable. This plot showed that CPN struggled to consistently satisfy kinematic, jerk, or collision constraints. So in summary, we propose Pilot, a method to leverage the best qualities of optimization-based planning and data-driven efficiency, combining low runtimes with guaranteed safety and smooth trajectories, in an attempt to achieve all 3 of the pillars of AV planning. Thank you very much.
Hi, I'm Chili, and today I'm representing HD Map Night, an online HD map construction and evaluation framework. HD map construction is an essential module for modern autonomous driving. It enables autonomous vehicles to localize them precisely, make instant decisions, and predict objects' motion. However, classical pipelines of annotating and maintaining HD maps involves a complex pipeline and is costly and labor-intensive. Moreover, road conditions are ever-changing. To enable long-term use, HD maps demand constant updates and maintenance. As an alternative approach, we propose HD MapNet, HD map learning framework using modern deep learning approach with onboard sensor and computation. In contrast to traditional map learning pipelines, our framework is simple, cheap, and is able to perceive dynamic environments. We propose a neural network that takes as input n images along with their extrinsics, or LiDAR point clouds, or both of them, and output a vectorized bird's-eye view HD map as shown in the bottom. We test our method on nuisance dataset. Here is a video demo for our HD map confusion. We show 6 input images on the left and the vectorized HD map predicted by our method on the right. The red lines indicate land boundary, the white ones indicate land divider, and the yellow ones indicate the path crossing. We also align LiDAR point clouds for visualization purpose. As we can see, our prediction is relatively robust and temporal consistent. HD MapNet surrounding consists of 4 parts to process surrounding images into bird's-eye view HD map, namely camera view encoder, view transformation module, view projection module, and bird's-eye view decoder. We use pre-trained EfficientNet B0 as camera view encoder to operate on each of the camera images individually, which downsample the images by a factor of 16. For view transformation module, we use fully connected layers to do view transformation implicitly by jointly estimate the ground height. Then, we use camera extrinsics to transfer camera features from camera coordinates to eagle frame coordinates by differentiable sampling. Finally, for bird's view decoder, we use ResNet 18 backbone to output 3 branches, namely semantic segmentation, instance embedding, and direction classification, which will be used for vectorization. HD MapNet can also handle LiDAR input. We firstly voxelize point cloud, and then use a shared point light to extract semantic feature, and finally use bird's view decoder on it, as we have done for surrounding images. Note that if your vehicle is equipped with multiple sensors, like cameras and LiDARs, to combine them is very simple. Remember that we output 3 branches from bird's eye view decoder. For vectorization, we firstly use DB scan clustering algorithm on instance embedding to get instance masks. And then we apply non-maximum suppression on instance masks to reduce redundancy, and connect them by predict direction to get a vectorized HD map. Note that although we only handle 3 classes of map elements in this paper, the extension to others is the same. To evaluate the performance of semantic level segmentation, we adopt intersection over union to measure pixel level accuracy. However, intersection over union doesn't work if the ground truth has no overlap with the prediction. Hence, we also use chamfer distance to measure the curvatures of the connected points. To evaluate instance level performance, we use average precision, as similar to object detection. In this paper, we use chamfer distance as a threshold instead of intersection over union, because most of the map elements are lies. We compare our methods against inverse perspective mapping, leaf splat shoot, and view processing network. From the results, we can see that HD MapNet Fusion achieves state-of-the-art results on all map elements, and for camera-only methods, our HD map surrounding is also the best. One thing worth noting is that for divider and path crossing, surrounding cameras outperform LiDAR, while for LiDAR boundary, LiDAR works better. While for land boundary, LiDAR works better. We hypothesize that this is because there are elevation changes near the land boundary, making it easy to detect in LiDAR point clouds, while on the other hand, the color contrast of road divider and path crossing is helpful information to recognize in images. We will release our code soon, and you should feel free to reach us via email if you have any questions or comments. Thank you.
Right. Well, I'd like to thank all the authors for their submissions. We were impressed by the quality, and you can ask the questions to the authors in the poster session. I would like to apologize for the technical issues we had in the previous poster session. Hopefully this is resolved now. And you can find the link on the for the poster session on the website. I just posted it in the chat in Zoom, and I will also put it here in Zoom as a snapshot. All right, thank you.
Hello, everybody. So, hello, everybody. Okay, welcome everybody. This will be now
hello, everybody.
Okay. Okay. Excuse me for this loop sound. Hopefully now this will be off. So thank you thank you and welcome everybody to the third session of our workshop today. And now we'll have three exciting presentations. One of them will actually be live. Then this will be followed up by a Q&A session. And finally, there will be a panel at the end. So let me start by introducing our first speaker. So Shenlong Wang is currently a visiting researcher at Intel Intelligent System Labs, working with Dr. Vladlen Koltul. Starting this fall, he will join the University of Illinois Urbana-Champaign, the Department of Computer Science, as an assistant professor. And previously, he was a research scientist at Uber ATG and PhD student at the University of Toronto, under the supervision of Professor Raquel Urtasun. And today, the talk will be about towards realistic and scalable simulation for autonomous driving.
Thank you for inviting me. I'm Shenlong from UIUC. In today's talk, I'm going to present how to build a realistic and scalable computer simulation for training and validating self-driving autonomy. As we believe self-driving vehicles will provide a safer, cleaner, and more convenient transportation. To reach this goal, autonomy requires several desired properties. Firstly, we need our self-driving cars to be flexible so that they can interact with traffic participants safely and foresee a short future. And we also need to make our self-driving cars robust and handle corner cases that autonomy may never see during development. And thirdly, we need to make our self-driving scalable and drive in many places with low cost for expanding the geofence. And finally, when we develop autonomy for self-driving, we also need some demonstrably proof that it is safe and it works under certain situations in the real world. So I think there is still a long way to go for both industry and academia to deliver autonomy that satisfies all the four standards. While it is crucial to design new perception, prediction, and planning algorithms towards solving these challenges, in today's talk, I want to discuss from another perspective, how should we build tools to evaluate a self-driving autonomy and answer whether we have reached the goal, or how far away we are if we haven't. Let's revisit the four criteria. Firstly, we expect self-driving autonomy to be able to interact with other traffic participants. This requires our testing environment to also have capacity interacting with the self-driving car, responding to different behaviors of the vehicle. And secondly, since we expect our self-driving vehicle to handle rare cases and safety-critical scenarios, our verification environment should be able to construct such scenarios to allow empirical evaluation. And thirdly, we want to deploy autonomy at large scale, then we also need to verify them at a large scale. And lastly, since we need to have some guaranteed safety in the real world, testing environment should be as realistic as possible. While there is no golden standard to measure the performance of autonomy, but in industry, we typically use three different ways for verification. One common approach is to build a test track with reproducible safety-critical scenarios. It tests the real software and hardware system, but it's limited in scale. Another popular approach is to use pre-recorded data. It's very convenient for developers and researchers who run and iterate, but it's very hard to test safety-critical cases like pre-crash events, because we don't want to take risks to collect those events. Besides, it's also not very interactive. And the final solution is to use computer simulation. Computer simulation is easy to scale and run many tasks, but current industry and academia solutions still has pretty significant realism gap. So in today's talk, I will cover two works pushing the realism and scalability of computer simulation, namely generating the realistic traffic scenarios and simulating realistic video footage of virtual events. Let's move on to the first part. In this project, we are aiming at generating realistic traffic scenarios, and specifically given the self-driving vehicle's current state and a high-definition map of the surrounding area. Our goal is to construct a complete traffic scenario by placing objects with different categories, sizes, and attributes into the scene. This is a task we call traffic scene generation. Here, the self-driving vehicle is shown in the red, vehicles in blue, pedestrians in orange, and bicyclists in green. There are two major challenges for this task. Firstly, traffic scenes are highly structured. We need the generated scenarios to be realistic and reflecting the traffic rules. And secondly, given an input, there are infinite number of output. So we need the generation process delivers diverse results. Prior works on traffic scene generation using different handcraft rules or heuristics, such as topology or scene grammar, which are difficult to design and lack diversity or coverage. Therefore, our goal is to develop a more general method that excludes the need for such heuristics. Let's first see the output parameterization. We represent each actor by its class, position, bounding box, and velocity. This lightweight parameterization can be readily used in existing simulation stacks. And our approach is to model the generation process with a neural autoregressive model, which we call SceneGen. SceneGen is simple and straightforward. At each step in the generation process, we rasterize the current scene into a multi-channel bird's-eye view image that contains information from both a map and existing actors. Then, SceneGen takes this image as input and predicts a distribution for the next actor's parameters. And we sample a new actor from this distribution and insert it into the scene. And we repeat this process iteratively, composing the scene by generating one actor at a time. And finally, when SceneGen outputs a stop token, we then end the generation process. To evaluate the realism of SceneGen, we experiment with two large-scale datasets. Here we visualize our iterative generation process, which we've slowed down for demonstration purposes. Notice that the SceneGen is able to generate traffic scenes that reflects the complexity and diversity of the real-world traffic scenes, just like parallel cars here we show. For instance, here SceneGen generates a traffic scene with many vehicles of a variety of sizes and grouping effects of pedestrians as well. And here SceneGen produces a scene in which two bicycles perform unprotected left turns. SceneGen can also produce diverse traffic scenes given the same input. Here we show two samples from the SceneGen. On the left, we see pedestrians crossing the intersections, whereas on the right, we see a vehicle completing a left turn. We also quantitatively compare SceneGen against a variety of baselines in terms of negative log likelihood and maximum mean discrepancy for different attributes. For all metrics, lower numbers are better. Overall, SceneGen outperforms the competing baselines, and importantly, compared to heuristic method or grammar-based methods, we are also able to produce the exact log likelihood. One application is to find rare scenes that SceneGen thinks that is less likely to happen. Here we show an example of rear scene where the actor is conducting an illegal U-turn. Coupled with sensor simulation, SyncGen can also be used to generate realistic label data to train 3D detectors. Specifically, first, we convert SyncGen's output into 3D meshes. And then we use LiDAR sim, one of our prior work on realistic LiDAR simulation, to generate their corresponding LiDAR point cloud. And finally, with this data, we train a 3D detector that will generalize to real world. Generating such label data does not require manual annotation. Here we show the results of one such detector trained on simulated data and evaluated on real-world data. And they summarize our approach on scenario generation. Next, let's discuss how to simulate realistic sensor data. In this work, we tackle the problem of camera simulation for self-driving. For instance, how do we test if a perception system would detect a vehicle if added here? While testing such situations in the real world may be too costly, risky, or even impossible, camera simulation can help. It can also provide additional training data to better handle situations. However, current methods are not realistic enough and cannot scale to millions of scenarios. There are two main camera simulation approaches. Graphics approaches are 3D aware but require significant manual effort and can still have a visual reality gap. Image editing methods push a realism using generative models with large-scale data, but they are only 2D aware and not easily controllable. Our work combines both approaches to get the best of the two worlds. GeoSim firstly reconstructs the 3D assets from the real-world data, and then inserts a dynamic object into a video sequence. The results are realistic, geometrically consistent, traffic-aware, and scalable. Since manual asset creation in graphics-based approaches is expensive, GeoSim leverages real-world data to reconstruct vehicles in the wild. While this is non-trivial, as 3D ground truth shape is not always available in the wild, and sensor data can be very sparse and noisy. So we develop a self-supervised model to solve this. It takes the input from multiple images and LiDAR and predicts the per vertices deformation on the learnable mean-shape mesh. For self-supervision, a silhouette is differentiably rendered from the predicted mesh and compared with inferred segmentation masks. And the LiDAR point cloud consistency loss is also applied. Using the reconstructed 3D mesh, we can perform novel view warping of the source image to a new target poses. We built a large and diverse asset bank with over 8,000 unique vehicles. We now show how GeoSim leverages the assets library to insert actors and simulate new images. We firstly automatically generate a plausible placement and trajectory that complies with the existing traffic. An asset is then randomly selected for rendering. We then render the selected object at the target pose. We account for occlusion by using dense depth prediction from a pre-trained depth completion network. And additionally, since our assets are in 3D, we can then render them inside the graphics engines to obtain soft shadows and compose the shadow map onto the image. And finally, we perform post-image composition. We use a synthesis network to handle inconsistent illumination and implement the discrepancies at the boundary so that the vehicle fits into the environment seamlessly. Here is an example of our approach applied to video simulation. Notice that our simulated objects are temporally coherent and that the added vehicles obey the traffic rules and have a reasonable motion. Unlike 2D-based approaches, we can simulate consistently across reasonably long time horizons. Notice that the vehicle in front. GeoSim's retrieval-based approach from the real-world data allow us to simulate the flashing braking lights. Notice that in this scenario, we intentionally simulated vehicles that are running the red light and cutting into the police car's lane, creating a very interesting scenario. Being 3D aware means that we can do multi-camera simulation that is physically plausible. Here, the top view shows that one of the side cameras, while the bottom view shows the front-facing camera. The 4 vehicles simulated by GeoSim are consistent across different cameras. And here are some additional qualitative examples. Can you tell which vehicles are simulated? The answer is here. GeoSim simulates diverse scenarios, such as different types of occlusions and different viewpoints. We also conduct visual comparisons. For existing camera simulation approaches, one can easily detect that the added object due to the geometrically invalid results or unrealistic appearance. But GeoSim images are hard to distinguish from the real images. In a human study, users heavily prefer our method over existing object insertion method. And in addition, our hybrid geometric guided warping method significantly outperforms other rendering options, such as graphics-based method or 2D image synthesis method. Furthermore, with GeoSim, we obtain cost-free annotations for data augmentation, which improves the performance across multiple segmentation methods. And GeoSim is generalizable to different geographic areas and camera configurations. Here we show results in Argoverse and obtain very realistic results, further demonstrating that the scalability of our approach. So in summary, we present a neural autoregressive generative models to create realistic traffic scenarios and a geometric guided simulation framework and achieve great realism for object insertion. Both papers will be also presented in this year's CVPR. Next, I will discuss some remaining challenges for self-driving simulation. Firstly, we are still very far from full photorealism with unsolved problems. For instance, in our data-driven simulation, we focus on object insertion and haven't simulated the full video footage if the camera view diverges from the original recordings. Recent advances in free view synthesis demonstrate promising results in dense view interpolation, but we also need a stronger capacity to push view extrapolation, as we cannot densely scan the scene in the self-driving cases in the real world. Another challenge is that we haven't been able to accurately model the physical process of alighting and imaging, like understanding the global light environment from images and even relighting the scene, or reasoning sophisticated camera materials in the wild. Modeling such physical properties is a cool and important direction towards creating photorealism. And in today's talk, I mainly cover how we should push the realism of simulation. But only realism is not sufficient. There is an infinite number of scenarios for us to simulate. We need to identify what we need to simulate in order to improve autonomy. Being arbitrarily challenging might lose realism, while a common realistic scenario might not be helpful to improve autonomy. I think the rule of thumb should be what lies in between, being challenging while proven to be realistic. But how to achieve this goal is not clear yet. Another important question is whether we could draw any conclusions by running autonomy in simulation. If we succeed in a simulated scenario, does that imply that autonomy is likely to succeed in the real world? I don't think we could provide a concrete answer yet with our current simulation and autonomy scheme. Towards this goal, we need to push from both sides. We need to build a simulation environment that is able to provide a measurable reality gap. For autonomy, we might also need to push verifiable or certifiable autonomy. And this slide summarizes peer-reviewed conferences that I've covered in this talk. And I would like to thank my co-authors, and I'm happy to take questions.
Okay, thank you very much for the talk. So just a reminder, you can ask questions on the chat on both Zoom and YouTube, and we'll have a Q&A session later on to address this question. So the next speaker is Professor Sergey Levin. So Sergey Levin is an assistant professor in the Department of Electrical Engineering and Computer Science at the UC Berkeley. He received his PhD in computer science from Stanford University in 2014, and his work focuses on machine learning for decision-making and control, with an emphasis on deep learning and reinforcement learning algorithms. And not surprisingly, the talk today will be also about reinforcement learning, but one without trial and error. Let's play the video.
Hi, my name is Sergey Levin, and today I'm going to talk about the kinds of reinforcement learning technologies that could perhaps one day enable end-to-end learning of autonomous driving strategies. My goal in this talk is not to convince you that end-to-end learning is the way to go for autonomous driving, but rather to discuss if we were to actually try to do end-to-end RL for autonomous driving, what might that look like? And what kind of technologies are being developed now that could make that possible? So the basic principles are fairly straightforward. If we want to do end-to-end learning of autonomous driving, we need high-capacity representations that can actually represent driving strategies, and deep networks offer us a very appealing possibility for this. And we need algorithms that can actually learn control strategies of the kind that you need in autonomous driving, which means we need reinforcement learning algorithms, because reinforcement learning algorithms are what provide us with a formalism for decision-making and control. So it's a pretty safe bet that if we can do end-to-end learning of autonomous driving, it's going to have the form of some kind of reinforcement learning procedure. So together, if you combine reinforcement learning with deep networks, you get generalizable control methods that could be suitable for open world problems. So what do? Well, okay, what's the obvious thing? Have an autonomous car that tries to drive around in the world, learn from its experience, modify its strategy, and then try again many, many times. That's a really bad idea. Don't do this, right? Because the first thing that you do when you deploy your untrained policies is going to crash. It's going to experience some catastrophic failure. It's going to kill somebody. This is not a good idea. But this is not the only way to do reinforcement learning. And the thesis of this talk is that what we should really be doing if we want an end-to-end approach is offline RL. Basically borrow an idea from how other fields have approached the problem. In computer vision, there's no training from trial and error. You learn from data collected in many diverse settings by many different people. If you want to learn to recognize speech, again, large diverse data sets are the way to go. So in order to deploy deep RL algorithms to these kinds of problems, we would want data-driven reinforcement learning methods. Reinforcement learning methods that learn from large, previously collected data sets. So instead of doing this, what we would do would look more like this. Take a large data set collected by human drivers or previously deployed autonomous driving systems, use it to train up the best autonomous driving policy you can, and then if you are not happy with how well it's doing, consider deploying it into the world some more to fine-tune it further, but only once it has reached some basic level of competence. So, can we develop these kinds of data-driven RL methods that can utilize large previously collected data sets? In conventional on-policy RL, of course, we learn from trial and error, and that's exactly what we want to avoid. Offline reinforcement learning is the branch of RL that studies this question of learning from previously collected data sets, and it's in its kind of most basic form, offline RL is concerned with learning entirely from previously collected data sets without any online interaction, which is basically the first part of this pipeline. So in today's talk, what I'm going to describe are some algorithms that we've developed that I think could serve as stepping stones in this direction. I'll first describe how we can develop offline RL algorithms with guarantees on performance. And then I'll discuss how some of the concepts from these algorithms can actually be also leveraged to enable online fine-tuning with active interaction that also inherits some of these appealing guarantees. And then to conclude, I'll briefly discuss some results from some of our recent experiments in actually using data-driven control for real-world robotic systems, not autonomous driving systems on city streets just yet, but ground robots you can think of as kind of sidewalk delivery style applications. So let's start with the algorithms. A quick primer on the basics of off-policy RL. You have an agent that takes actions, which you know with A. The world responds with states and rewards. And the goal in RL is to learn a policy, pi of A given S, that maximizes the expected total reward that the agent will accumulate. A very useful object for this is called a Q function, which is the total reward that you will accumulate if you take action A in state S and then follow the learned policy. Now, this can be used to then improve the policy if you like, or you can skip the middleman and directly optimize a Q function that satisfies the Bellman equation, which is shown here. So if you can learn a function of states and actions where the Q value is equal to the reward plus the max over actions of the value at the next time step, then you will have learned the Q function for the optimal policy, which you can then recover as the greedy policy. So all you have to do, in principle, to solve RL is to enforce this equation for all states and actions. What we do in practice, of course, is we get samples of states and actions, and to enforce this equation, we solve a regression problem to make the left-hand side equal to the right-hand side. Now, crucially, in order to do this, in principle, you don't need the states and actions to come from the policy you are learning. Those actions could have come from some other policy, like those human drivers or previously deployed autonomous driving systems that I mentioned on the previous slide. So this can be the basis for an off-policy RL method. The problem is that if we just use this naively, the way I've explained it, it actually won't work. So here are some experiments that my students ran a few years back to study this question. They collected a data set on the half-cheetah benchmark task, and then tried to use that data set to learn a policy, in this case with a conventional off-policy actor-critic method called soft actor-critic. And you can see that all of these curves, regardless of the size of the data set, so red is 1 million, blue is 1,000, they're all pretty bad. They're about negative 250. Good performance on this task is around 10,000. But perhaps more problematically, if we actually look at how well the Q function thinks it's going to do, it thinks it'll get an expected reward of about 10 to the 7th power. So the y-axis here is a log scale, and the red line caps out at 10 to the 7th power. So not only is it doing very poorly, it also thinks it's going to do extremely well. It's massively overestimating. Why is that? Well, let's go back to that Bellman equation. I've written it in a slightly different way here. I've written it so that instead of having a max on the right-hand side, it's actually the expected value under pi nu, where pi nu is the argmax policy. So this equation is exactly the same because the value at the argmax is the max. But written in this way, it makes it apparent that the target values, the right-hand side of the Bellman equation, their correctness is entirely dependent on how accurate the Q function is in expectation under pi nu. So if in expectation under pi nu those Q values are erroneous, then you will have erroneous target values and you will do very poorly. So of course then we could ask, are they going to be erroneous or are they going to be correct? Well, crucially, the Q value is trained in expectation under the data distribution, not under pi nu. So you can't really count on the expected value under pi nu being correct. Even worse, pi nu is selected to be the argmax, which means that it's essentially very much like the process you use to find adversarial examples. If there's some action for which the Q value predicts an erroneously large value, taking that argmax will find those actions and exploit them. And that's why you get massive overestimation. To think of this visually, let's say the green curve is the true Q function and the blue curve is your fit. In most places the fit is good, but if you take the argmax, you get exactly that peak that has the largest overestimation. So in addressing this issue, we've actually developed an algorithm that not only combats the overestimation problem, but actually provides some very appealing guarantees that could be tremendously useful for real-world use of offline reinforcement learning methods. So let me tell you a little bit about this. So the problem is this overestimation. And what we're going to try to do is explicitly find those peaks where the Q function overestimates and push them down. And the way we instantiate this is by regularizing the standard regression-style Q-learning update. So the lower line here is the regular objective, minimize the difference between the left-hand side and right-hand side of the Bellman equation. The first line is a regularizer, which minimizes the Q values under an adversarially chosen distribution mu, where mu assigns high value to those actions that have large Q values. So mu explicitly finds these erroneous peaks, and the minimization term pushes them down. So that's a fairly direct solution to the problem, but in fact we can prove that if the weight on the regularizer alpha is chosen appropriately, the Q function learned in this manner will lower bound the true Q function everywhere. And that is extremely appealing because that means that when you train your RL algorithm in this way, your Q function will not overestimate how well the policy will do as long as you've chosen the regularization parameter carefully. So this immediately suggests an actor-critic style algorithm. Learn the lower bound Q function for your current policy, and then find a new policy that maximizes that lower bound. And in practice, we can instantiate this by building on a number of existing actor-critic methods like SAC. We can improve this method further with a better bound, where we not only have this term that pushes down all the Q values, but we added another term that pushes up on the Q values in the data. Now, it might seem like a bad idea if we want to combat overestimation to push up on values, but think about what this will do. If mu is very similar to the data, meaning the high Q values are all in distribution, these two terms will balance out, and it's mostly the Bellman error term which will do most of the heavy lifting. Once you start assigning high Q values to out-of-distribution actions, then the first term will push down on those, and the second term will push up on in-distribution actions, which will pull you back into distribution. So this will still work, but it will actually give you a tighter bound. It won't underestimate as much. In fact, you're no longer guaranteed to have a bound for all states and actions, but you still have a bound in expectation under your policy, which means that it's a bound on the value function, the state value function, which is all you really need because that means that the value of the policy is not overestimated. So we can evaluate empirically whether this bound holds. So to do this, we measure the difference between the expected value of our learned Q function and the estimate of the true Q value with Monte Carlo returns. So here, CQLH is the final method with both terms. CQL equation 1 is the first equation I showed that only has the minimization term. You can see that CQL always has negative values, which means it's always underestimating, whereas a variety of different ensembling methods and prior approaches all have positive values, which means they're overestimating massively. So that's good. We're successfully solving overestimation, and with both terms, CQLH has a much tighter bound, meaning that those values are negative but small. In evaluation on the D4RL benchmark suite, CQL does very well. So these are older results. They're about a year old at this point. Better methods have come out, but at the time, actually nothing worked on the harder D4RL tasks. Behavior cloning was the most competitive baseline, which of course is not a very strong baseline. CQL attains state-of-the-art results on nearly all of these tasks. And then since then, a number of methods that have come out that do better than CQL, many of them actually building on the ideas in CQL and extending them in various ways. So the same thing in Atari. It works very well in Atari games with images. And we seem to know something about why CQL works. We have this lower bound property that explains why it should be expected to lead to reliable results. Okay, so that's for offline learning. Now we could imagine using CQL to train policies for safety critical applications like driving that have this lower bound property. But what if we then want to further fine-tune the policy with some online interaction? Well, it turns out that the ideas in CQL can pretty easily be extended to provide for a kind of safety critic during online collection that can act as a filter to filter out unsafe actions. So let's imagine this kind of pipeline. We're training a policy online now with kind of the regular RL cycle, but every time we go to take an action, we're going to check that action against a safety critic, which is labeled as QC here. And if the safety critic says this action is bad, then we will avoid it. We will not take that action. We'll ask the policy to do something else. So you can think of the safety critic roughly as the negative of the probability of failure. So it's essentially a number between -1 and 0. If you negate that number, you get the probability that action will lead to failure down the road. So the procedure basically looks like this. You collect some data, which you're going to use to update your policy with any RL method. You're going to also use this data, as well as any prior data you have, to estimate your safety critic. And the safety critic is just a Q function for your policy with a reward given by the negative indicator for failure. So you get -1 if you fail, 0 otherwise. So in autonomous driving, this could mean like -1 if you're too close to another car, or if you're too close to a lane boundary, whatever the adverse event that you want. The adverse event doesn't need to actually happen in the data, so you probably don't want to select like a car crash because those might be too rare, but some kind of event for which you can have an indicator like this that you want to avoid at all costs. And then step 3 is you're going to run your policy to collect more data, but then you'll filter the actions using the safety critic. Now, of course, the challenge with this is what if the safety critic is mistaken, right? So you don't need the policy to be perfect to do this, but you do kind of need the safety critic to be perfect. So what can we do? Well, we're going to leverage that conservative Q-learning algorithm from before. Just like before, when we incorporate this regularizer in CQL, we can prove that the resulting value function is a lower bound on the true value. This is the full statement from the CQL paper, but the important part is v hat is less than or equal to v. Now remember that for the safety critic, v hat is basically the negative of the probability of failure. So this equation equivalently means that the probability of failure estimated with a safety critic will be greater than or equal to the true probability of failure. So all we have to do is just use this procedure to train the safety critic, replace the reward with -1 for failure and 0 otherwise, and then the negative of the safety critic is guaranteed to overestimate the probability of failure, which means that it will always be pessimistic. So that means that filtering with it is guaranteed to be conservative. Again, provided you selected your hyperparameters correctly. And by the way, those hyperparameters need to trade off against sampling error. So in a very low data regime, you can still fail simply because a sampling error will overwhelm you. There's kind of nothing you can do about that. So this theorem can be further extended to actually prove a safe improvement theorem, to prove that if you do this properly, your probability of failure is bounded when you improve your policy through online interaction. And empirically, you get many fewer failures with this method. So CSC, conservative safety critic, the red line is this method. The other lines are various baselines, including ensembles, and the lower row shows the number of failures. Now, it's not 0 here, because here everything is learned entirely online, which means that even the safety critic initially is poor simply because it has insufficient data. You could still tune that parameter so that it never fails, but when it's that poor, it just wouldn't allow you to do anything at all. So in practice, you give it some slack, but you still minimize the number of failures. Although an interesting thing to explore in future work is to pre-train the safety critic on offline data and see if you can further reduce these failures, and that's something we're exploring now. All right, now in the last portion of this talk, I'm going to discuss some empirical results on actually using some of the algorithms that I described before. Sorry, there's a typo on the slide. The heading should be using data-driven RL for real-world learning, to use these methods to actually control a real-world robotic system. So the robot that we're going to be working with here is the ClearPath Jackal robot. It's a small ground robot, so not quite a full-size autonomous car. And the way that we're going to frame the problem is we're just going to say, well, the user is going to give you a picture of the goal that they want you to reach, and you have to reach it based on your current observation. This may not be so realistic for autonomous driving, but it's actually pretty realistic for something like a sidewalk delivery robot, where you might want to take a photograph of your front door and have the robot navigate to it. So the model we're going to train takes in your current observation and the goal, and is going to predict the number of time steps to that goal, as well as the action you should take. Now, for longer horizon navigation tasks, we're not going to use this model directly. What we'll actually do is we'll build a graph over landmarks in the environment. Basically, we'll drive the robot around, it'll collect observations, and then we'll connect those observations in a graph where the edges on the graph are weighted by the distance. Okay? So that way, you're not actually directly trying to pick the action to reach the user-specified goal. You're trying to use the graph to plan a sequence of waypoints, and intuitively you can think of it as a sequence of landmarks, and then taking the action to reach the first one. Now, the graph here is not geometric, it's actually topological, so everything is still using this learned model, but this way you can do longer horizon navigation. This is illustrating some of the navigational tasks. The overhead view is just shown for your convenience. The robot only gets to see the first-person images. The far right column shows the goal observations. The second column from the left shows the initial observation. In the middle, you can see how it navigates towards that goal. But crucially, the model here is trained entirely from offline data. It was actually data collected 4 months prior to this project, actually for a different paper by Gregory Kahn, and we just simply reused that data fully offline to train up this model. And we can do a variety of applications with it. We could do, for example, contactless pizza delivery, right? So someone takes a photograph of their front door, their pizza delivery driver, in this case this is the lead author, Drew Shaw, puts the pizza on the robot, and it uses this learned model together with the topological graph to figure out how to navigate to the front door and deliver the pizza. Here's a kind of a little mock patrol application. So you take photographs of a set of waypoints, and you ask the robot to patrol between those waypoints. And again, it's going to use this learned model, trained entirely from offline data, to navigate to each waypoint in turn and look at it and make sure nothing untoward is happening there. Okay, now this does require you to actually have navigated in that environment before to build a topological graph. That graph is not a map, it's not geometric, it's just giving you kind of high-level ideas about how to navigate between landmarks. But if you don't have that, then you can actually do a little bit of real-world fine-tuning. You can actually construct the graph on the fly. And this is an example of this idea that I mentioned at the very beginning of the talk, where you learn a model from lots of prior data, and then you interact with the world some more to really fine-tune that strategy. So that's what we did in this more recent paper called Recon. And here what I'm going to show you is 2 runs. On the first run, the robot is placed in the environment for the first time, having never seen it before. And it gets this target image. Now it doesn't know where this white door is, it sees this white building in the background, but the best it can really do is a kind of a search pattern. And the way the search is done is by actually sampling random latent goals on the fringe of the current graph and navigating them. So the graph is actually built online as the robot explores the environment. Essentially, the robot is trying to pick out landmarks, remember those landmarks non-parametrically, and then sample new latent goals to navigate to on the fringe. And once it sees the white door, it navigates to it and succeeds at the task. Having done this, it has built up its mental map of the environment, and then it can use that mental map to reach the goal again, but this time very quickly in a very direct route. So on run 2, having already built this mental map, it just navigates directly to the goal. So to summarize this approach, we learned this model from lots of offline prior data. The method here is actually simpler than CQL, although we could have used CQL too. And then we combine this with this online construction of the graph to actually navigate novel environments. So some takeaways. Offline RL can utilize previously collected data, and this already addresses a major safety issue in reinforcement learning algorithms. We can develop offline RL algorithms that also have this conservativeness guarantee to give us even stronger safety considerations, and you can use these to constrain online data collection by utilizing conservative Q-learning as a safety critic. And the basic principles work for real-world robotic problems as well. Not yet for driving problems, but at least for navigational problems. All right, thank you very much.
Hello. Thank you very much for the presentation. The next one will be by Sanya Fiedler. So Sanya is an associate professor at the University of Toronto, and at the same time, a director of AI at NVIDIA. She's also co-founder of Vector Institute, and she's Canada CIFAR AI chair. So the talk today will be about image GANs, which meet 3D engines. Let's play the video.
Hi, I'm Sanya. Thanks for inviting me to this workshop today. Today I'm going to talk about image GANs meet 3D engines, which is the common topic of a couple of CVPR papers that we're going to be presenting next week. Okay, at NVIDIA, the vision for the future is in 3D. So anything that is built will be visualized, anything that moves will someday be autonomous, and anything autonomous will be or needs to be simulated. So there is a huge need for large-scale simulation that is physically accurate, real-time, and enables a simulation of really complex virtual worlds. So towards this, NVIDIA has been building NVIDIA Omniverse, which is a platform for real-time collaboration and simulation. In fact, I have stolen a couple of the slides from my manager, Ref, who has been leading this effort to create Omniverse. So Omniverse is this collaboration and visualization platform that essentially allows you to plug in many different available 3D software, such as Blender, Maya, Unreal Engine. All these are just basically connectors into this visualization platform Omniverse, and it also allows you to plug in tech. So for example, if you have a new rendering algorithm, physics simulation algorithm, or AI. So in fact, a lot of our papers are actually demoed in NVIDIA Omniverse. And of course, this simulation platform can serve many different downstream domains here. One of them is simulation for robotics. In particular, here I'm showing a video of DriveSim. The latest update was unveiled at GTC by Jensen a month ago. And as we all know, right, simulation is really key for safety critical applications such as driving, where you need to test your vehicle in simulation before you can deploy it in the real world. And simulation is great because it gives you all this control that you need. You can design the different scenarios, you know, what kind of map you want to drive in, the vehicles, where you're going to place them, what kind of vehicles, pedestrians, and so on, and whether all that is available for you to control. And really the great thing about Omniverse, which runs this drive sim, is that for the ego car, for the ego algorithm running on the ego car, the simulated world is perceived at the same time as a real world. So it's all real-time, physically, physics-based rendering, photorealistic. And here the true belief is that we also want to simulate cameras, right? So for driving, one of the inputs might be camera, might be LiDAR, and we want to kind of have this end-to-end simulation that targets both perception as well as planning. All right, so in my NVIDIA Toronto AI Lab, which is the work I'm going to talk about today, the research has been really focused on serving Omniverse and target applications, meaning we are doing research or AI that wants to synthesize maps, place objects into this in maps, AI for creating 3D content from different modalities, and then AR and VR applications. Of course, the world is not static, so we're also focusing on AI-driven behavior simulation, animation, as well as some domain adaptation techniques that will allow us to use this synthetic data, simulated scenes, and transfer them well to the real scenes. And today I'm going to talk about several works, and it's all thanks to this amazing team and a collaborator that works with us extensively, Antonio. All right, so we're going to try to contrast two different renderers, image GANs and 3D engines. So one way to synthesize images is using generative models. So here on the left side, I'm showing the architecture of StyleGAN, where you essentially sample a latent code from some distribution or normal distribution, and then this goes through some synthesis network that eventually produces an image. An image can also be rendered using 3D content and rendering software, of course. So let's try to kind of compare the two. So both allow for easy rendering. One is just a forward pass-through neural network, and the other one a forward pass-through renderer. Now for the image generative models, sampling different images or different content is super easy. We're just sampling this latent code. So it's as easy as rendering. However, for the 3D engine, this is actually expensive, right? We either need to buy a new 3D asset if you want to render some new scene or create it. So both either is expensive or takes time and expertise. However, with image GANs, we kind of have this limited API, if you will, is the latent code that is being injected into the synthesis network, which gives you a very high level control over what is being generated. Maybe I can control what kind of car I'm going to be generating, maybe even the viewpoint, but it doesn't give you all that detailed control that maybe a 3D engine can give you, right? I can actually modify each individual vertex of a mesh if I wanted to, and modify, for example, a headlight and so on. All right, so images that are synthesized from image networks, that's also not content that is easy to plug in into a 3D engine, like a game engine or simulation, right? GAN is basically synthesizing into the environment that it kind of learned to paste it in. But this, of course, is very easy to do with 3D engines. We also want maybe differentiability. So if I'm given, a new image, we might want to go back and resimulate it with whatever renderer here we're going to be using. So on the left, we might want to inform our latent code, which if we input it through the synthesis network, would recreate the input image. And this is very easily done because this network is essentially differentiable. So we can just use gradient-based optimization to find the code. But this is a lot harder to do in 3D engine. It's a lot harder to actually find a 3D model with texture, material, and everything that's going to perfectly render into this input image. So we kind of want to get nice aspects of both of these worlds. So there is a lot of image data available. If I go online, let's say Flickr, and I just query very, usual keywords that of objects that appear on street scenes like car, van, bus, and so on, you get images in the order of millions for each of these categories. So just imagine the world where we can actually turn each of these images into a 3D model that then we can use in simulation or 3D engine. Okay, so the first thing we're going to do is we're going to consume photos of a particular object class with StyleGAN. And this is here, I'm just showing a couple of samples just to remind you that, StyleGAN really is able to capture that world variability and produce really nice photorealistic renderings. And here is kind of our wish. So we want to take an input image and we want to train some sort of an AI network that's going to produce this explicit representation in 3D. So, mesh with 3D vertices and faces, a texture, so some sort of color on top of this mesh. But maybe we want more. Maybe we also want to have materials. So for example, that something is metallic or furry, and maybe even some semantics, for example, that this part is an eye because maybe we want to animate it. Or for example, even a skeleton of this object so that we can animate this koala here walking. All right, so one way to do this is with this kind of direction called inverse graphics, where essentially we're going to input an image to a neural net that's trying to predict all these properties, so mesh, light, and texture. And typically you would need supervision on all these properties, but the way to avoid this is to plug this into a graphics renderer, which essentially renders an image. And now the loss can be defined on the output image. So the loss is essentially compared in the rendered image of these 3D properties and the actual input image. Now, to avoid trivial solutions here, what one could just output a flat mesh, a flat plane, and a texture that is a copy of the image. Typically, what these methods need to have, which is a paper here from 2019, you need to have a couple of views of each object during training so that you can enforce consistency across different views. So this prediction has to be consistent across different views of the object. And now we're going to turn into StyleGAN's API to see whether StyleGAN has actually has something to offer for us. And in particular, if you start messing with those style codes in StyleGAN, it turns out that those first four style layers actually control viewpoint of an object. And the rest of the style codes control content. So here, we're going to keep content code frozen, and we're just going to vary the viewpoint code. So considers, almost the same object actually synthesized in very different viewpoints. And it's actually quite consistent. Vice versa. So if we keep the viewpoint code frozen in each individual column over here, but vary content code in each row over here, we essentially get many different cars rendered in the desired viewpoints that we want. And this is precisely the data that we actually need for 3D reconstruction. So all we're going to do here is enforce this consistency, not me going out and taking different pictures of the same car, but basically using these GAN-generated views. These are some results, basically using this D-bar network that we introduced a couple of years ago. And the only trick is just to use GAN-generated training data. So here is the input image. And on the right side, I'm showing basically different renderings of the same prediction, different viewpoints, just to persuade you that 3D looks good. And now essentially, have an inverse graphic networks that can take any image and produce a nice looking 3D model, which basically means that sampling 3D models is as easy as sampling images. And because this is a 3D model, we can now also insert it into a 3D engine. Here I'm plugging into Omniverse. So picture in on the right, and the model appears in some scene that I have chosen here, and it's all as fast as you're seeing. It's all real time. This maybe does not look, same quality as an artist would create it, but maybe it's already useful. All right, so maybe the next thing is let's try to get even more things from image GANs. Okay, so again, this is our style GAN over here. And we're going to turn now not to this API here, to this latent code, but to actual synthesis network. And let's look at this image, right? So if we look at this image, you can see that style GAN is really understanding both geometry and semantic composition of different parts of this object. Everything looks perfect, right? So we're hypothesizing that in order for this generative model to kind of render this image over here, then this pixel-wise representations that the synthesis networks needs to learn internally needs to actually capture this kind of semantics, okay? And we're gonna basically try to teach style GAN what is synthesizing. Okay, so we're gonna sample some images from style GAN, and we're gonna ask an annotator to label this image with semantic segmentation. And in particular, we're gonna ask them to label it to the level of detail that the style GAN is able to synthesize these images. So in this case, we can see there's a headlight. You can even see a logo here trying to be synthesized, door, handle, and all of these details on the wheels. So we're going to try to produce a semantic map for each of these detailed parts. So, maybe this is something that the annotator would produce. And now we're going to try to add a very simple label branch, similar to the image branch, but now it's trying to produce this labeled image. Okay, what we're hypothesizing over here is that this learned feature representations, pixel-wise feature representations, are already geometrically meaningful. They have already found correspondences of the same object across different views and across different objects in order to create these really nice looking renderings, right? So we're hoping that we need to label only a very few images here to such level of detail. And then we can train a very tiny MLP on top of these learned representations. And we're hoping that this new style GAN with this label branch is going to be able to predict also semantic segmentations. So here comes our dataset GAN, where this is precisely the idea. So we're going to be sampling a couple of images, very few. We're going to ask the annotator to label them according to some chart that we define. And then we're going to train this very tiny label branch over here. And this basically turns style GAN into a dataset generator, because now we can synthesize both images along with their labels. Okay, so now we can, basically synthesize infinite amount of data if we want to, and we can use this data set just as a real data set, right? So we can train any downstream segmentation network. In our case, we use deep lab, but you can use the latest transformers to train like a semantic segmentation network on this data and then test it on any real data that you want. So here I'm just showing the entire label data set here for faces and for cars, only 16 examples for each individual class. So this is probably small even for a pre-deep learning era. So these are the examples of the synthesized data set. So on the left is the sampled image, and on the right side is the sampled segmentation mask. This is for faces. And here are the results for part segmentation, and I really love this plot. So on the x-axis, you have the number of images that we annotated, so 5 would be 5 annotated GAN-generated images, and on the y is performance, a mean IOU over the the number of part segmentation masks. So these are a couple of baselines that we implemented that use semi-supervised learning to train, and you can see that our method, which is here in blue, even when we have a single example, it's like the gap is huge, right? So we can actually outperform these methods by a lot, even when they use 25 or even 30 times more label data than us. But really the interesting part is over here. So with 19 annotated images, we're essentially matching the performance of a fully supervised deep lab that was trained on this real data set AD, but using 2,600 training examples, so almost 100 times more data. And we're matching basically the performance of this. Here are some results. Basically, this train network, train deep lab, just running on some driving videos. here, Jensen's keynote. All right, so now coming back to our 3D task. So we have, images can go to 3D mesh. We can also predict texture as before, but because now Stallion also understands part segmentation, we can also predict parts as well as the texture, right? And this is really nice because if we have this kind of semantic understanding of the object, now we can just place correct materials. I know this is a windshield, so I can place something that's going to be transparent. If this is a headlight, I can animate it. I can switch on the lights. And if this is a wheel, I can just replace that predicted wheel, which might not look so good, with a rigged wheel. Here are some results. And from this image, we can go to this animated 3D model in real time. Cool. The project page coding data is going to be released this week, and we're also preparing a benchmark for this very few shot part-based segmentation. There is also a nice other aspect of having this really detailed part segmentation. We can also do interactive image editing by essentially the user editing part segmentations, and we're kind of optimizing the latent code and then synthesizing that edited image back. So you can have a pretty nice control now over the parts of the object. Okay, so of course the next question is, what about video? We can do awesome things with images, but we want to do the same thing for video. And in particular in driving, we have just lots of data available by just collection vehicles going around and capturing these videos. A lot of it may be unlabeled. Okay, so here we're going to present DriveGAN next week, so I'm not going to talk about the details, but essentially we want to have a generative model of video, and not only of video, we want to have it a neural simulator. So we want to enable the user to actually control what is being generated here. So there's going to be a wheel that the user can rotate, as well as control the speed. And then the generative model is DriveGAN, that is based on StyleGAN, is going to be synthesizing frames. And using kind of similar tricks that we also use in dataset GAN, you can have this environment, this neural environment, somehow interactive as well. Let me play this video. So the quality is not perfect, but it's getting there. So here you can add cars, and you can change the weather, the time of day, and so on. And of course, you can do the same stuff as with that data set again by labeling a couple of images with semantic segmentation. And this is really early results, but it shows signs that with, again, very few labeled examples, you're able to synthesize both images and their semantics. And of course, what the future brings is improving the quality both in image generation, which we're hoping then is also create better segmentation. This is just a funny video that I wanted to show as a closing. Notice here the user rotating this wheel, and it's trying to basically make an illegal maneuver. It's trying to get out of the road. And what the GAN does, it's not allowing it because it has never seen any training data, has never seen a crash on a legal maneuver. So instead, it takes a little bit of delay, and then it starts repainting the map. So it basically makes it basically rotates the road instead, which basically means that maybe we need to combine these neural simulators that train purely from data and game engines where we can actually make these illegal maneuvers that maybe we don't want to do in the real world when we're capturing data. So in conclusion, image GANs are great. They learn both geometric and semantically disentangled features, and we can utilize these features really efficiently for few shot learning of pixel-wise and 3D tasks. And really kind of what we have been working on is marrying image GANs as renderers with graphics-based simulators. Thank you.
Thank you very much for the presentation. And now it's time for the live Q&A session. So just a reminder to the audience that you can actually ask the questions either on chat of either YouTube or Zoom. And if I could ask the presenters to actually switch on their camera and unmute when needed. So yeah. So once again, thank you very much for your super interesting presentation. And let's start with a question to Shenlong. So there was a question in the chat. Is it like possible to make SceneGen actually produce rare but realistic scenes rather than unlikely, unrealistic scenes by sampling with small negative log likelihood?
Yeah, that's a good question. For SceneGen, I think we're currently pushing the realism. That means that we want our samples to be realistic. That being said, the sample that SceneGen doesn't think it's realistic, it might be still physically possible and could happen in the real world. I think this is something that regarding also another question about, what does it matter for which scenarios that we should generate and which scenarios that matter for developing our autonomy. I do agree that just realistic is not a good one, and some unrealistic or corner cases that our network think it might be rare, but it happens, has a lot of merits. And this is also one of the small examples that we show, but I think it's worth explore even more.
Okay, thank you. So I have another question to Sergey. So I was wondering if there's something can be done, that in the offline RL setup, like we still have to define the reward, right? And like the defining reward can sometimes be error-prone process, as we might know. So I mean, is there something that we can do about that one?
Well, yeah, there's definitely more clever things we can do. Roughly speaking, like what one mental model we could have for these kinds of things is that you have a perception system, a vision system, and your vision system detects what's going on right now. And then you have an RL system, and the RL system can tell you, if you do certain things, what will happen basically in the future. So if you can detect something, then you can plug that in as reward terms and start predicting it. That might still not be good enough because you might not know what you want the algorithm to do. In which case, there's a pretty vast literature on things like inverse reinforcement learning and imitation learning that we can try to leverage. It is definitely possible to take inverse RL methods and combine them with offline RL and have offline inverse RL, and that's totally a thing you could do. In the same way that each of those introduces additional challenges, it makes each thing kind of harder, but it's definitely possible.
Okay, thank you. Okay, so we actually run out of the questions. So maybe let me ask a question to Sanya. Do you think that it would be kind of like important to try to kind of like merge the extended variety of the images that we can generate showing your method with the planning actually? Or do you think it would be kind of like enough to use this for prediction for the perception system?
You mean like for the video generation?
Yes, yes.
Yeah, I mean, it's a very long-term goal. Obviously, it's not anywhere near ready, but that was the full idea is to have a neural simulator, right? So there is an ego agent in the loop that can make any actions, which means a planner, right? A perception and planning. And then there is a generator that is basically painting what the world should look like in a reaction to that action. So the long-term goal would be that these neural simulators that learn purely from data would behave just like a graphics-based simulator, which handles both perception and planning. We're nowhere near there, but I think the answer is going to be somewhere in between. As I've shown, is that if you're just training from these data-driven methods, then you just can't generate certain things that you have never seen, accidents, illegal maneuvers. So I think a combination of game engines or graphics generators with neural generators probably the right way for the future to get both the realism as well as anything like all these corner cases.
Yeah, that's like a very interesting perspective. I mean, so we actually had the project of like with Sergey of doing this for Atari games, right? But like actually going with all this all the way to autonomous driving, this would be super exciting. Okay, I think we're actually like running out of the time of the Q&A session, so I think we can already switch to the panel. Panel will be led by Sergey and Eran, and actually will be also helping in the second part. And I think we have more panelists joining us. Yeah. So I will now give the voice to Sergey and Eran. Thank you.
Yeah, thanks, Blazik. Welcome to the panel. I think great talk. I think we just directly jump to the questions, given we don't have much time. I think the first question I want to ask the panel is that, so we've been talking about all these cool research work, and then data has been always on the background, right? So the question is, what's the data requirement? Let's say we want to solve, let's say, L4 for San Francisco, right? And so, given the current technologies, so are we talking about like a couple hundred cars collecting a few months or a year? Or, are we talking about like really the press has been talking about you need to collect billions of miles in order to, let's say, solve a city? Yeah. So yeah, just want to see, yeah, who wants to take the question? Okay, Charles, you want to take this question? I'm going to ask the industry.
I'm not sure whether I am the right person to answer. Just maybe share a few points I have. I think regarding the data, it's maybe more important to think about the quality and the diversity instead of the mere like quantity, how many hours. If you take data like a car doing a loop or running on the straight road for even billions of hours, it didn't add too much diversity to your database, right? So, but how to quantify that, it's I think another question. Whether your diversity meets your need, I'm not sure. And also I think it's challenging for the simulation as well. You can simulate many normal cases well, but then does that cover the long tail cases, which really matter for your final metric on MPCI? Yeah, maybe others can say more about this.
Maybe a couple of thoughts there.
Yeah, go ahead,
first, I guess the final metric is my expert intervention is not the final metric, as I think most of us will agree on. But I think to your point, there is if the only mechanism that you have to get training data has to be real data, and you need to drive a lot such that you observe things that are less common.
Right.
If you have the capabilities of a simulator that can really generate high fidelity in terms of the appearance of the sensor, as well as the behaviors of the actors, and you can do it in a controllable way so that you also have an understanding of how complete your scenario set is, etc. Then there is no such a need for driving millions and millions of miles of, in the real world.
Right.
So it really depends into what you have in front of you.
Let's say you can create the best simulator, right? But you still have a gap, right? You still need real world data because you, especially those that you cannot imagine, right? That do happen in real world, right?
So there is always a need for the real world because you need to at least understand whether there is a gap in the first place, right? So by definition, you're gonna need to drive in the real world.
Right. Yeah.
Now the question is, how much can you drive that gap to basically be inexistent? And one of the things that is also important to understand is this gap is not just a function of the simulator. It also depends on your autonomy system. Some autonomy system has requirements that are, that if you deviate a little bit, then they behave in a very erratic manner, right? Say that if you don't calibrate your intensity of the LiDAR perfectly, then you suddenly cannot do anything, right? So it also depends into how you build your autonomous system and how robust that is, right? And this together with, things like adversarial examples, right? And a way to generate things so that you can discover where you fail is a great tool to drive, to avoid driving, so many miles. Now there is still a need for driving, right? It's not that you can just remove it.
Right. Well, the question is how much, right? So are we talking about, right, like, a few hundred cars driving around for a few months, a year, or are we talking about like, really billions of miles, right? Just say focus on a city, for example. Right?
Maybe let me take a stab at it. So I joined the panel late. So I'm Ashish. I lead the autonomy team at Lyft Level 5. So I think it really depends on the kind of approach someone is taking to build autonomous driving. I think so far in the past, people have associated the need for data with the need for perception.
Yep.
And like to train like perception system. And typically for that, actually, you don't need that many cars, that many miles, pretty much as long as you have some number of agents in the scene, that data is useful. But as motion planning and prediction are becoming more and more machine learned, the need for the data over there, because the interesting behaviors that you encounter are very, very sparse. They are much more sparse than what you actually, like how often do you see a jaywalker or maybe somebody pushing like a stroller in front of the agent. Yeah. So I think anyone who is actually today trying to machine learn behavioral planning or like prediction, they end up having to actually drive a lot more just because the real world is quite sparse and the interesting events are very, very sparse. In terms of putting an absolute number on the number of cars needed, I think in practice that really comes down to the budget constraints. So if somebody has extremely expensive LiDARs on their car, in practice, today, probably the largest fleet with LiDARs is maybe 600 in number. That's like after like years of billions of dollars of investment. So I think this is a question to the community that we have to think about more scalable ways of getting data, where maybe you can actually get data from cheaper sensors, and still you can actually build a competitive autonomy stack on top of it. And maybe that may be easier to scale to like maybe thousands and thousands of vehicles. Because one thing which is quite clear is like it is quite difficult to actually scale cars with expensive LiDARs to like thousands in numbers until because most of these cars are actually not even generating revenue today. So how do you justify the value proposition of actually having thousands of such vehicles? So maybe I wouldn't directly say how many cars you need, but maybe it's the right question to ask is that what sensor solution do you need so that you can actually scale to like a pretty large fleet?
Yeah, so I'm implicitly assuming that we're using the dominant approach where we have these dense LiDARs with cameras, right? And then radar, yeah.
I think in dominant approach, the bottleneck is the cost.
Okay, I see.
Pretty much you cannot, it's just extremely costly. Like the biggest fleet with dominant sensor suite today is maybe at like under 1,000. So I think it's kind of unrealistic to assume the availability of so much capital that people can scale to tens of thousands with the dominant approach, at least in the near term.
Well, does Amazon have any plans to put LiDARs on their delivery trucks? I mean, they have a fleet of thousands of cars, right? I mean, they could get the data in no time.
That is true. Yeah. Well, Lux is part of Amazon. Yeah.
So I want to make some comments on using the real data to collect those corner cases, especially using the same autonomous platform to collect those corner cases. It's never enough for an industrial company to collect like millions of miles. There might be just a few corner cases that might be helpful. Instead, I think we should think a little bit more smart on where we can extract the data, right? What we care is mainly just corner cases or safety critical cases that will fail our autonomy. Then there are a bunch of dash cam or more easy data that even on YouTube, there are some traffic accidents or pre-crash events that I think the goal is that we could potentially try to extract the morphology of those scenarios and try to reproduce. Just want to echo what Raquel said, reproduce tons of different, similar scenarios, similar pre-crash events in simulation for development. And also, since you mentioned with current technology, I think with current technology, even for validation, regardless of how many data that we have, real data we have for validation, we cannot say any guarantee about whether we are safe at the L4 level, right? And I think pushing the autonomy to give us some guarantee and pushing the simulation to be able to recreate a lot of corner cases from some rare corner cases matter more than miles of driving.
Sure. Yeah, I think that's a good point. So there are cheaper ways to do it. Yeah, maybe Peter, you want to chime in since you give a talk about using cheap sensors?
Well, I think that that Asher summarized the point pretty well because we work together.
Okay.
Yeah,
Okay.
Yeah. We recently published a paper at ICRA this year where we did some experimentation about how much you can degrade the perception performance and see the impact on the end-to-end to the planner stack. And what we discovered is that quality matters, but what it trumps is that quantity of data and the different situations that you can see. So I think that we can maybe relax some of the assumptions, maybe focus more on end-to-end metrics, and that allows us to answer these questions more empirically.
Anybody else want to chime in before we move to the next question? Okay, I think, yeah, let's keep this data requirements in mind. I think it's a very important, I think it's related to the rest of the question we want to ask the panelists. And the next question, it's related. So what is the current machine learning gap in terms of, let's focus on perception, right? So, we all know that the current machine learning has issues, right, related to spurious correlations. Do we need a breakthrough in machine learning, say generalization to solve perception, or is perception already kind of more or less solved by the current technique? So, okay, maybe I'll pick someone so we can get started. So Killian, so you're deep in machine learning. What do you think?
Well, the question is always what your goal is, right? Like, what error rate are you happy with? And I think that's a very, very big factor. And I'm not, I doubt there's going to be another big breakthrough anytime soon, whatever that means. Machine learning is going to do its part. You can also make I guess my point is it will get a little better every year. And that's probably what it is. And ultimately the question is that good enough? And I think that's more a policy question than anything else, really.
What do you mean policy? You mean like how good our perception would meet the public policy requirements?
Right. Well, if you want to send self-driving cars out, right? When do you say they're good enough? Right?
Mm-hmm.
And when do you see, when would you say perception is no longer a bottleneck, right?
Mm-hmm.
And ultimately, it's a question of, what are you tolerating? Like, how many mistakes are you tolerating? And I think that, like, for example, you could allow it on highways, right? Where, I mean, Raquel knows a lot more about this, but the error rates are pretty good, right? And I think it would work pretty well. So, I get to answer your question correctly, concretely. I don't think it needs another breakthrough in machine learning, and I don't think there's one coming. And we basically can turn the crank, over the years, and it will get a little better every year. And at some point, we have to say this is now good enough.
Okay, yeah, that's a very good point. Anybody else?
Maybe I can add 2 cents here, my 2 cents.
Sure.
So I don't think that, talking about what is the requirement on perception quality is the right question, in the sense that in the absence of talking about what comes after, it doesn't really matter, right? And if you look at, as the systems, in particular perception, gets better and better and better, yes, doing better at perception metrics does not correlate with driving better. Okay, so if your system is bad, right? So then yes, you see this increase, and it's like, oh yeah, I can make my choices just based on perception metrics, but it's not the case afterwards, right? You need to have a, first, to me there is no difference between perception and prediction, so we should already merge those two. But on top of this, you need to plan under uncertainty, right? And that can tolerate many more errors, and certain actors are more important than others. Certain parts of the actors are more important than other parts because are they maybe the potential area that you're going to collide with, etc. And none of that is reflected in traditional or perception metrics, right? So we need something else, right? So we need to go to a system level metrics in order to really tell us whether we are doing the right thing.
Yep.
So
I agree.
I think that on that comment, obviously, I don't work extensively on autonomous driving per se, but in other areas of robotics, I think there's kind of a similar issue that comes up, is that if we view the perception system as a discrete component, and you have a safety critical kind of application, you almost get the situation where basically nothing is good enough. It's like if you have some small probability of a mistake, but that mistake could be literally anything. And whatever comes afterwards just assumes that the output of the perception system is true. Essentially, nothing is good enough. And in robotics, that's very often the case. So I'm a very big believer in the notion that I think is a little bit related to what Raquel articulated, that we really need to be thinking about perception in a more end-to-end way. That doesn't mean we need to train perception systems in an end-to-end way necessarily, although I do think that's a good approach. But certainly we should be thinking about them in that way, and that can let us basically get over this issue. The thing is, if you have a chain of modules, and each of those modules has some small probability of failure, and each one relies on the previous one, the probability of the whole thing failing increases exponentially as the chain increases. Right? This is like kind of that's the standard thing. So they need to somehow be integrated more naturally.
Yeah, maybe just to add here. So I totally agree that it needs to be a holistic system to look at, and that planner can accommodate or amortize some of the problems, right? So my dad doesn't see on one eye, and he can still drive. Maybe it's not the most pleasant for the passenger, but he doesn't see 3D, but he can still drive. Now, in terms of machine learning, I still think there's opportunities that, or maybe things that we need to solve. So, for example, if there is an intervention that was due to a perception failure, it means that it's a corner case we haven't seen. And now the question is, how do I retrain my network? How do I actually effectively add those very sparse long tail examples successfully to my training data? I don't know the answer to this. Maybe people have kind of solved this problem. And the other thing the machine learning models still suffer from is the overfit of a domain, right? If you train with some sensors, maybe the sensor change, or just going from, Kitty to new scenes to Waymo data set, you can still notice a gap, right? And, some more generalization that's gonna handle different sensors that are gonna evolve, I think you still need it in terms of just like core machine learning algorithms.
Great.
Okay.
So actually, I wanted to ask a question from our YouTube channel. So Alan Zolan, because I think it's very related to this discussion. So that asked that even with infinite data or perfect simulator, the verification procedure itself is an open question. So what's the panel thoughts on how to validate an AV software stack given the resources? And any takers? Okay, so I know, maybe let's ask somebody from the industry about this. So Ashish, do you have any?
Yeah, so I mean, I think infinite data and perfect simulator, I think they're dreams. They're like not a reality. And assuming you actually have them, I don't see a reason why you cannot validate it. So I think we need to come up with ways of validating the system where we will not have perfect simulator and we will also not have infinite data, and we'll also have budget constraints in how much you can spend in actually validating the final solution. So I think so. Going back to the original question, I think just these two assumptions, I believe, are like actually not probably not true. But if they are true, I don't see a reason why you cannot validate in like a perfect simulator. But I think that achieving that is actually probably not possible in like the next few years with the current technology we have. Yeah.
So kind of like, but okay, so assuming that the resources we have currently, so kind of like what would be the best way to actually validate an AV stack? Would this be like extensive use of simulator or?
Yeah, I think we have to extensively build better and better simulator over time. And I think traditionally a lot of simulators were hand designed and like hand curated. And it's becoming quite clear that they are hitting their ceiling. So we need to start machine learning the simulators. And I think there were pretty good talks in this workshop itself on like many different ways of machine learning the simulator. I think in next couple of years, we should see some, probably I would not say like breakthroughs, but like some like massive improvements in our simulation capabilities. And I do believe that they will play a key role in, I mean, you'll always need real world miles, but the hope is that your real world miles are then just to validate the simulator and how good your simulator is, but not really to validate the software. And once you know your simulator is actually good enough, then you pretty much develop a lot of the things within the simulator at that time.
Okay, thank you. Any other thoughts on how to validate AV software?
Maybe a couple more thoughts there. Agree 100%, and as everybody knows, that simulation is an extremely important component of verification and safety. Now, since you cannot just have or test the exponentially many scenarios and things that can happen in the real world, and then let's not forget here that it's not just about testing the motion planner as you typically see in industry, but you need to test the entire software stack. Right, so different appearances might actually have different effects or different sizes or shapes of different objects, right? So this is, way too many things to test, right? So it's important into how you test, when you test, etc. Right, so you need to use a decomposition approach where it's able to validate pieces of your approach, while at the same time having the ability to validate or test everything jointly. And as I mentioned before, the more that your system gets better, the more that is going to really pass all the different tests, right? And so you need to understand whether you have a complete set of tests versus not, which is, as I said, an open question. And you need to have a way to poke this with, say, adversarial, be able to do like adversarial scenarios and things like this. So it's definitely, a complex question. And the other thing that is linked to is what is your operation domain. So it's not just about, okay, let me just test everything. Right, so typically you decide into where you're going to operate, and the way that you decide this is based on the capabilities of your system, right? And this implies also that you need to understand what are the set of things that might happen in this operation domain, and basically you need to understand the probability distribution of those events, understand how well you can do in those events, and then you put this all together to compute your expected risk. And when this expected risk is to the level of that you feel comfortable with, you can actually make a case that actually your system is safe enough, and then you can deploy, right? But even understanding what is the probability distribution of events in my OD, in my operation domain, is an extremely difficult problem. And that's an area maybe where these chip sensors are actually really, really useful, right? Because we can use raw data from just dash cams and things to estimate the scenarios or scenario families or things like this.
I want to make a comment only just doing empirical verification or validation. Currently, we are all talking about, regardless of infinite number of miles or infinite number of simulation environment, it's all empirical results. And just getting empirical results might not be enough. I think we might need to think about whether we could have some guarantees just from our autonomy itself. For instance, suppose like perception is perfect. Can we have guarantees on planning that it will guarantee to be not colliding to the car? Or suppose we have observed some LiDAR points of pedestrian. Can we guarantee that we can always detect? Or if we do not detect, can guarantee that our computer system could give an uncertainty that saying that I might not be certain. And when it says certain, it could be certain. I think if we have this type of formal verification or certifiable guarantees, I think that could help tons, and not only just empirical validation, because to me, empirical validation is not going to be enough.
100% agree with you, Shalong. The problem right now is that for verification of neural nets, you can only do like super simple operations on tiny networks.
Yeah, that's
and the question is, when is this gonna get what will go faster, right? With the two areas.
Yeah. We should definitely call for academia to pay more attention for verification of deep learning, although it's hard. Perfect simulation is also hard. But I also agree, we might make more, solid progresses along the empirical verification side in the recent few years.
Actually, that's interesting, because I actually don't think that's going to happen. I think that's a lost cause. I mean, maybe I'd love to be wrong, but I think, in control theory and so on, like verification has worked really, really well, right? And so we're kind of spoiled, right? For planes and so on, you can verify that they behave, within a pre-specified framework. I don't think you can do this for neural networks. I'd be very, very surprised. It's just too, the functions are just so, I don't think neural networks are very difficult to understand. They just have, they're just very, very highly nonlinear functions with, billions of nonlinearities, right? So how can you reason about it? I'd be very surprised if that'd be a breakthrough. I'd be very happy if it comes, but I think we probably have to work under the assumption that it may not come, and maybe that's okay, right? Maybe it's just, as long as the test data looks like the training data, it works most of the time. Like the human brain, right? Sometimes we do crazy things, but most of the time humans behave pretty normal.
Yeah, the trouble is that any verification system requires some kind of assumption on input, on the input, right? And that's why this works in controls, is you make some assumption that your rocket will never experience perturbations larger than some magnitude, and as long as you're fairly generous about that, everything works. That's just very, very difficult to encode reasonable assumptions in very open world environments. So I'm also actually not that optimistic on the prospect of a sort of control style, H infinity style robustness thing actually panning out anytime open world environments are involved.
I think we are too focused on the perspective of using machine learning model inside autonomy. I think in autonomy, there are quite a few things I think we could certify. For instance, like if we have model-based planner rather than just purely learning-based planner, or if we have a mixture of hybrid version of model, or for instance, like autonomy, the early part of autonomy, the perception side, say like localization. That is something that potentially I think we could make some solid progress with. But I agree, neural networks is just too hard, and make some assumptions at least at this moment, the assumptions are too strong in verification systems.
Okay, great. Maybe let's proceed to the next question. Killian had the view that we just make incremental progress. I think right now, like we're just using human ingenuity, right? We just think about new ideas and try all kinds of stuff. And so one idea is that that works really well in NLP is that the people have found that you can just scale up this transformer model, right? So you have your, as you scale up, as long as your data compute is not the bottleneck, and then your test loss is going down, right? And then at least it's scaling into from like millions to billions and to millions, to trillions of parameters, right? So the question is, so if this is one of the sure way to sort of improve the capability, right? So does this apply to self-driving, right? So is there any gaps, or this will not work? So if it works, will be a reasonable approach. We kind of scale up our model. We like a big model, like solve all your self-driving tasks, right? And then we kind of distill to a student model and then put it online, right? So just trying to see that, yeah. What do you guys think? Yeah.
So I definitely see the I can provide some thoughts. So I definitely see the parallels between the sequence prediction when you look at it that way. In NLP, you see a lot of text, and then you can be kind of with the prefix. You're asking what are the possible continuations, which is very similar to the prediction, being able to kind of foresee what's going to happen next. And I say, why not? That's of course it's different in a way that this class distribution is much more skewed, but I don't see any reason why this shouldn't work. And if you had like a lot of data, you would be able to train very good predictive model of the traffic that you could use. And I think that that data quantity will surely trump the algorithmic complexity as we've seen in other domains.
Let me add one thought here. So I agree that this is certainly a strategy you can play, right? Like add more data, make the model bigger. That always improves things, but it also has diminishing returns, right? And so you basically have some asymptote. And so there's some value of when you say the model is good enough, and could be that that's above or below the asymptote, right? And so essentially what I'm saying is it only gets you so far, right? And if it gives you above the threshold that you need, sure, just double your model 10 times, and just throw money at data, and you're done, right? But it could very well be that the asymptote is in the wrong place, and then you need to do something smarter. And I guess in NLP, what we saw is that basically, you get these cheap gains, right? To just throw more data at it. But at some point that stops, right?
Well, at least it scales to trillion parameter, right? And so do you think by then we will probably have solved self-driving?
I think there's also a fairly difficult kind of algorithms issue that basically the way that we approach these problems greatly affects our ability to utilize data. Let me, I might say something a little controversial, and since I don't, know as much about this this topic in particular as many of the other panelists, also maybe something ignorant, but I'll say it anyway, just for the sake of starting some discussion. Imagine you do have your autonomous car company and your car experiences a crash. There is no, to my knowledge, there is no automated technique right now that allows you to take the data from that, plug that into your algorithm, and have it not crash again if it were to find itself in the same exact situation. That's a manual process. And of course, you'd have, if your car actually crashes, you have all your engineers looking at, poring over it, figuring out what happened, modifying things and so on. But a crash is just a very extreme thing. Imagine that it does something much more routine, but still bad, like it cuts somebody off, it gets a little too close, whatever. Right now, actually taking that and automatically feeding that into a learning system that improves from those mistakes is not something that we use. That's not something we do for deployed robotic systems, at least as far as I know. And that's actually part of why in my talk I chose to focus on offline reinforcement learning. I don't think that's the only answer, but I think that is one of the possible categories of answers, basically algorithms that can improve the entire end-to-end pipeline from experience. And certainly those algorithms aren't there today where the scenario I described would just work. But I do think that thinking about how to get on that path is important if we're really thinking about leveraging ever increasing data set sizes with relatively simple techniques.
Anybody else want to chime in on this question?
Yeah, so maybe without going into crashes, okay, but if you think of interventions, right? So these are, used in the industry as source of data. This is, for example, for Tesla, one of the best sources of data that they have, right? How to automatically just get every time that you touch, somebody touches the wheel, basically you get, up that to maybe labeling or whatever. So there are things like this in industry, and it definitely helps, but you shouldn't wait until it happens to actually be able to know that you cannot handle it. Maybe the different points from what I guess Sergey was making is I think that it's not a size issue, okay. And there's more problems on this. And the first problem that maybe we have in self-driving is that we don't have the right loss function because we don't have the right metric. If we had that, I think it will be much faster. Our progress will be much faster. And then maybe it's a matter of model size. I will argue that it's more than just model size. Actually, in the model itself, there is a lot of beauty and secret sauce. But without knowing how to optimize this. Right.
Yeah, so I want to second to what Raquel said. I think on one side, we don't have the right test loss, right? That's the NLP we can optimize for. But on the other side, we don't have the right input as well. So considering like NLP case, you have tokenized the input, which is like the complete information you need to feed into the model. But for self-driving, what is the complete information you need to feed into the model? Do you feed in the raw sensor data from all the sensors in video form? That's like the full end-to-end learning, which you will face this exponential problem of combinations. And people tend to do that in a more modular way, right? But if you don't feed that raw sensor data, what the form of formulations you define, right? If you define some bounding boxes, that might not be enough. You want to maybe have key points, you want to have gates, you want to understand the geometry of the roads, but who is the person to define those formulations? It's not that very clear. Then combining this formulation unclearness and the test loss unclearness is not that trivial to directly apply the techniques from NLP.
Those are great points. So, oh, Peter, go ahead. Yeah.
Oh, I just had the phone. Well, I don't see that as much as issue. When you look at mu0 from DeepMind, so what they've shown is that the representation can be directly learned as part of the decision-making task. And that somehow can be applied to learn from the actual experience. But I think that the breakthrough there was that you can actually avoid these explicit representations, learn directly from the data to learn these predictive models, and you can use these predictive models in the latent space to actually plan. And I think like with some modifications, that could actually work for self-driving as well.
Well, very good points. Charles, Raka, you guys want to respond?
Yeah, I think the relevant discussion is like, okay, we have seen successes in like games, like Alpha Star, like machines can play games really well with multiple agents. You can see the action space is even bigger than driving. But why haven't this transferred to the real world driving? I think that's probably a very relevant question to discuss.
I think that with the right simulator, you can do a lot of cool things. Maybe some of the things that he's hinting.
Yeah, I think yeah, that I think that might close the gap, right? So like we don't have a really sophisticated simulator up to this point. So Peter, you wanna? Yeah, go ahead, Peter.
Oh,
I thought you want to say something.
No.
Okay, so maybe let me change the topic a little bit and follow up with another question from the audience. And I think this is slightly bad that we didn't get anybody from Tesla on the panel, because the question is exactly about them, and this that they are not using LiDAR for autonomous driving and focus on camera only, I think at the moment, not even radars. So, you know, how do you think about like safety of approach like this, or like, can we get with the current technology to camera only self-driving car? Any opinions on this?
I think it's a question of when, not if. Here, I mean, there is clearly an existential proof, right? Humans can do it, but it's not certainly clear how long it will take. I think there are like some pros to that approach, is that you can actually, a big part of discussion in this panel was the size of data and scale of data. You clearly can actually maybe solve that problem with like a camera only approach. You can get a very, very large data sets, which can maybe even enable trying things like GPT-3, like which was the previous question. But and maybe at some point in time, these methods may start working. I think, but it's not certainly clear whether today we have all the pieces of the technology needed to actually make them work at the same efficacy as what you can do, let's say with like LiDARs, for example. Like LiDARs makes the problem substantially easier, at least today. It's still, the problem is not solved with LiDARs, but at least they make the problem a lot easier. They can make the safety case a lot easier. They help you cut the tail, essentially, the long tail. So I think it's probably a matter of time that we'll see that camera-based approaches may start catching up and maybe even outpace the LiDAR-based methods.
Maybe a comment. Big believer of multiple sensors, and the reason why is safety, right? So yes, there exist humans that can actually drive, as Sanya mentioned, even with a single eye. That doesn't mean that that's what we should be looking at, right? We should be looking at what is our path to develop safely and deploy safely a system that can actually help in so many ways transform the world. And for me, this is about using redundancy and using multiple sensors. Now you need to be able to understand and learn how to do sensor fusion, in a good way, but that's just part of the challenge.
So, any other takers on the camera only?
Jan, you published a paper, Pseudo LiDAR.
Oh yeah, so yeah, I work on this direction in the past. So I believe maybe at some day when we have very good LiDAR sensor, we can use them as a ground truth to train very good stereo or multi-view stereo models, which can achieve beyond LiDAR performance. That's my belief. Also, currently we design some models that can use high resolution images. Therefore, it's possible to detect a long range depth. It may also help LiDAR. So since the LiDAR, the depth, they have some limitation on the depth. For example, beyond 200 meters, it's very hard to see the objects if you use LiDAR point cloud. However, in the image, you can clearly see the objects even beyond 200 meters.
So I think one last thing I would say, like the debate shouldn't be about like camera versus LiDAR. I think it's really more about whether there's a hypothesis that we need a very massive volume of data sets to solve self-driving cars. I think the first question should be around that. And then it is basically, if the answer to that is yes, then the question is like, okay, what sensor set can actually scale to that volume that can give you economically viable, that can actually give you very large scale data sets to actually train like self-driving car systems. So today, the sensor set that is dominant in the industry, which is 3 modalities, high resolution LiDAR, they do have a scaling challenges. And maybe that can be solved in like the coming future as they become cheaper and all that. So I think that probably is like the real debate here. Is like, it's less about camera versus LiDAR, but more about the volume of the data and the price you have to pay for it.
I think that's a very good point. I think it's really, I think it's often misunderstood, and I guess in part because Elon Musk keeps shouting that we don't need LiDAR or something. But it's, it's a pragmatic choice, right? And that's, I think essentially what you're saying is by not using LiDAR, it allowed Tesla to, push out 500,000 cars, right, that all collect data for them. And hey, that's an advantage, right? But I think everybody agrees also that having more sensors will make the problem easier, right? And they have different failure modes. So obviously, it can only be a good thing. And so if there's some way to kind of collect, combine the massive data that you can collect now with, maybe less but more precise data, that in my eyes seems to be the way to go. So I agree essentially that ultimately the question is a little misleading.
Yeah, I want to have one comment. So I agree with Raquel and Kelly in terms of that we should have multiple sensors, and we should definitely have some sensing capability in our self-driving car better than humans. And if the question is if we need LiDAR or not, then my answer might be not sure. But if we need good depth sensing technology, I think that is sort of like for sure if we want to have some, if we want to really push safety. But there are a lot of other technologies like what Yan said, potentially multi-view stereo or binocular stereo, we can push further for the limit. Or even like structure light has been progressing really well. And so long as we have some depth sensing technology that can overcome the issues that only LiDAR can be able to solve, like the dark imaging and also high range, long range, depth sensing. If we are able to have this type of technology, LiDAR then is not a must. But at this moment, I do think we should have LiDAR. rather than just putting those cameras on board and have them to drive, because we know with the current depth sensing from camera, I don't think that is sufficient to guarantee safety.
All right. Well, I guess we're out of time. I'd like to I'd like to thank the all panelists and all speakers for the great presentations and awesome panel. I guess let's go to the poster session.
Yeah, thanks everyone. So we would release the recording if all the speakers are okay for it. Thanks for your attendance.
Thank you.
Bye.
Bye.
Thank you.
Bye. Bye.